And we're live.
Okay. So can you promote Ning Ning Jia as a panelist? He's the second speaker.
I think I had already done that.
Can the speakers raise their hands? Authors, please raise your hands so you can see you. It's easier like that. Zhuang. We have Ning Chang.
Done. So I was checking C. C is working.
Okay. Hello, Ning.
Oh.
Chang.
Good morning, Ning Chang. Welcome. Can you hear us?
Yeah, I can.
Yeah, yeah. Okay.
Zhuang, can you check what Jason Meng wants? If he's a presenter. I don't know if he's a presenter. I don't see him.
I'm checking with him.
Yeah, I'm Changping Meng.
Are you a presenter?
Yeah, I'm the presenter for the third paper.
Oh, but you're not an author, okay.
Which paper are you presenting?
I'm presenting the it should be hierarchical attention. It ReadNet. It should be the third one. There's a third one, I think.
Are you
Let me
in the
check.
correct session?
Yes, because in my session, the third paper is called ReadNet, a hierarchical transformer framework for web article. I don't see. There should be a third paper, right?
What's the name of your paper?
Called ReadNet, a hardcore transformer.
People were looking for you yesterday. Your session was yesterday.
Oh! I thought it is.
Yeah, the people. If you look in Slack, there's a large. They were looking for you.
I didn't use Slack, so I thought it. Oh, okay. Yeah, because on the website, I thought it's today. Okay, okay, I got it. Yeah, maybe I just leave the panelist.
Maybe we can accommodate Jason in the end. No. You're João. Turn on the mic.
Yeah, I'm turning on the mic.
No,
it's me. It's me. Sorry, it's me. I was talking. So your talk is actually not in Google Calendar, but it's on the other ones. So the other ones are more.
There was a small mistake in the program, at least when I copy pasted it to Slack yesterday.
Okay.
So
and somebody noticed. So there's a discussion about your paper.
Okay.
We're going to put your paper on.
Can we put it on the end of today?
A9. I think A9 we have space. 1, 2, 3, 4, 5. No.
Or do it here in the coffee break.
Let's see. Yeah, I guess you may present at the end of this session.
Okay.
Is it okay, Benjamin?
Yes, it's okay.
Okay. So it's ReadNet hierarchical transformer framework for web article readability.
We have space in the question answering session, but not very. In the question answering, we have space, but this one may be better because it's deep learning anyway.
Yeah, I don't know why on my calendar, Google Calendar is today.
Pablo? Do you have a way to reach the authors of the fourth paper?
So are there any other authors in the audience? Please raise your hand.
I searched for them, but
Oh, there.
I think there's Clément.
because we have all the speakers, but then well, Clément is joining in a few minutes. Oh, he's joining now.
And we're lacking the fourth one, right?
Yes, right. So if you have a way to, I don't know.
Hi guys.
Hi Clément.
Hi. Okay, would you like to try to test your microphones and your screen?
Yeah, okay.
Or maybe the first one.
Nazir,
Yes.
you want to try it?
Yeah, actually, I tested my microphone earlier, but I don't know what else shall we check.
What? So,
So I tested the microphone earlier today, and I just joined.
yeah, you want to try the slides? Is that what?
Okay. Shall I start?
Yeah, do the first.
Okay, thanks. Sorry, I just have to. So is it working now?
Yes.
Okay, thank you. Hello, everyone. I'm Mazam Wardifat, and today I'm going to present our paper that we worked with
Wait.
CLEF.
Wait.
Okay.
It was really
It was just a test.
try. It was
Okay.
to start.
Okay.
We have Ningjia on the attendees, João.
Yeah. Yeah. No, Ning. Hold on.
Is it? Oh,
Hold on. Give me a minute.
it's the second one.
No, but hold on. Ning Chang, are you one of the authors?
No, it's Ning Chang is the fifth.
Ning Chang,
Okay.
yeah.
Got it.
And Ning Jia
Is the second.
The second.
Yeah.
Where is she? She was here.
She's here.
She keeps logging in and logging out.
Oh, well, maybe the connection is bad. Okay, shall we start the session?
Yes, let's start the session then.
Okay, so welcome everybody to this session, the Deep Learning 1 session. We'll have 6 talks today. So the 5 were planned, and then the 6th one is ReadNet, a hierarchical transformer that should have been presented yesterday, but that will be presented today. And the first talk is seed-guided deep document clustering. It will be presented by Maza Moriadi Fard. And just to all attendees, you have two ways to interact with us. You can use the Q&A button on the bottom of the screen just to ask questions, or you can raise a hand and then we will unmute your mic at the end of the presentation so you can ask a question. So welcome everybody, and let's start with the first talk.
Okay. Hello everyone, I'm Mazen Wardifar, and today I'm going to present our work, which I collaborated with Thibaut Tona and Eric Gossier, and it's called Seed-Guided Deep Document Clustering. And here in this flow, we can see first the transformation that we did from clustering towards deep clustering, and then from deep clustering toward constrained deep clustering. This is the topic that I'm going to talk about today. But what is clustering? Clustering is the task of grouping unlabeled data points into several clusters based on their similarities or dissimilarities. But what about deep clustering? In deep clustering, we try to learn new data representations which are apt for clustering. In this case, data representations and cluster representatives will be updated simultaneously. Here in this figure, we can see a general architecture of a deep clustering approach. In this case, we have two losses, an autoencoder reconstruction loss and a clustering loss. In this case, the input, which in our case is a document, will be fed to an autoencoder. And in the autoencoder, as usual, we try to reconstruct the input. Then the autoencoder loss function will be computed based on the original input and the output of the autoencoder. And basically, we try to minimize this dissimilarity between the original input and the output of the autoencoder. And finally, the encoded input through the autoencoder will be used for computing the clustering loss. Basically, fx, which is the encoded input, will be assigned to one of the clusters. And in constrained deep clustering, we want to add constraints to the current deep clustering frameworks. In this case, the input is the data and the constraints which are provided by the user, and the output is the bias representation learned through a deep clustering framework. Usually, clustering can be done based on different definitions of similarity or dissimilarity. For instance, in this picture, we can categorize these cartoonic characters, whether based on their gender or whether based on their relation or occupation. And basically, this is called the subjectivity aspect of clustering. One way to solve subjectivity aspect of clustering is to adapt the representations of objects to clustering objective. But when we talk about constrained clustering, what do we mean in terms of document clustering? Basically, different users may be interested in different clustering views underlying a given collection. Enabling them to provide constraints reflecting their needs can then help to obtain tailored clustering results. For document clustering, constraints can be provided in the form of seed words, each cluster being characterized by a small set of words. In this paper, we jointly learn deep representations and bias the clustering results through the seed words, leading to a seed-guided deep document approach, or SC2C. But what is SC2C actually? We propose to integrate constraints on seed words in SC2C framework by biasing the ending representations, which can be done in two ways. One, SC2C doc, and two, SC2C rep. In SC2C doc, we try to reduce the gap in the emptying space between the representation of the documents and the representation of the seed words occurring in these documents. And in SC2C rep, we simply want to bias the cluster representatives based on the seed words. Here in this figure, we can see the general architecture of SC2C doc, the first version that I discussed earlier. So in this case, we can see first here the architecture of deep clustering. So basically, we have the deep clustering formulation and all the losses and architecture, but seed words now are provided by the users. As we can see, for each class or cluster, we have some seed words. For instance, a sport, competition, and champion are the seed words for cluster 1, and finance, stock, market are seed words for cluster 2, and so on and so forth. In this case, similar to deep clustering algorithm, we compute the autoencoder reconstruction loss, and we do also we compute the clustering loss as well. But here we have the additional seed words. So the input document will be masked first by the seed words, and we will obtain the masked input. And this masked input will be fed to an autoencoder. And we use the encoded version of the masked input, noted here. And we try to minimize the dissimilarity between the encoded masked input and the encoded original input, fx. It means that we try to bias the representations from the input toward the representations of the masked document. This is the idea of SC2C doc. What about SC2C rep? We have the same deep clustering framework as well here. So we have the autoencoder clustering loss, and we have also, similar to SC2C doc, the seed words that are provided. But here, for each class, we will average the seed words per class, and which obtains S1, S2 until Sk. And we try to bias cluster representatives, not data representations, just cluster representatives toward the encoded seed words. And by doing that, we just try to minimize the dissimilarity between the encoded seed words and the cluster representatives. In our experiments, we chose deep k-means, or DKM, as the deep clustering algorithm, as it proposes a truly joint formulation of the deep clustering problem. For both SC2C doc and SC2C rep, different dissimilarities can be adopted. Cosine distance performs consistently better for dissimilarity in the ending space than the Euclidean distance. But we found no such trends for dissimilarity in the input space for our autoencoder. And this can yield into two versions for each method, SC2C doc E and SC2C rep E if we use Euclidean distance, and SC2C doc C and SC2C rep C if we use cosine distance. In our experiments, we use two sets of baselines. We use the approaches which do not use the seed words, and we use the approach that use the seed words. So the approaches that do not use the seed words are KM or K-means, which we know that this is like the standard K-means. We have autoencoder plus K-means and DKM. Autoencoder plus K-means is basically pre-training an autoencoder, and after finishing the pre-training, applying K-means on the learned representations. While in DKM, we try to jointly learn data representations and cluster representatives, which, as opposed to autoencoder plus K-means, this is a joint end-to-end framework deep clustering. And the approaches which use seed words are STM and nearest neighbor, or NN. STM is a seed-guided topic model, which belongs to dataless text classification approaches. And this approach tries to cluster documents based on a few seed words. And nearest neighbor, each document is represented by its word ending average and is assigned to the nearest class, represented by the average seed word endings per class. The dataset that we have used are Reuters, 20 News, Yahoo, DBpedia, and AG News. We perform stemming and we remove stop words. And for the seed words, there are two sets of seed words, automatic seed words and the manual seed words. The automatic seed words, we try to automatically withdraw seed words from each collection individually. And manual seed words are the seed words that are provided by other papers and other authors, and we directly use them to validate our results on automatic seed words. And the metrics that we have used are clustering accuracy, ACC, and adjusted rand index, ARI. And in this table, we can see the statistics of the pre-processed datasets. We can see that we have different characteristics in our collections. For instance, in terms of number of classes, we have 4 to 20. And in terms of number of documents, we have 8,000 to 120,000. And in terms of the average length of the documents, it starts from 22 for AG News until 145 for 20 News. So we have different characteristics that we are covering in our experiments. We use a word-to-vec model to obtain word representations as well. The architecture of the encoder part of the autoencoder is shown below, and the decoder is the mirrored version of the encoder. As you can see here, the encoder is simply fit for a neural network with 4 layers, with 4 consecutive layers. And we adopted this architecture from other approaches, such as that has been used in DCN, in IDC. We use the same autoencoder, and we perform no hyperparameter tuning on this autoencoder. And here we can see the results for automatic seed words. Above are the results in terms of accuracy. As you can see, 20 News AC, or the name of the data set plus the accuracy. And also we have the results in terms of ARI. And for the results in terms of accuracy in the top, we can see that on 20 News, on Yahoo, and on AG News, our SC2C approaches here can outperform STM and NN for sure. And on DBpedia, STM and SC2C rep E are on a par. And on Reuters, STM is able to outperform our approaches. The same trend can be observed for the ARR results as well, but with the difference that the results are more contrasted. Here in this slide on the top, we can see the results for manual seed words in the top, and we can see also the results for the automatic seed words that we saw actually in the previous slide in the bottom. As we can see for the manual seed words on 20 News Group, in terms of both accuracy and ARI, our approaches can outperform STM by large distance. And on Reuters, this time, ECIR2020 Rep C is able to outperform STM, while on automatic seed words, showing below, we can again outperform STM on 20 News Group, but on Reuters, STM was better. But now, on manual seed words, our approaches can outperform STM. So basically, our intuition about how to extract automatic seed words is confirmed, and our results can be validated then. Here we can see the influence of the number of seed words. We can see for each collection and for each approach, the behavior can be different. Sometimes, like 20 News and AG News and Yahoo, we can probably see a better trend. For instance, going from one seed word to the second seed word, we can see that we can have quite better results, while adding more seed words probably is not improving the results. After probably 3 seed words, the results become more stabilized. While for some other data sets like Reuters, we can see some sort of fluctuations in the results when seed words are being added. And here in this table, we can see the execution time per run in seconds for each model. And we can see that, so basically, in nearest neighbor, we don't have any trainings. So that's why this algorithm is really, really fast. But on STM, if we compare STM and ECIR2020 approaches, we can see that on 20 News, on Reuters, and on Yahoo, our approaches are quite faster than STM. On DBpedia, ECIR2020 Rep is faster than STM, but ECIR2020 Doc is slightly slower. And on AG News, STM is faster. But what we can conclude, we propose 2 different variants of ECIR2020, which can bias document clustering. Our proposed frameworks are able to outperform STM on the majority of collections. By using as few as 2 seed words, we can obtain significant performance gain. But we want to know better, we want to better understand when it is beneficial to bias document representations, ECIR2020 Doc, and when to bias the cluster representative ones, ECIR2020 Rep. Basically, we just want to know when to use ECIR2020 Doc and when to use ECIR2020 Rep. And for the future works, we want to investigate attention mechanism-based models, and also we want to combine ECIR2020 Doc and ECIR2020 Rep models to see the influence of them. Thank you for your attention.
Thank you, Maza. So now we will proceed to the question. We have about 5 minutes. You're just on time. That's perfect. So please use the Q&A button or raise your hand if you want to talk and to ask a question to the speaker. Okay, so while people are warming up, I was wondering, because the autoencoder has a strong impact on the clusterization you will make afterwards. I mean, if we think at the limit of an identity autoencoder, it will cluster on the word-to-vec representation. So did you try to modify a bit the autoencoder part to see if it had an impact on the performance? Is it that important, or?
Actually, so basically I tried a few things on the autoencoder to see, basically just for our preliminary results, to see if the autoencoder has an impact or not. And yes, actually it does, but we didn't want to tune actually everything. We just wanted to come up with some general architecture. And moreover, I use also a CNN autoencoder that can capture the relation between between consecutive words. But the CNN autoencoder did not perform well. But in terms of feed-forward neural network autoencoder that we use, yes, the architecture actually has a great impact indeed.
Okay. And do you know why the CNN didn't work? Do you have an insight on this?
No, to be honest, I tried I tried the CNN with different layers. So I think that I tried with 3 to 5 layers. I tried to work on that, but unfortunately, it didn't work.
Okay, thanks. Deepak has a question. Could the host unmute him? Okay, Deepak.
Yeah, so I had a quick question. So you had the clusters of labeled words, the seed words, and the clusters that are formed in the document space, right? When the autoencoder, based on the autoencoder representations. Does your loss depend on identifying a one-to-one correspondence between those clusters of seed words and the clusters in the autoencoder representation space, or is it?
Okay, let me go back to this figure. So to better understand your question, you mean if there shall be a one-to-one correspondence between these seed words, these average ones, and these cluster representatives?
Exactly, yeah.
So actually, no, indeed. So this is really nice question indeed. So first I have to mention that we did the pre-training in our autoencoder. And basically when you do the pre-training in normal deep clustering algorithms, you pre-train an autoencoder and you just save the weights and the biases, everything. And then you apply k-means and you use the obtained cluster centers obtained from k-means to also initialize your cluster representatives. But here we didn't use k-means cluster centers. We used actually the seed words representations for initializing. So in this case, we noticed that there is no one-to-one match, and we don't need to really take care of that.
Okay, yeah, thank you very much.
You're welcome.
Okay, so we have a question from an anonymous attendee. The question is, can your method still be considered as clustering, which is unsupervised, since your seed set is something like ground truth?
So actually, this is, so basically this is clustering, but this is like clustering with just additional information. I noticed that in some baselines, in some papers, they call it a semi-supervised approach, but in some others, they still think that this is fully unsupervised. And basically, in my opinion, this is still fully unsupervised. And these seed words, we just think that, okay, a user or an expert can come up with some ideas and just tell you, okay, I want to be clustered based on these seed words. So we don't consider that much these seed words as the true labels or something that can really be considered as supervised or semi-supervised, I guess.
Okay. Is there any other question? Otherwise, I have still others. Actually, I was wondering if the projection step you're making is wise or not in the S2 doc method. Basically, did you think of other ways to constrain the clustering, well, the document to be close to seed words? And did you consider that maybe seed words were just a start and you had to kind of enrich their representation to add other related seed words to them, so the projection is not so rough if there are not so many seed words?
Excuse me, from the projection, you mean masking the documents?
It's the MS function that you apply.
Okay, then may I ask to repeat your question probably quickly, please, because I was thinking that you think you're talking about the masked documents.
Yeah, it's well, I saw it in the paper. It was I think it's MS. I'm not sure anymore, but it's a function that from the seed words and a document try to project it on the, well, kind of the hyperplane of the seed words.
So basically, so first for the mask version, we tried two different things. We tried actually an approach which was based on we just computed the TFs of the seed words occurring in one cluster, and we actually in one document actually we masked based on that, and we also masked. There was another formulation which was based on cosine similarity. So probably there are also other ways to mask the document and to project it, but we only discovered these two.
Okay, yeah, I was just wondering. Okay, well, thank Maza for your talk. and the discussion, and then we will proceed to the next speaker. If she had problems connecting, so I'm not sure she's over there. Ninja, are you here?
Hello. The second speaker, she's network is not very good now.
Okay, so
she will contact me and she can apply for a report at the end.
Okay, maybe at the end. So maybe we can switch to ReadNet. No,
Okay.
because we keep the schedule for the next slides, next talks, and then we will. If Ninja is able to reach us before the end, we will schedule her at the end.
Okay, so shall I present next?
Yes, please.
Okay, thank you.
So I remind the participants that you can use Q&A at any time during the talk, so we can schedule the question at the end. Okay?
Okay.
So Chen Meng will present the ReadNet architecture now.
Okay. Wait a minute. Okay. Good morning, everyone. Really sorry that on my Google Calendar it said my talk is yesterday A4 instead. Yesterday's A3 instead of today's A4. So welcome to my talk. It's a pity that we could not see each other in person, but hope everyone is doing well. My talk is on ReadNet, a hierarchical transformer framework for web article readability analysis. My name is Changping Meng. Sorry. I studied at Purdue University and currently working at Google. This is an intern project at Google with Mao Jie collaborated with Mu Hao from UCLA. Different articles on the same topic may have diverse readability. For instance, taking the definition of rainbow as an example, it can be a precise and a rigid scientific definition with difficult word and complicated sentence structure. Or it can be a generic description with easy words and simple sentence structure. The first one is suitable for scientific writing, and the second one is a good common sense reading for the general audience. Evaluating readability can benefit a variety of applications. First, it can be used in information retrieval. Like you can recommend a search engine can recommend appropriate articles based on user and understanding ability or search history. For instance, when a user search photography on search engine, it can recommend intuitive articles for the Rockies, or they can provide professional articles for the veterans. For the education purpose, it can recommend articles based on the children's understanding levels. Here comes our task. Input is given a text. Our target is to predict the label to indicate the readability of this article. The labels can be a binary label based on the English Wikipedia or the simple English Wikipedia, or the mapping to the level of Cambridge English assessment. Since we adopt the ordinal regression in our project and in our task, the labels can also indicate the difficulties. The higher labels indicate the difficulty is harder. There are plenty of existing works related with readability analysis. The first part is from the field of computational linguistics. They design explicit features by the domain expert, like the cohesion matrix, the FK index, and also there are general NLP, general neural network models for the general NLP task. These models can also be applied in readability classifications, like the hierarchical LSTM with attention, the transformer, and the newest bird. But there's no specific model designed for readability analysis, which combines explicit features and deep neural network. There exists a lot of explicit features designed by the domain expert. Here we roughly divide them into two categories. You don't need to know the details, and if you want to check the detail of each explicit feature, you can refer to the paper. We divide them into two categories. The first one is sentence level features, and we will compute it for each sentence. And the second part is the document level features. We will compute it for the entire document. And here is an overview of our proposed model. It's a hierarchical transformer for readability analysis. The hierarchical transformer structure will encode both the semantic of text and the explicit features. From the word to sentence, it uses a sentence level transformer encoder and combined with the sentence level features. From the sentence to the document level, it uses a document level transformer encoder and combined with the document level features. And these sentence level and document level features are just presented in the previous table. It also contains a transfer layer. It will handle the transfer learning when the training data is not enough. Let's dive into the details of the major components. The first is we use a self attention layer from the transformer paper to encode the semantic informations. The else layer will encode the matrix HL into the HL+1, where the initial is 0 is the embedding matrix from the raw text. And each layer contains a multi-head attention function and the feed-forward function. After the P layers of self-attention, we got a matrix of capital HP, and we need to encode it into a vector H through the attentions. And this attention will be got into the vector H. After you set the embedding vector for the sentence, it will combine with those explicit sentence level features, H star, and for all the sentence from the first sentence to the end sentence will be concatenated and passed to the document level encoders. The next part is the transfer layer. The transfer layer is used to perform the transfer learning when there's not enough training data and the transfer learning is required. We can use the large data to pre-train the model, and when apply a specific task, we can fix the weight except the transfer layer and only use the small data to retrain the task layer. The learning objective is the ordinal regression, where the R is the embedding vector for the doc and the theta are the parameters will be automatically learned. Why we use a hierarchical self-attention? First, we choose self-attention instead of LSTM because the self-attention can better model the long-range dependence than the sequential model such as LSTM. The hierarchical structure instead of a single layer, it benefits in two ways. First, it mimics human reading behaviors because human understand from the words to sentence and then from sentence to document. The second, it will reduce model's complexity. Here comes to the dataset we used. The first is Wikipedia. It contains 50,000 pairs of simple English Wikipedia and the corresponding English Wikipedia. The next is the Cambridge English exam. It contains hundreds of documents in different levels. The next is the VBeat. It contains 7,000 articles from the Weekly Reader magazine and BBC Bedside. This table says the statistic of the number of sentences and the average number of words in each sentence for the datasets. In this experiment, we compare with 3 categories of models. The first is a model with only use explicit features, like the logistic regression, support vector machines, and the multi-layer perceptrons. The second category is the neural document classifier. We use the convolutional neural network, hierarchical LSTM, and the hierarchical attention neural network. The third part is combines the explicit features and deep neural network models. We compare with these baselines based on the classification accuracies on the 3 datasets. The explicit features have satisfying results since those explicit features are reliable. As we see from the data statistic when we introduce the dataset, the number of words per sentence and the number of sentences varies in different difficulties. It can be used to evaluate the difficulty of the documents. The next part is neural document classifiers, especially the hierarchical LSTM and the hierarchical attention performs well since they can also know the infos based on the 0 paddings of the sentences. Combining these 2 can further increase readabilities. And we can conclude that both explicit features and the deep neural network models are helpful, and combining those 2 can further increase the accuracies. And comparing the hierarchical attention and hierarchical self-attention, our proposed model ReadNet, it can see that also the transformer model works better than the LSTM because it has a shorter interaction path length, which can model the longer range dependence. In the previous tables, we have significant better result on Wikipedia and the VB dataset because it has at least thousands of training examples, while on the Cambridge English, the advantage is not that significant because there's only hundreds of training examples. It's not enough to train a large model. So in this case, we can use the transfer layer, and we use the VBeat or the Wikipedia to pre-train the models, and then use the Cambridge English exam data. It only contains hundreds of examples to retrain the transfer layer. From this table, we can see that using the VBeat and Wikipedia to retrain the models can increase accuracies compared without the transfer layer. The conclusions is we propose a hierarchical model designed for readability analysis, which combines the explicit features and the deep neural network. In the future, we will evaluate the importance of features since we propose a lot of them, and we want to quantitatively evaluate the importance of each one. And we will also better explore the general pre-trained models such as BERT, because this project is done before the popularity of the BERT, so we haven't got the chance to evaluate it yet. Here are the references, and thank you so much.
Thank you, Shangping. So we will now start the question session. Well, we have a couple of them. Could you first unmute Ting Su from the University of Glasgow? Wanted to ask a question.
Okay.
It's a host. No, the host will do it. Don't.
You mean the what embedding does the model use? This answer?
Okay, Tingsu, yeah.
Oh,
Hi.
Go ahead.
Hi, I have two questions and they're sequential. So firstly, maybe I missed it, but how did you initialize the words representation? Did you use word2vec or did you use a pre-trained or did you just train it?
We use a pre-trained. Yeah, we use a pre-trained word2vec embedding.
Word2vec. Okay, and can you please go back to the slides where you have this architecture of your RedNet? Yeah, here, it's fine. So you said that there is explicit word information, for example, how difficult it is according to Wikipedia or Cambridge University or something, but you have only a sentence feature combined when you, after you aggregating the word features. I'm wondering if you have this, do you combine this difficulty of words with the pre-trained word embedding, or how did you get this sentence feature from the word level?
Okay. For the sentence, for the word embeddings, we only use a word2vec, which contains only the semantic information without the difficulties of the word. And but in the sentence level, we combines with those sentence explicit features, and which is UI. And when we do the document level encoders, which hardcode version, and when we do the document ones, there's also the document level features, and we will also concatenate it with the semantic embeddings.
So you mean that the sentence feature and the document feature contains information about how difficult the words are inside, but you don't put this word level information into the word embedding?
Yeah.
Okay.
Yes.
Okay, thank you.
In fact, previously we have tried. We have proposed like the method like based on the frequency of the word and integrate that into the word embeddings, and it helps to let the word2vec with frequency information can partially like help you determine the difficulty of the word, and also combines semantic informations.
Okay, because in my opinion, like as far as I can remember, the BERT has 3 levels of information, right? The word embedding, like the word embedding quotation mark, and the mask information, and if it's belong to the first sentence or the second sentence. I was just wondering that if you can put this word difficulty into this similar way so that you can combine it on the word level. But okay, thank you very much.
Thank you, Tingsu. We have 2 questions from the Q&A. So the first one will be quick. Is your code available for reproducibility and implementation?
The source code, you mean?
Yes. Yeah, I guess so. Yes.
It's for the code, it's a little hard because it's a intern project, but we can provide using the open library or model that use open libraries instead of the libraries we use inside Google.
Okay, and the second question from Nirmal Roy. What do you think about the time efficiency of the proposed model? Can it be implemented in a real-time search engine?
We haven't tried. We haven't. The efficiency is fine as long as you have enough computation powers. In fact, you don't need to do a real-time search engine because all the query result, like the text, when you store it in your libraries, when you for instance, when you save the page rank scores, you can at that time you can do an offline computation of the readability or the difficulty of the word of that web article, and then store it. You don't need to do a real-time computation.
Okay, just one more.
Web.
Yeah, that's true. Just one more question. Did you make, maybe I skipped it, but did you try to remove the sentence and document features, do appellation studies to see what was the impact?
Yes, in fact, we have tried that, and it's like kind of 1 or 2% worse than the current this model.
Okay, but still better than the competitive approaches.
Yeah. Yes.
Okay, so 2% is not that much. Okay, yeah, I guess well, Bilal will ask you via Slack or directly, because we have to switch to the last talk,
okay.
To the next talk. Sorry. Yeah. Well, thanks for your talk, Changping.
Okay, thank you so much for arranging this.
Yeah, that's you're welcome. Okay, so we'll switch to the next talk. The presenter will be Clément Rebuffel, and the talk will be about a hierarchical model for data to text generation.
Hi.
Hello.
Can you see my screen?
Yes.
Yes? Okay, great. Okay, so hi everybody, I'm Clément and I'm here to talk about a hierarchical model for data to text generation. This work was done with Laure Soulier, Geoffrey Scouzeten and Patrick Gallinari from the MLIA team based in Paris. The agenda for today, we are first going to present the task with some examples, then review the current state of the art. Following this, I will present our hierarchical model and the evaluation protocols, and we'll conclude with some interesting perspectives about future work. The data to text tasks comes from 3 facts. The first one is that knowledge today is often modeled in a structured way, such as in indexes, tables, key value pairs, or such, and that this data, by their nature, is not easily usable by humans and really need to be synthesized. Third, there have been some studies that have shown that communicating via text is more efficient than communicating via raw data. Consider the following fake Wikipedia table. If we want to generate an adequate description of this table, we first want to select the relevant information. Then we want to order this information. And finally, we want to realize the sentence. There are many more tasks involved, such as maybe sentence aggregation, where we say several facts inside the same sentence, or data interpretation, where, for instance, we say ECIR instead of European Conference for Information Retrieval. In the real life, data can be very complex, such as in the financial sector, where an instance of a data set is composed by many tables, and each table describes several objects of different types with different properties. More fun, perhaps, in the sports journalism field, we have statistical games, statistical tables describing the games, and a journalistic description of the games. Maybe we want to take the place of the journalist. Formally, an instance of a data-to-text dataset is comprised of a table T and a reference text R, which is an adequate description of the table. The table is a collection of records which are entity key-value triplets. And if we group these triplets by the entity property, we obtain a group of entities where each entity is itself a group of key-value pairs. For instance, in the figure below, each entity is a line in the table. The key attributes are the column names, and the value attributes are the cell value. A record from the table can be outlined in red, where Pascal Siakam played 46 minutes inside this game. A neural network for data to text should involve 2 steps. The first one is to encode the source table, and the second one is to generate or decode the description. This is why models are based on the encoder-decoder architecture from neural machine translation. This figure here presents the classical architecture you can find in most translation and summarization papers. First, the source text is encoded, where all words have a representation in red, and then the description is decoded 1 word at a time in yellow. To generate the next word, The decoder uses its hidden state and a context vector to compute a distribution over the vocabulary. The context vector is given by the attention mechanism, and it's simply a weighted sum of all the inputs representation. This architecture can be augmented with the copy mechanism if we take into account that the attention weights can be viewed as a distribution over the inputs. Now, the decoder can choose to draw the next word either from the vocabulary distribution or from the attention distribution, effectively doing a copy from a word in the input. This architecture can be very easily adapted to table inputs when we linearize the sequence, linearize the table, sorry, as a sequence. If we look at the figure from the previous slide, the source text now becomes the linearized table. Please note that when we use a text, we use 1 embeddings per word, and now we have 3 embeddings, 1 for the entity attribute, 1 for the key attribute, and 1 for the value attribute. Data text models can be grouped in 2 categories. The first one is the papers focused on the encoding process, such as this one from Liut et al., who proposed the modified LSTM with an added gate, which is able to attend to the key attributes as well as the value attributes, and a dual attention to communicate with the decoder, where the attention weights are computed both on the value and the key attributes. On the other side of things, there are the decoder's papers, such as the papers on content planning, where the decoders act in 2 steps, separating the sequence of mentions from the table from the fluency of the text. For example, Pudupuli et al. Proposed a model who first generates an ordered sequence of records, which he calls the plan, and then encodes this plan to generate the final text based solely on the plan. These approaches have several limits, and we can outline the 3 major ones. The first limit is that linearizing the data structures leads to losing the explicit limitations between entities. The second and third limits comes from the use of recurrent networks in the encoding process, because first, recurrent networks have been shown to struggle with large inputs, and as we have seen before, data-to-text instances can be very large indeed, with several hundred of cells. And second, recurrent networks need their input to be fed sequentially, and this assumes an order on the collection. And it has been shown that where no natural order exists in a collection, assuming an arbitrary order can significantly impact the learning performances. To deal with the first issue, the linearizing of the data structure, there have been a first attempt from Pudupuli et al. Called entity modeling. They focus on the decoding process, and their decoder acts in 2 steps. They first generate a word and then re-encode part of the table. The way they re-encode part of the table is that they choose a subset of entities and then recomputes the encoding of all records belonging to these entities. This yields better results, but results in a more complex and very costly decoder, because now the encoding process has to be done each time a new word is decoded, which can be up to several hundred times. To deal with this, we introduced the hierarchical model for data-to-text generation. Here we focus on the encoding process. This means that we use a simple decoder, as in most previous work, which is simply an LSTM, to ensure fair comparison of all systems. To explicitly model the structure in the encoder, we rely on 2 facts. First, instead of linearizing the table and losing explicit limitation between entities, we propose a hierarchical encoder. Each entities will be encoded separately from one another, and the collection of entities will be encoded as a whole in the second step. Then, the second contribution of this paper is that instead of using LSTM and arbitrarily ordering the rows and columns of the tables that should stay unordered, we use the transformer architecture that has been known to deal with unordered sets. Our encoding process is in 2 steps. First, we encode each entity independently from each other. Recall that the entities are a collection of records, which are simply key-value pairs. The records are represented by a key embedding and a value embedding, which are fused for a record embedding. Then we use a transformer, and especially the self-attention inside the transformer, to encode all these records. We also, like in most BERT-like papers, we use a class token. We use an end token, which will be used as a global intermediary representation for the entity. To encode the collection of entities, we extract the representation of all the end tokens and use a second transformer encoder, the high-level encoder, to represent this group of tokens. To communicate with the decoder, we adapt the standard attention mechanism to a hierarchical attention mechanism. This should mimic the way human annotators write. First, we select an entity. So we compute a set of alpha scores, which is a distribution over the entities. And then inside the entity, we select a record. This is done by computing a second set of beta scores on the records. We experiment with two variants. The second variant is based on the fact that when people write a sentence, for example, James Harden has scored 24 points, once the entity is chosen, the fact becomes irrelevant. Now that I know that I'm going to talk about James, I will mention his first name and his last name, whatever they may be. Our first case, the hierarchical KV, computes the beta scores after the low-level encoder. But our second case doesn't take into account the value. The beta scores are computed immediately after the key embeddings before any value has done any impact. We evaluate our approach on the RotoWire dataset, which are basketball game statistical tables paired with journalistic description of those games. We have chosen this dataset because it is the largest to date, with tables that are up to 600 cells. Before, any dataset in data-to-text had only 10 or 15 cells inside the tables. So this represents a challenge with 28 entities and such. We evaluate the approach on 4 automated metrics. The first one is the well-known BLEU, which computes the precision of n-grams from the generated description compared to the gold reference. And 3 next metrics are based on information retrieval model from Wiseman et al., where we first tag all sentences to extract the records, the mentions inside the sentence from the table, and then compute the relation generation matrix, which is how many records from the table, their precision and number, the content selection matrix, which measures how many facts from the gold description are found in the system description, and the content ordering matrix, which measures how well the system has ordered the records using the Levenstein distance between sequence of records in the description from the human annotators and from the system descriptions. We compare our model to 5 baselines. The first one is Wiseman et al. Is the standard encoder-decoder with attention and copy. However, their encoder is an LSTM, so we also compare with the same architecture, but using a transformer instead of the LSTM. And finally, we compare with the 2 content planning approach presented in the related work, as well as the entity modeling approach also presented in the related work. Please note first that the information extraction module from Wiseman et al. Fails on 4% of the time on true descriptions. So there is a margin of error to this matrix, and the 100% is not possible on this column. And also note that the human annotators mention on average 17 records from the table among the 600 possible. So an adequate system should not aim for as many mentions as possible, but should stay more or less at 17 mentions. First, if we compare the flat architecture with the hierarchical architecture, we can see that the lower results obtained by the flat scenario compared to the other hierarchical scenarios suggest the effectiveness of encoding the data structure using a hierarchy, which is expected, as losing the explicit delimitation between entities makes it harder for the encoder to encode the semantics of the object and for the attention mechanism to extract silent records. If we compare KV, where the attention scores, the beta attention scores are computed after the low-level encoder, with K, where the attention scores, the beta attention scores are compared directly on the key embeddings, we see that the K variant works better, showing that omitting entirely the information of the record value in the attention mechanism is more effective because this variant performs better. And this means that structure is more important than the value. If we compare our approach to the two-steps approach, the planning approach presented before, we see that our hierarchical model outperforms these two-steps models, showing that capturing structure in the encoding process is more effective than predicting structure in the decoding process. Furthermore, we can note that PDPLI plan reaches 34 mentions on average, showing that incorporating modules dedicated to entity extraction leads to over-focusing on the entities, where our model is more balanced and generates more balanced description. If we compare with PDPLI update, the comparison shows that dynamically updating the encoding across the generation process leads to better content ordering scores and better precision. This may be due to the fact that updating the representation after each mention allows the model to keep track of mention history, which guides the ordering of mentions and narrows at each step the possibilities of the next mention. This yields, in practice, better precision. In contrast, our model encodes better the silency and the semantics of the object, leading to better content selection. Note that they also tend to mention too many records, with the 30 on average. Here, in this figure, we illustrate the difference between hierarchical K and hierarchical KV weights, the beta weights and the alpha weights in the attention mechanisms when the models are trying to decode the words circled in red. We see that hierarchical KV is uncertain and ends up with the wrong records, where hierarchical K, whose weights are only computed on the key and not the value, are very sparse and choose the right records at the end. In conclusion, in this work, we have proposed the hierarchical encoder for data to text, which leverages the structure for efficient representation of its input and has strong synergy with the decoder via the attention process. We also evaluate our approach on RotoWire, showing that our model outperforms most models on all metrics except the entity modeling ones. And in the future, this way of representing structured data may lead to automatic inference, maybe because we can implement operators which are able to compare rows and columns using the structure inside the encoder. Or maybe we can constrain the generation by fixing some attention weights, maybe to the same entity during a sentence to avoid coherence problems or such. Thank you.
Yep. Thank you, Clément. So same as for the other talks, you can use Q&A or raise your hand if you want to ask a question. Okay, so waiting for the first question to come up. Just a small question. How do you deal, because there are many tables, so how do you deal with numbers? I know it's a complex problem with neural representation, so how do you do this?
Yeah, it's a very interesting question. It's a very part of the future work. We do not deal with numbers yet. This is certainly why omitting the value during the attention mechanism works better. It's because numbers tends to be very complicated. So for now, they are dealt with like normal words. So each number has a semantic, which is not really great. So for example, every number above 100 are considered like a team score, because no player scores 100 points, but a team can add up to 100. So if we maybe say that the player has scored 100 points, the network will be lost because the semantics of the numbers are not really well encoded.
Okay. We have a question from Jae Chin Jun. So the question is, you used LSTM in the decoder part. Why didn't you use other decoder model like transformer and decoder?
Yes, this is to ensure fair comparison with all other systems that use an LSTM, we want to show that the encoding process is really important and that the decoding process comes next. So we didn't want to introduce variability in the decoder during comparison with other systems.
Yeah, as a follow-up, did you, well, in the paper you didn't, but did you try to do so afterwards, just to see if there was another improvement with transformer decoder?
Not for now. We haven't done it yet.
Okay. I was also wondering what was the link with the, I mean, there should be a link with the summarization architecture that are used, because they are more related to the task than translation models that you took as an example. So I wondered if you try to look at those works.
Actually, we are really inspired by summarization methods. In fact, the figures presented inside this presentation were taken from a summarization paper. You can see at the bottom of the slide. Yes, we draw inspiration from all generation fields, and summarization is one of them. Does this answer?
Yeah, no, yeah, it does a bit, yeah, but it was because they have the notion of coverage of the content and things like this that could be interesting to import in that kind of models. So do we have another question? No.
If we have some time, I can answer a bit more about coverage.
Well, we're just on time, so maybe
Okay.
chatting about this will be fine, unless there is a very quick question. Okay, well, thank you, Clément, for talking the discussion, and we will proceed to the next talk, which is a multi-component system for automatic Arabic diacritization. And the presenter, I don't know if the presenter is here, because I didn't see him or her. Is the presenter of this paper here?
The panel.
Hello? Yeah. So did you reach her or him?
Not sure. So can the author? It's here. I think it's mine. So your.
Oh yeah. Okay.
Your
so
user.
Hamza, can you upgrade him as a panelist?
Can you raise your hand? Okay. So Ning asked Ning Chang to play her presentation as a video.
Yeah, I know. So it would be after her talk. Yeah. Hello.
Hello.
Hamza?
Can you hear me?
Yes. Okay. Yeah, we can hear you.
I have prepared this presentation as a video, so I will launch it now. If there is any problem, I can switch again to present myself.
Okay, that's fine. Thanks.
You need to share your computer sound, otherwise we will not hear you.
Okay.
There's an option there. That's the problem with playing the videos, with playing the presentation with video. Can you start playing and then share the screen?
Okay, I will find it.
So when you press share screen, you have an option which is share computer sound. That needs to be on.
In the more options probably. But share first the video.
Yeah, I am trying, but the video didn't show up in the menu. So.
Need to press share screen on Zoom.
So I should, okay, I will try. So this is my screen, but.
And did you activate the, okay, now in the more, you need to share computer screen.
So can you see the,
yes,
the video or not? Can you see it paused?
We can.
Okay, so I will launch it and see if the sound works or not. Presentation is about my paper, Multi-Component System for Automatic Arabic Diacriticization. First, we will start.
Yeah, it's working. It's working.
Okay.
You can start.
With the background about the Arabic language. It's the most widespread Semitic language in the present. It's used by 442 million people, and it's the native language for most people in the North Africa and the Arabian Peninsula. And it consists of 28 or 29 letters because there is a disagreement about one letter. So most of them having multiple shapes depending on their position in the word. But on the computer, it's represented by 36 characters because there are two characters which have more than one form. One of them has two forms and the other one has the rest of them. So until you reach 36. Has no uppercase letters and it's always written in cursive style from right to left. The writing matches the pronunciation of the word in almost all cases. Talking about the consonants and vowels, there are two types of vowels in Arabic. We have long vowels and short vowels. So 3 letters can act as long vowels. So are those 3 letters, alif, waw, ya. And the rest of them are considered consonants. So the rest of Arabic letters, except so this one, and this one are consonants. So short vowels are not letters. They are represented as diacritics above or below the letters. So those diacritics are some marks that are put above or below the letters. And the consonants and long vowels, so all what you see here, are always written, but the short vowels are often omitted. The diacritics are 8 phonetic marks that appear above or below the letters. They are presented on computer encoding systems as additional characters, especially UTF-8. So 7 of them are primary diacritics that can be used independently. Fatha, Kasra, Dhamma, Sukun, Tanween, Fath, Tanween, Kasr, Tanween, Dhamm. And one of them is a secondary diacritic that can't be used alone. It's Shadda, and it should be used with one of those. Fatha, Kasra, Dhamma, Tanween, Fath, Tanween, Kasr, Tanween, Dhamm. So all of them except Sukun. So no diacritic is also an option in fully diacritized text. So we have a total of 14 possible diacritization because we have 6 here and 6 with this one becomes 12, and this one 13, and with no diacritic becomes 14. Diacritics are important because they define many linguistic features such as part of speech, active passive voice, and the grammatical case. And they define the right sound for the letter from the different possible sounds. And also because the meaning of the Arabic word is dependent on them. As you can see here in the table, we see that the variation, the diacritization of the single and diacritized word changed the meaning significantly. Now we will talk about the problem of the automatic diacritization and the ideas proposed to overcome this problem. So the available Arabic text today uses an undiacritized text due to various reasons, such as typing speed, condensation of the text on the looking files and the file size. And diacritized text can be read and understood by most of the time correctly by native speakers, but they can't be understood like that by beginner learners and NLP tools. So the problem is it possible to restore the diacritics of the undiacritized text without any additional information except the text itself? The native speakers can easily read the text without diacritics. We think that the automatic diacritization should be possible. That the native speakers can infer the correct diacritics from their previous knowledge and the context of every word. So we should make a model that can guess the correct diacritics for every letter. So this model can be based on rules, statistics, deep learning, or multiple methods from those. So we will talk about the types of approaches that exist in the literature. The first type is the rule-based approach, which consists of writing a set of rules operating on a dictionary and handcrafted features. The features range from simple letter-based to complete analysis-based ones. They are useful when having limited data or memory, but they are extremely time-consuming to implement when the rules are complex, and most of the time are complex. So an example is, for example, if the current letter is ta marbuta, the diacritic of the previous letter must be fatha. Second type of approaches are statistical approaches, which are based on building probabilistic models, then tuning them on training corpus. They are mostly language independent, so it eliminates the requirement of a strong background about the language. They are easy to implement and train without needing a huge computational power. Examples of this approach are Engram's model, Hayden-Markov models, and weighted final state transducers, and classical machine learning models such as maximum entropy classifier and SV. The next type are deep learning approaches, which relies on building neural networks. The type of neural networks used include fully connected bidirectional LSTMs and GRU. No deep knowledge of the language is needed as well, and often achieve state-of-the-art performances. They require a lot of data and considerable computational power, in addition to their long training time. Now we present the details of our approach. A proposed approach is a method combining different types of approaches in order to benefit from the advantages of the different ones. So it includes three parts: deep learning model, correction rules, and statistical corrections. The DL model generates the initial prediction for the input, then its output is forwarded to the correction rules and the statistical corrections to improve this prediction. So in total, this problem is formulated as a sequence labeling task, where every element of the sequence, which is a letter an Arabic letter in our case, should have a corresponding label, which is a diacritic. The dataset is a text file having one diacritized sentence of space-separated words per line. The sentences are extracted from the Teshkila dataset after the pre-processing, because the original dataset is not well pre-processed. So the pre-processing includes segmenting the text according to the new lines and some punctuation marks in order to form independent sentences, as well as removing useless entities such as undiacritized Arabic text and punctuation. In addition to that, the numbers are replaced by 0, since their values don't affect the diacritization of the surrounding words. And the sentences with less than 2 words are excluded, because we don't need sentences with just 1 word. For the input and output conversion, the letters are separated from diacritics to make the letters as inputs and the diacritics as outputs. The sequence of letter is transformed first to 1D vector of indexes, then it's transformed to 2D array using one-hot encoding. Then it's transformed into 3D using a sliding window of 1 to give a result like this. Then the sequence of diacritics is separated into 2 sequences, and using this, 2 vectors are transformed. One for the secondary diacritics, which is a binary vector, and another one for the primary diacritic, for the primary diacritics, which is transformed then into 2D array to form using the one-hot encoding. Next, talking about the deep learning model. It's made of 2 bidirectional long short-term memory layers with 64 cells in each direction, as you can see here. So it makes it 128 cells per layer, and the time steps dimension is 10, as we said in the previous slide. The output of these layers is flattened because it's 2-dimension if we exclude the batch dimension. It's flattened, then forwarded into 2 dense layers, because the dense layer accepts only 1 dimension if we exclude the batch dimension. Those 2 dense layers are of size 8 and 64 respectively. Then it's forwarded into another 2 dense layers in parallel, which represent the output layers, this one and this one. So the activation of non-output layers is the hyperbolic tangent, and the activation for the output layers, for this one it's sigmoid, and for this one is softmax, because this one is a binary classification layer, so it only outputs 0 or 1. It should output 0 or 1. Because there we have only one diacritic here, one secondary diacritic. So it's either exist or not exist. And for this one, we have 8 classes, we have 8 primary diacritics. So we need a softmax to convert this into a probability distribution. Second part of our system is the rule-based corrections. They operate on the output of the deep learning models. They operate on character level, just like the deep learning model. They modify the probability arrays of the output to eliminate the obviously wrong diacritics for the current character. Sometimes we can eliminate all the wrong diacritics, and sometimes we can eliminate just some of them. Some rules work on single characters, and others takes also the context. It means the previous and the next characters into account. This schema represents the operation. It takes the input, the output, the first output, which means the secondary diacritic output, and the output number 2, which means the primary diacritics output. They merge them together, and there are some rules to correct the secondary diacritics, and some other rules that operates on the primary diacritics. And then we have 2 corrected outputs. So this one becomes this one, and this one becomes this one. Part of our system is the statistical corrections, which are composed from 4 stages. But before beginning those stages, we have to merge the output and the input to make a diacritized text. Then this text is tokenized into space-separated words, because their statistical corrections work on word level. And then for every word, its diacritization is replaced with the most likely correction in one of the 4 stages. First, the trigram corrections, which replace the diacritization of the current word using the highest frequency, diacritization that has the highest frequency according to the surrounding word. For example, if you look at this example, this word is the diacritization of this word is fixed using by looking at these 2 words. Then we look from the training set which form has the highest frequency of operation frequency. So we took this to correct this. And then the bigram corrections, which use the same principle but using the previous word only. So we don't look at the next and the previous, but we use only the previous one. Now for the unigram corrections, the minimum edit distance is used by calculating the minimum edit distance between the candidate word, which we need to correct, with all the known forms from the training set. And for the one which has the smallest distance is chosen. In case of ties, we break the ties using the first one that we have in the list. So for the patterns correction, we apply the same principle, but instead of calculating the distance between the candidate word with the known words, we use here the pattern of this word with the patterns of the candidates. So the pattern is it's a simple idea. Well, in this work, it's a simple idea to just replace the consonant by a constant and leave the vowels as they are. So here in this word, we change this one and this one because they are consonant, and the middle letter is left as it because it's a vowel. And we do the same calculation as unigram correction. This graph is an overview on how the statistical corrections work. We just note that if the word is corrected at one stage, it's not forwarded to the next stage. Only the only the uncorrected words in a stage are forwarded to the next stage. For learning the parameters, we have two parts in our system that needs that. So we have the deep learning model, which requires many iterations to improve, and they are updated using the other data optimizer. And we have the statistical corrections, which just need one iteration to populate its content. Testing, two metrics are used, the diacritization error rate, and which represent the ratio of false diacritics, and word error rate, which represents the ratio of words with at least one error. Both of the metrics have two variants considering the last letter, so either we include it or we exclude it. The letters without diacritics should be included in general, but sometimes they are excluded as a workaround for the partially diacritized datasets, which is not the case with the Tashkila dataset. We see here from the results that our system achieves better results than the tested ones. Now, to conclude this work, we said that our system benefits from using multiple components to restore the diacritics of raw undiacritized text. This system has achieved fairly good results, but it's still slow and consumes significant memory space. So in the next work, we will focus on reducing the size of the system and relying more on the idea of the patterns that we have just started in this work to try to improve the efficiency of our system. So that's all for today, so thank you for your attention.
Okay.
So the presentation has finished now.
Yeah, we heard this. Okay, thanks Hamza for the video talk. If there are any questions, not yet. Well, we have time just for a couple of questions because it took time to set up. So I was wondering how were the rules generated in the second step of your model?
Actually, the rules were not generated because they are fixed. They are the only part of the system which is fixed. So the rules are written if we have this and this, then this. So it's just it's a fixed procedure.
So did you take the rules from somewhere, or did you write them yourself?
I have written them myself because I know some rules in Arabic. So there are some simple rules that we have to respect. So I have written them because if the model generates something that is that doesn't work with the rules, so it's certainly false because we have some rules to respect. So those rules are used to limit the number of errors that can be committed by.
So it could be a standard set of rules applied for any model, not only yours.
Yeah.
Just one more quick question. It seems that I know it's a very trendy thing, but the transformer architecture would be perfectly suited for that kind of task because it takes the context into account. So did you try to go towards this?
No, when I started this work, I didn't know about the transformer, but until now, I have. When I have finished it, I have just heard of them. So maybe in the next work I will work with them. So I am still learning about the transformer architecture and the BERT and XLNet and those variants.
Okay, well, it could be worth trying. Okay, no questions. So, well, given the time, we will switch to the next talk. Thanks, Hamza, again.
You are welcome.
Thank you.
So the next talk will be given by Ning Chang. And the title is a mixed semantic feature model for Chinese name entity recognition with character and words. So Ning Chang, are you here?
I'm here.
Okay. You can go ahead.
Okay. Hello, everyone. I'm Ning, and I'm a student from Chongqing University. Today, I will present some work on Chinese named entity recognition. Natural language processing is a subfield of linguistics, computer science, information engineering, and artificial intelligence concerned with the interactions between computers and human languages. In particular, how to program computers to process and analyze large amounts of natural language data. Natural language process has many subtasks, including machine translation, question answering systems, and so on. Named entity recognition is one of the key technologies and the basis of most downstream NLP tasks. Named entity recognition refers to the identification of entities with specific meaning in the text, usually including names of people, places, institutions, proper nouns, and so on. For example, in the following sentence, I have an apple, it tastes good. Our task is to identify and classify the entities in the sentence and recognize that the non-entity apple is a fruit, not Steve Jobs' Apple's products. For English text, this problem has been studied extremely. However, Chinese NER still faces challenges such as Chinese word segmentation, and it's often difficult to define what constitutes a word in Chinese because there's no gap between words in Chinese. At present, there are two major challenges in Chinese NER: entity boundary segmentation and out-of-vocabulary recognition. In order to segment words in Chinese sentences, some researchers have proposed NER models based on our word segmentation. That is, first, use the word segmentation tool to divide the sentence into a word-based sequence, and then use word segmentation as the basic unit for entity recognition. But this operation may cause error propagation. Errors in the word segmentation stage may adversely affect subsequent steps. For the problem of out-of-vocabulary recognition, the character-based model can solve the problem. The character-based model doesn't rely on dictionaries, and the labels are classified in units of characters. However, the disadvantage of this model is that the word boundary segmentation is not accurate. Let's look at the example in the slide. For example, there is an error in the word segmentation, dividing Beijing and the People's Park into people from Beijing and Min Park. This directly leads to the label misclassification of the words in the subsequent entity recognition. Therefore, we want to propose a model that can combine the features of characters and words to solve the problem of entity boundary segmentation and unregistered words. Many researchers have also considered this problem and proposed the corresponding models as shown in the figure. Well, before this, first, I would like to introduce the basic model in named entity recognition, bidirectional long short-term memory, and a conditional random field. Most of the current NER model is based on this structure. First, the characters or words are mapped to vectors, and the characters word embedding are fed into bidirectional long short-term memory neural network, training and combined with the forward and reverse information. And finally, use conditional random field with context labels for label prediction. The models in the slide are combined characters and words proposed by previous researchers. The model on the left uses convolutional neural networks to extract the character level information corresponding to each word, and then combines it with the word vector as a comprehensive representation. The model on the right adds an attention and calculates the weight between character information and word information in each word. In this paper, we utilize BioLSTM and CRF as our basic structure and extends a self-attention mechanism to obtain the long-distance dependencies of the character and word encoder sequence. As illustrated in slide, the architecture of our model mainly consists 3 parts. First, character and word embedding, and second, multi-granularity representation fusion based on self-attention, and last, CRF for tag prediction. Next, we will introduce these 3 parts in detail. For the sentence, Lily is at Beijing People's Park. The sequences in character units and word segmentation units are respectively fed into model as input. Sentence segmentation using Jieba segmentation tool, and then the character sequence and the word segmentation sequence are mapped into vectors. The word vector mapping uses data from Tencent AI Lab, and the word embedding is generated using random training. Character embedding sequence and word vector sequence are respectively represented as EC and EW. Second part, multi-granularity representation fusion based on self-attention. The character vector and the word vector in the previous step are sent to the bidirectional LSTM network layer for training, and the forward and reverse information in the sequence is captured to obtain the hidden state sequence, HC and HW. Join the 2 hidden sequences to form a total hidden state, HTurtle. In HTurtle, the front part is the character's representation, and the latter part is the word semantic feature. Then a self-attention mechanism operation is performed on the turtle hidden state sequence. When expressing each character, it will take into account the influence of the later word segmentation structure. For example, when performing entity prediction on the character Bei and Jing, the word segmentation Beijing in the second half of the turtle sequence will have a higher attention score, which can be used to obtain a weighted representation. And then through a feed-forward neural network, a new representation of the characters Bei and Jing can be obtained to help the characters predict the correct label. Traditional recurrent neural network will cause the problem of information loss with the increase of distance. The self-attention mechanism can break the distance limit and calculate the correlation between arbitrary positions. This model combines 2 granular hidden states at the sequence level to preserve the original features intact. Also, the self-attention trains the weight information of the turtle sequence and preserves the semantic information of the context characters to perform a calculation with the information of the word sequence structure. The character information will correct the error problem of word boundary segmentation. Moreover, this method captures the structural information of the word sequence in order to compute similarity and correlation with character context information to further identify the combined boundaries of the long phrases. We quote a standard conditional random field on top of the attention layer. The CRF can use the state feature function and the state transfer function to maximize the characteristics of the text. Besides, it can consider the context information and the annotation information of adjacent words. After analyzing the experimental results, the recognition effect based on characters is significantly better than the labeled results of word segmentation. So our model would use the character-based output in the subsequent experiments. It can be seen from the model that we discard the output result based on word segmentation. Now we compare the model from another angle. From the figure, we can see that our model combines two granularity features at the sequence level and uses the self-attention mechanism to calculate the dependency between any character and any word segmentation in the input sentence. The left model may lose some features during the fusion of each word and character, but the model we proposed could keep the complete information of each character and word segmentation and train the weight matrix with self-attention. We use dataset provided by Microsoft Research Asia and the Weibo corpus extracted from Xinlang Weibo to experiment with the model. MSRA contains 3 entity types: person, location, and organization. And the Weibo dataset is annotated with 4 types of entities. The detailed statistics of the corpora are summarized in slide. We pre-process the datasets and annotate the entity type with BIO rows, which indicates begin, inside, and outside of a named entity. Ablation experiments are designed to verify the necessary of each part in our model and its impact on the experimental results. We gradually add each component to the baseline architecture bi-directional long short-term memory and conditional random field. And we compare our bi-long short-term memory and self-attention and CLEF model based on a mixture of characters and words with the previous proposed advanced models on the MSRA and Weibo datasets. From the experimental results, we can see that our model has improved on both datasets compared with previous models. Because MSRA data is standard, and previous studies have achieved valid results on this dataset. Well, Weibo NER data comes from a social platform. There are many unregistered words. Therefore, the overall experimental accuracy of the Weibo dataset is lower than MSRA. More experimental details can refer to my paper. And this is the reference cited in the table on the previous page. Summary, the model we proposed combines self-attention mechanism into bio-long short-term memory and the conditional random field neural network for Chinese named entity recognition to capture multi-granularity information and combines the semantic and structural features of characters and words to predict entity tags. We solve the problems of word boundary segmentation and long phrase combination, and the experimental results show that our method has improved the accuracy of Chinese named entity recognition. Well, that's all. Thank you.
Okay, thank you, Nick Chen. Before we start with the questions, I remind all the participants that we have a last talk that was the second scheduled one that we postponed because of speaker connection issues. Okay, so please raise hands or ask a question on the QA if you have any. Well, to start with, I was wondering, is there anything learned at the CRF level, and what is the input of the CRF?
Can you repeat it?
It's a slide 13, I think.
Can you repeat the question?
Yeah, it's for the CRF, the conditional random field part of your model. And I was just wondering what kind of input you provided it. Is it a distribution over labels given by the transformer, or is it something else?
Oh, because in traditional named entity recognition model, there usually add a CRF layer on the top, because it can compute the tag transition scores.
Yes. Okay, so it's just for computing the transition. So the output of the transformer is a probability distribution over the different tags. Is it correct?
Yes.
Okay, I don't. Okay, somebody talked. I don't know who. And another question I had is, oh, sorry, Tingsu is wants to ask a question. So go ahead. You can unmute your.
Yeah. Hi. I just want to ask, when you separate the sentence into words, you said you used a package called Jieba. Did you update the dictionary they have, or did you not? Because the dictionary was like a couple years old last time I checked.
Jieba could add some dictionaries in it.
So you did update the dictionary?
When I trained this model, I didn't add some new dictionaries in it, but in our future, I would add some computer science dictionaries in it.
Okay, and so the model you have, it's like a character-wise and a word-wise. So you're saying that the word-wise might not be very accurate. So you're trying to use the character-wise to make it a bit more accurate. Is that what you? Is this the main goal?
No, we have some experiments to test the accuracy of characters and words, and the results show that characters is more have a higher accurate result of than words, because can be influenced by.
But do you know? Yeah, but do you know that if the word is not performing, the word-wise is not performing well, is it because of the segmentation problem, or is because of others? So did you? What I mean is that, so currently the word level, it's produced by Jieba and segment sentence into words. But did you, for example, produce a hand-labeled segmentation for sentences and then see if that actually is better than, how is it comparable compared to the character level? Because my understanding is that there are two levels involved, and the first level, the segmentation, is not working very well.
Because the model we aim to use the word feature to construct the boundary of word.
I'll ask you afterwards. Thank you.
Okay, we have last question from Karin Verspoor. You can go ahead.
No, actually, I wasn't trying to ask a question. I was just trying to make the session chair aware that I was here. Sorry.
Oh, okay. Yeah, but we'll discuss later. Okay, Ningshan?
Yeah.
So can you play the video of the talk of Ninja?
Yeah.
Okay, so it will be the last talk. It was planned to be the scheduled as a second talk, but it was postponed, as I said. So it will be the last talk of the session. And hopefully Ninja will be able to join us for the question session, at least by text messaging.
Wait. Oh.
May I help in Chinese?
Yeah.
Sorry, I just want to help her to make sure that the video is played fine. So I just unmute myself. I'm sorry. 你是要就是视频放还是放那个还是放 PPT 啊？
它是放 PPT， 然后它会出来它的视频。
So you can play it. And then.
Okay.
So for the people of CLEF, please wait a little bit. We're still running the previous session.
So 你在那个你左下角那个 mute 那个上面点一下箭头，然后选那个 same as system speaker 的那个选项，就是叫什么 speaker， 你要选 same as system。
Same as system。
就是上面不是有一个 select microphone and select speaker 吗？现在
我的中文的。
对，但是你不是有一个 select speaker 吗？那个就是 I don't know how to say speaker in Chinese。你就选第1、2、3第3个，你从头可以选的那个选第3个。
Can you please if you for not enable, there's another deep learning session.
Yeah, I think it would be wise to postpone this talk if there are technical issues, and you can join a bit earlier and see with the hosts if how it should be done.
Okay, maybe I can help her.
So the next you have a deep learning session Friday at 15:20. So session A9. Maybe you should see if you could present there. Okay.
Yeah, thanks. I think it would be easier because otherwise we will delay all the conference.
And,
okay, well, so I want to thank all the participants to this session, and and wish you a good continuation with ECIR, even if it's not in Portugal.
Thank you. Ning-chan, can you stop sharing the screen so I can take a group photo? And if you can turn on your cameras.
Is okay?
No. Stop sharing screen.
Okay.
I have stopped.
I've stopped for you. Okay. Can you turn on your cameras? The people from the previous session. Oh. Hamza? Clement? No?
Clement?
Okay.
Okay, I'm here.
Ning-chan, can you turn on your camera?
Okay. Sorry.
So 1, 2, 3. Okay, thank you. Okay.
Thank you.
So, let's advance for the next session. So change role to attendee.
Okay, well, bye.
Bye. Bye, Benjamin. So I will promote now Pavel. So Nicola, you here? Okay.
Hi.
Hello. Let's try to find out. There's a lot of people here.
Yes, a lot of people.
Okay. I'm going to promote everyone. So all the authors from the CLEF, please raise their hands. And I'm going to try. Oh my God.
They are 12. Do you need the names?
Okay, I'm going to promote everyone, and then we will kick out everyone that doesn't fit. Okay. Wait, I'm promoting people. This is almost a meeting.
Yeah.
I think I'm going to take a picture of right now. So, wow, smile. Okay. So Nicola, do you think you're missing?
So Bogdan, I see him. Richard. Okay. There should be also Doug. Yes, there. Anastasios. Hi. Alberto. Where is Alberto? Okay. Karin, I see you.
Hello.
Lorraine. There should be Lorraine for e-health. So David Lozada. So Rui, you need to grant access to Alberto Barron Cedeno.
Can he raise his hands?
Can you raise your hand, Alberto?
Okay. Oh, I think I promoted him.
Okay. David.
So guys, this is, so you do your presentation, and this is how many minutes, Nicola?
7 minutes, basically. Yeah.
At the end, people can do questions in the Q&A or
yes, we have room for one quick question, basically. Yes. And I will try to show something. Can you see it?
Okay, you have to show it like this. If not, you have to show it like this, because if not,
I will do like this. Yes, 2 minutes left, and like this when you are over. So Matteo, yes, I see you. Philip, I see you. Martin, podcast is not here. yet. Alexander, yes, and Alexis. So if I'm right, we are missing Martin, David, and Lorraine. Here we have Rim and Deepak, who I guess are not.
Hello.
Hello. Are you going to present anything about CLEF? I don't think. Rim.
Sorry?
Are you going to present anything about CLEF? I don't think so.
No, no.
Okay, so Rui, you can demote Rim from being panelist.
Done. So Lorraine is part. Is Lorraine a speaker?
Yes, Guru.
And David Lozada?
Yes, exactly. And there is Deepak, I guess, is not going to present. Hi, Lorraine.
So Deepak, I remove.
Yeah.
Where's Deepak?
So can we do a test to see?
Okay, Deepak is not a panelist, so.
No, he is not a panelist.
If one of you wants to do questions, please press the participants menu and raise your hand just like the attendees, okay? So Nicholas, shall we, oh, so this starts in 2 minutes, okay.
There is one thing. Doug would like to show a video while Richard is talking. No, I didn't understand. Can you give the mic?
No, I'm just here to answer questions. If somebody gets a question, Richard can't answer.
Okay.
Thanks for your help, Doug.
When you share videos, please share the computer audio. There's an option in there next to I think in the more options, share computer audio, because if not, the sound of the video will not be audible to the users. But we can test that when we get there.
So we are basically just missing Martin Potast for PAN.
Which is the first.
No, Bogdan is the first. Can you check if he is in Martin? If you are in the attendees, can you raise your hand so we can ask you?
Martin
Potast.
Yeah, he's here.
Okay, and I still see Deepak among the panelists.
He's not, no, he's not. If you look into participants list, he's not a panelist. He's just an attendee that is allowed.
No, I mean, I see. Okay, there was still the box in my view. So guys, as I was saying, 7 minutes or even less if you can, and there is room for 1 minute question. Okay, so if also Martin turns on the screen, we can now do the photo with everybody.
Okay.
Martin, could you turn on your screen?
Okay. Just one quick pick. And 1, 2, 3.
Thanks.
I'll
Okay. So do you want to start?
So Nicola, I will be here to help and to unmute attendees, but you control now.
Okay. So let's start because we have a very dense session. So welcome everybody to this session on CLEF 2020. As you know, the purpose of this session is to advertise the activities of CLEF to the ECIR audience and to strengthen the link between the two communities, because what we would like to happen is that ECIR attendees join or participate in CLEF activities, in CLEF evaluation activities, and CLEF outcomes from the CLEF lab and CLEF evaluation activities are then fed as papers to the next round of ECIR in order to create a positive feedback for everybody. So in this session, you will have work through all the activities planned for 2020, which are 12 labs in all the areas of multilingual and multimodal information access. So I would start from Bogdan Ionescu, who will talk us about image CLEF. So it's up to you, Bogdan.
Thank you. Thank you, Akin. I think you can hear me. Yes?
Yeah.
Perfect. And you can see my screen here. Yes?
Yeah.
Perfect. Okay. Greetings, everybody. It is a pleasure meeting you. I hope everybody is safe and in these times everything goes well. I'm going to describe very briefly our Image CLEF lab. This year edition is about multimedia retrieval and live logging, medical, nature, and internet application. As it's just an advertising, we don't have yet the results, so it's just announcing the tasks. I'm Bogdan Ionescu, and I'm the lead organizer of Image CLEF since 2017. And together with my colleague Henning Müller and Renaud Peteri, we are organizing yearly this event. Just to acknowledge all the task organizers, there is a lot of people and a huge effort to run this lab. Just a quick facts about the lab. It started in 2003 as part of the CLEF. In 2004, we started the first medical task, and they became regular. And in 2019, we switched a bit the focus, and we attempt to have a diversity of application, not just several fields, but to be as broad as possible. The lab is organized yearly till since 2003, so it's a regular lab. Just some insights from 2019 to understand the scale. We have like 350 submitted runs and 50 working notes published with the proceedings. In this year, we have four tasks. One is about live logging. The other is about coral natural images, and we have an internet application task, and we have a group of medical tasks. So I'm just going to run through them and present you the main idea. So for the live logging, everything is about live logging data recorded from personal devices. There are two subtasks. The first one is in the 4th edition. It's about live log moment retrieval. So basically, you have the developed system that retrieve automatically activities from this information. The data is consistent. All the data sets are validated and are rich data sets for each of the tasks. You have some images here about what an activity means. For instance, you are retrieving all the recordings when you have coffee with friends. So this kind of algorithm. There is a second subtask about this is a new one about sport performance live log, and you are required to predict some expected performance from an athlete. Again, the data is the real world data from actual people training and wearing the live logging equipment. The coral task. This is about natural images. It's about developing algorithms for segmenting and labeling coral images. There are a lot of applications like creating 3D models or monitoring the coral activity. There are two subtasks. The one is a classic annotation and detection. So basically you have to label the images according to the coral type. The data, again, it's a real data from coral reefs in Indonesia in this case. You have some examples. You have a coral image and you are requested to provide bounding boxes for different types of corals. The second subtask is about pixel-wise parsing. It's a segmentation task. So it's similar with the previous one, but you are required to segment precisely each coral in the image. It is the same data set used as for the other one. The drone UI, it's in the first edition. This is a very interesting idea, and behind there is a working startup. The idea is to automatically build your website by drawing the user interface components. So you draw them on a paper, and you are tasked to automatically recognize their types and purpose. And based on that, you can generate automatically the website code. The data is, again, it's real data. Basically here there are 21 classes 21 classes of objects to detect. Okay, the medical tasks. We have regrouped all the medical application into one task. The idea is to exploit as much as possible synergies between the different tasks. So we have three tasks. The one is very popular is the visual question answering in the medical domain. Here, there are two approaches. So the first one is the classic visual question answering. So you are requested to give an image and a natural language question to respond using the visual content. And I'm going to provide you an example here. For instance, in the first image, the question is this a contrast or a non-contrast CT? And you have to answer by analyzing both the question and the image, and the correct answer is contrast. New for this year, it is a vice versa case, so visual question generation. So you have to go from image to question. So you have the image and you have to generate the question raising the response. The data is, again, it's consistent, and also you can use in these tasks the previous data sets released in 2018 and 2019. The second medical task is about concept detection. This is a classic task. It is in the 4th edition. So basically you have to recognize from medical images the concepts within the image. So you have to associate text concepts to the images. The data set is huge. There are like 2 million archives and 6 million images and caption pairs. So it's a truly large scale task. The final one is about tuberculosis detection and prediction. You have to, again, to label cities with the tuberculosis degree level. And you have to assign also probability scores for that degree to happen. There are different annotation for each lung. So basically there is the double number of images annotated. So you have the left one and the right one, and you have to predict them separately. Okay, this is in a super fast, in a nutshell, what we propose this year. Registration is still open. And I would like to announce that CLEF21 is going to be hosted by us in Bucharest. So we are waiting you to, at that time, I'm sure there will be no virus problems and any constraints. Thank you.
Thank you very much, Bogdan. Any questions for Bogdan? Okay. So thank you again. Thank you. We can move on to the next presenter, who is Richard Zanibbi, and he will talk about ARQ math.
have to share my screen here. Sorry.
Yeah.
And play. Okay, can everybody see that?
Yes.
Okay, great. So hello, thank you, Nicola. So my name is Richard. I'm going to be talking about the ArcMath task. This is going to be the first time this task is run for CLE 2020. The people that I want to thank first are my teammates. So Anurag Agarwal, Behruz Mansouri, Wei Zhang from RIT, and then Doug Ord from the University of Maryland. So the goals of the task are twofold. First, to advance math-aware search, and also advance semantic analysis of mathematical notation and text, particularly when they appear together. The collection that we're using for this task is from Math Stack Exchange, which is a well-known community question answering forum for math. There are about 1 million questions in our collection and about 28 million formulas in LaTeX. And this data is stored in some linked XML files provided for free use on the Internet Archive. The raw data is well organized but hard to work with, so we've also provided some tools to parse the data into threads like you would see on the web page using a Python tool. Further to that, the tool is able to generate HTML, static HTML pages that represent the threads, and so we've actually generated those and made those available for participants as well. And that's made available for study, checking, and also our evaluation tools will make use of these threads at annotation time. In addition, the formulas themselves, we have some separate formula indices in tab-separated variable files. We have 2 encodings of appearance, what the formula looks like. That's LaTeX and presentation MathML. And then we have a semantic encoding for the operator trees representing the application of operations to arguments in content MathML. So there are 2 tasks. The first one, the main task, is finding answers to mathematical questions in the forum. We have 98 topics for this. Now the task goes as such. So given a posted question from the year 2019 as a query, you're then allowed to search the answer posts that we provided in a static snapshot from the years 2010 to 2018. So you have to find old answers to new questions. And the task, of course, is to return relevant answers. So as shown in the example here, we have a query containing a formula asking how to evaluate a sum. And on the right-hand side, we have some search results showing, in this case, 2 relevant hits in the green boxes and 1 that's not. The second task is to do formula search. But an important feature here is we're going to be evaluating the formula search in context. In other words, in the context of the post in which it appears, in the context in which the query or topic formula appears. So in this task, we're going to take topics from the first task. So we're going to take another question post from task 1 from the year 2019. The task now will be to search both question and answer posts from the years 2010 to 2018 and return relevant formulas, specific formulas, but located within the post they're associated with. So taking the same topic we saw from the previous slide, now the query actually distinguishes a specific formula that we're focusing on. And the search results are showing 3 formulas, each of which belong to a post that they're associated with. Okay. Now, one of the hardest questions we had while devising the task was trying to figure out how to do the evaluation for this. So I'll talk about that just a little bit now. So what you're seeing here is the evaluation interface to be used for task 2. This is implemented in the tool Turkle, which is available freely online. So it's an offline version of Mechanical Turk, okay, that you can distribute very easily. So the hard question here is, so if I have a topic, and you can see here, sorry, I'm pointing at the wrong thing. You can see here at the left, we have a query formula within the context of its post. So this is an integral of e to the x squared dx. And we can see that there are 2 different posts that match the exact same formula. Now, a question is in all instances, is the formula going to be relevant? In this particular example, it's very likely it will. But because variables and operators can be overloaded and have their meanings change frequently in mathematics, you can't assume that the formula will be used in the same domain as the question. So for example, the question may ask about sets, and the answer may talk about abstract algebra, for example. So the way that we're going to approach this is we're going to identify formulas that have the same appearance based on our LaTeX representation. We're then going to pool the posts that are associated with that unique formula. And then we're going to sample the posts not just purely at random, but randomly across threads. So we're going to try and make sure that we capture different question threads for each post that's included in the pool for evaluation. Then each of those, shown here in the middle, we have 2, it could be 10, could be more. Each of those will be evaluated separately. So what you see on the right-hand side is we're going to evaluate relevance using a multi-level scale. And so we have non-relevant and then low, medium, and high relevance. We'll also have 2 options to indicate if the assessor just does not know if the formula in this context is relevant to the query, and to indicate if there was a system failure by either the search system or the evaluation tool. The runs for both tasks, so for both task 1 and task 2, are going to be evaluated using normalized discounted cumulative gain prime, the prime indicating that we will only use evaluated hits. The significance of this is that when people go to run the data, thanks Nicola, when people go to run the data offline, once the task is completed, this will allow a fair comparison because everything will be compared on the same posts. Oops, sorry. Next, there we go. Second last slide here. So baseline systems, we're going to have 2 baseline systems, 1 for each task. The Approach 0 search engine, which is available online at this link shown here, is an ad hoc retrieval system that combines text and math and uses formulas in the semantic encoding operator trees. And then for the formula retrieval task, we're going to use a system that actually only uses math formula content to do the search. And the formulas in that system are considered in both their appearance and semantic encodings. Okay, and these are by Zhang and Divya. Okay, so thank you very much for your attention. We'd be very happy to have more people join the task. We'll be sending out an email to try and facilitate that. And if you have any questions outside of this meeting, please feel free to send email at the address shown. Thank you very much for your time.
Thank you very much, Richard. Any questions for Richard? This is a very thrilling new task for us in CLEF. Any curiosity?
One hopes.
Okay, so thank you again, Richard. And the next speaker is Anastasios Nentidis, and he will talk us about BioASQ.
Hello, everybody. This is Anastasios Nentidis, and I'm going to present you the BioASQ Lab at CLEF 2020. This is about the BioASQ challenge on large-scale biomedical semantic indexing and question answering. This year, the challenge is co-organized by the National Center for Scientific Research Demokritos from Athens, Greece, and the Barcelona Supercomputing Center from Barcelona, Spain. The BioASQ challenge is a series of challenges on biomedical semantic indexing and question answering, and this year it is structured into 3 tasks. The 2 first tasks are the established BioASQ tasks already available in previous versions of the challenge, and in particular the task A on large-scale online biomedical semantic indexing, where the goal is actually to annotate biomedical articles in English with topic labels from the MES hierarchy. The task B on biomedical semantic question answering, where the goal is given an English biomedical question in natural language to retrieve relevant material and provide the answer to this question. Finally, the third task, which is a new task that we are happy to introduce this year, is the task MESINESP on medical semantic indexing in Spanish, where the goal is to provide topic labels for medical documents written in Spanish, and the labels should be from the DEX hierarchy. The BioASQ challenge has already run for several times in the last 7 years, with 60 teams participating from 19 countries around the world. And this year, as part of CLEF 2020, we ran the 8th edition of the BioASQ challenge. The participation can be partial. That means each participant can participate in submit results for any of the tasks or subtasks or batches. And some small prizes are also awarded as an additional motivation to the teams, again, independently for each task and subtask and batch. All the infrastructure and the data sets developed for the challenge are open source and available to the community. In task A on semantic indexing in English, the participants can train their systems in a dataset of more than 14 million articles in English, annotated with golden labels from the MES hierarchy, topic labels. And we distribute new test sets of unclassified Medline articles, and participants have 21 hours to assign MES topic labels, MES terms to these articles. Later, when eventually these articles are annotated with topic labels, with ground truth topic labels from the Medline curators in NLM, we evaluate the system responses using both flat and hierarchical measures. The task is running, is currently running, and it's structured into 3 batches of 5 test set each, which run weekly, 1 test set every week. In the second task about question answering, the participants can train their systems in a dataset of more than 3,000 biomedical questions in English, annotated with golden relevant material and answers. This task is further structured into 2 phases. In the first phase, we release the questions, that is only the body of the question in English language, and the participants have 24 hours to retrieve and submit relevant material, that is relevant biomedical articles, snippets inside the articles, useful to answer the question, relevant biomedical concepts and triples. Then in the second phase, we also provide some relevant articles and snippets provided by the same experts that developed the questions. And the participants have again 24 hours to extract and submit exact answers and ideal answers for these questions. The exact answers can be yes or no, or an entity or a list of entities, depending on the type of the question. And the ideal answers are paragraph-sized answers in natural language, in English. Then the evaluation for both phases is based on automatic standard measures against the golden elements and answers provided by the experts, but also manual assessment that is done directly by the experts using the BioAsk tools. So they see the answers of the systems and put some scores on them. The task is structured into 5 batches, which run every 2 weeks. And in each batch, we have a test set for both phases. The task is also still running. Finally, the new task that we are happy to introduce this year, the MESINESP task. Here, the participants can train their systems in a dataset of more than 300,000 articles written in Spanish from IBEX and LILACs, and that are already annotated with DEX terms. And they can also fine-tune their systems on a development dataset of 1,500 articles annotated for the task by 7 experts. Then we will release a test set of new unclassified articles in Spanish, and the participants will have limited time to assign DEX terms to these unclassified articles of the test set. This test set will also include some background data of other articles of different types. Then the evaluation of these submissions will be based on manual annotations following the same procedure that was followed for the manual assessment of the development dataset. The awards for this task are sponsored by the Spanish Plan for the Advancement of Language Technologies, and the task will run next week in a batch, so participants can still participate. We are grateful to our sponsors, our platinum sponsor Google, and our silver sponsors Atipon and PlanTL for the MESINESP task, and also to our past sponsors that supported previous versions of the challenge. Thank you for your attention. Any questions?
Thank you very much, Anastasios. Perfect timing.
Thank you.
Any questions? Raise your hands or write them in the chat or in the Q&A tab. Okay, so thank you very much.
Thank you.
Again, Anastasios. And we can move to the next speaker, who is Alberto Barron Cedeno, and he will talk us about check that.
Okay, hello, can you hear me?
Yes.
Great. Let me share my screen. You might be listening to some music because we have a daily concert at 12:30 here in the city where I am. So I apologize if that's the case. But at the end, it's nice to be confined and have music every day.
Indeed.
So it looks like I don't have permissions to share my screen, which is very funny.
Maybe the previous.
That's weird.
Okay, let me. Oh, I need to quit and go back, so I'll be back in a second. Maybe you can switch to somebody else. I managed to activate it, but it's telling me that I need to switch it off and on again.
Okay. Karin, would you be
I'll be back.
Yes, Karin, would you be willing to go on stage?
Sure, no problem.
Okay, so the next speaker is Karin Verspoor, and she will talk about KMU, new lab at CLEF this year.
Great. Okay, can you see my screen?
Yes, thank you.
Good. So my name is Karen Verspoor. I'm from the University of Melbourne, and I'm representing a team which is a collaboration between the University of Melbourne and Elsevier. And Elsevier is a very important partner in our project here because they actually provide a lot of the domain expertise that we need in order to prepare both the task and the data set. So the names you see at the bottom of the screen there are a combination of the team in Melbourne, and they're mostly in blue. We also have one visitor from Fujitsu, Higori Yoshikawa, who was with us for a year in Melbourne. So she's an adopted member of our team. And the names in orange are the key people at Elsevier that we've been collaborating with in this context. And there are other people that are involved with the project, but these are the key people. So KEMU is an information extraction project where we're trying to focus on named entity recognition and event extraction from chemical patents. And we're specifically focusing on chemical reactions and how they're described in the text. And the motivation for this project is that there's really an incredible amount of information about chemical compounds that's only available through patent documents. So much of the research that's happening in pharmaceutical industries and chemical industries appears first in the patent literature long before it's in any kind of peer-reviewed scientific literature. And so what we're trying to focus on is somebody trying to chat to me. Sorry. What we're trying to focus on is the information about those chemical compounds that's available in the patent documents. So we've been developing these tasks. We feel important downstream effects for chemical research. So we'll open up and make it more accessible the information that's available in the chemical patent literature. And of course, we're providing a new data set and hoping to advance the state of the art in information extraction over chemical patents. And now my screen isn't shifting. Okay, so we have two primary tasks following from that. One is named entity recognition, which is focusing on specific types of chemical compounds. And I'll go into more in it, but it's actually a much more fine-grained task than the previous chemical named entity recognition tasks that have been made available, because it's much more oriented towards the role that the compound is playing in the context of a chemical reaction. Then task 2 is to do event extraction over chemical reactions, which essentially means identifying the participants in a particular chemical reaction. We've developed a corpus of 1,500 reactions, which corresponds to 7,000 sentences, which have been annotated for these two tasks by domain experts through Elsevier. So here's an example of the sort of data that we have. As you can see, it's quite complex data, requires sort of sophisticated understanding of the domain in order to make sense of it. You have to understand, of course, complex chemical terminology like 2-chert-butyl-4, ethyl-5-amino-3, etc., as well as the particular relationships that are relevant for describing reactions, dissolving, adding, and mixing, and so forth. And so in this example, we have 4 key entities. And as you can see, the types that are associated with them are really about the roles. So it's not just, is this phrase 2-chert-butyl, et cetera, a chemical, it's what kind of role is it playing in the context of this reaction. And in particular, that one is a starting material. Triethylene is a reagent. And then the events that we would be hoping to extract from this are the dissolving and the adding events. And so what we see here annotated is that we have particular arguments that we expect the systems to identify as the participants in a particular reaction. So in this case, the dissolved event involves the T-chert-butyl-4 ethyl, et cetera, and the dichloromethane. So the types of entities that will need to be annotated by the systems include these, so reaction products, starting materials, reagents of a reaction, solvents that are dissolving a particular chemical resulting in a solution, and also some sort of properties of the reaction, such as the temperature, the time, and the yield, which is the amount of material that's produced by the reaction. The events fall into 2 primary categories. So we have workup events, which involve isolating a chemical product, and reaction steps where particular materials are converted into a product. And our annotation guidelines are very detailed and describe these much more carefully. You can actually see some sample data for the task fully annotated through our website. So we used BRAT to do the annotation and the BRAT format to release the data. And so if you're curious at what the data looks like, you can actually explore it through that website directly online. We'll be using the standard metrics used in information extraction to measure precision, recall, and F-score. We'll be using both exact matching, so requiring that the exact span of the entity or the event trigger is captured, but we'll also allow for some more relaxed matching through approximate span matching. Of course, the types won't be relaxed; they have to be accurate. We're going to have 2 phases in the evaluation. In phase 1, we're focusing on the named entity recognition task, as well as an end-to-end evaluation, which will be suitable for systems that do the event extraction task and also the named entity recognition task, or possibly approach it as a joint learning problem. And in phase 2, we will provide gold standard entities, and therefore the phase 2 evaluation will focus on event extraction only, and will be suitable for participants who really want to focus on the relationships and can assume gold standard entities in developing their methods. So we have actually 2 websites. So we have the original website that we set up, but we've developed a new submission website where there's a leaderboard, which can be private or public. So we're going to hopefully have some participants sharing their results as they go through, and we're going to be putting up a benchmark system for the public leaderboard in the next couple of weeks. We released sample in early March. The training data is available after signing a data usage agreement, and we plan to begin the phase 1 evaluation period on the 22nd of May, followed by the phase 2 evaluation period starting on the 29th of May. And so everybody is welcome to come join us. At the moment, we had 24 teams that registered through CLEF, but so far 8 have registered through our data submission site. And so, yes, so we invite participants to participate on these 2 new tasks with 1,500 snippets that have been fully annotated for the chemical named entities and the events relevant to chemical reactions. And we already have participants both from academia and from industry. So I think that kind of demonstrates the relevance of the task to the pharmaceutical industry. And that's the end. Thank you.
Thank you very much, Karin. Any questions for Karin and this task, which bridges between academia and industry with a clear use case?
We have a question from you, Juan Bascur.
Yes. My question is, why cannot because you're looking for something in the document that should be reported, right? Like this is a patent, they should write the chemical compounds. So why is this not happening? So my question is, how, why is this a problem, right? Why they are not reporting the chemical compound?
So they are reporting the chemical compound, but what they're reporting on is the synthesis of the chemical compound. So every new chemical compound or new drug that's developed is developed through a process of transforming existing chemicals into a new chemical, right? So what the chemical patent describes is how do you make this drug or how do you make this chemical? And so you know what we're really trying to get at is the composition of these chemicals and sort of the recipe for creating them. So it is made available. It's just that it's made available through the complex description of the process to make it. And the name in itself, the name of a chemical compound, which is typically what's referred to as the title compound in these patents, which is the new chemical that's being described, is not enough to tell you how to make it. And so what the chemical patent describes is much more detail around producing that chemical. Does that make sense?
Yeah, so if I understand your answer, is because people are not writing the description of the creation process in a way that you can extract it in a standardized process.
No, it's written using natural language in a patent application, and so it's meant to be understandable by patent officers who grant patents. It's not really meant to be, and in fact, some people might suggest that a lot of what you might call intentional obfuscation happens in the context of patents, because of course companies that develop these drugs are playing a fine line between making the patenting and protecting their drug and making the giving other people the ability to make the drug, right? So it's they have to they want to tell enough to get the IP rights for the protection for the chemical, but they don't want to give so much away that they're giving the whole thing away, their advantage away.
I see. It's a complex issue.
That's right.
Thank you.
Thank you very much. Thank you again, Karin. And I think we can move to the next, who was the previous speaker, Alberto, and check that.
Yeah, hello. I hope this time I will manage to show you my slides. Can you see it now?
Yes, it works.
Okay, awesome. So I apologize for the issue. So the concert is over. Maybe that was the reason this thing crashed. So my name is Alberto. I work for the University of Bologna, and I'm going to present the Check That Lab. This is the third edition of the task, the 2020 edition. And the topic we are working on is the automatic identification and verification of claims in social media. So the scenario is as follows. Let's say you have a Twitter account, and obviously when you see at your tweets thread, there are some tweets that are actually fact-checking. For instance, let's say a person is writing this tweet: don't panic with COVID-19, the sunny and warm weather is around the corner and we will not suffer as they are doing in cold places. Let's say this is from South US. So these kind of tweets are definitely worth checking. So because before you spread the word or before you actually believe to these claims, it would be nice to have some background or some support to actually determine if you are safe of COVID or not because of the weather. So if before just spreading the tweet, retweeting to all your contacts, if instead of doing that, you just go in Twitter itself or on the web and look for the position of some of the institutions about it, you could find that this is actually false. So there is, for instance, the World Health Organization who says exposing yourself to the sun or to temperatures higher than 25 degrees does not prevent the coronavirus disease. Or maybe some scientists who say that hot weather, or there are cases which have been reported regardless of cold or hot weather. So if you do that as a user or as a company trying to determine the veracity of a tweet, you could save a lot of time to people and you can maybe even save lives. A second example I want to share with you, which is very recent, this is from probably 3 or 4 days, and this one is real. The previous one, it was, I just made it up. There was a current situation in Spain nowadays because there is this new policy that most of you might know, which says that WhatsApp will now only allow to forward posts to one single conversation at a time, with the idea of combating fake news. But in Spain, there is an ongoing campaign who claims that there is this new policy applies only to Spain. And this is because there is a fact-checking company, a Spanish fact-checking company, which has collided with the current government to set this limitation. And there are political parties who have a live campaign on Twitter, WhatsApp, Facebook, claiming that there is one person behind this policy. Again, only applying to Spain. 90% of users just believe this, in particular those which are aligned with this kind of parties, but it is trivial to go online, try to search with some keywords about COVID, Facebook, the name of the company, and you will find news articles like this one, for instance, from The Guardian, that says that this policy has been applied all around the world, and it's not only specific to Spain, and it is not dictated by a Spanish company. So this is what we have defined as the good citizen or the good journalist flowchart. So given a tweet, the first thing you have to do here on the left is you would like to define or to determine if this tweet is check-worthy or not. If a tweet is not check-worthy, then you can simply relax and keep with your life as it is. But if it is check-worthy, the first thing you might like to find out is if this tweet or this claim in general has been verified in the past or not. If you find that somebody else, for instance, one of these companies like Neutral has verified a tweet already, you simply have to go to their website or to their Twitter channel and find out if this is true or not, if COVID with hot weather is less damaging. If nobody has verified a claim, then the next step would be actually retrieving some evidence from the web. And finally, with that evidence, verify if the claim is factually true or false. And all these tasks can be very translated in a very kind of straightforward way to information retrieval and natural language tasks. And these are the 4 tasks that we have developed for this Check That initiative. So task 1, which we call check-worthiness, is predicting whether a tweet in a Twitter string contains a claim worth checking. I would just like to stress that both we are working in Arabic and English. In both languages, we are including instances about COVID-19. We have a 5th task, which I'm going to describe now because it's very similar to this one. It's also about check-worthiness, but this one is not on Twitter. Instead, we have material from political debates, speeches, and press conferences. And once again, the idea is for each of the utterances in these materials trying to determine if there is some word fact-checking utterance. Task 2 is given a tweet claim or a claim in a tweet and a set of already verified claims, rank those that verify either the full claim that we have as a query or at least one subclaim in it. So this is a ranking task. The third task is, we call it evidence retrieval. So in case the system or the person didn't find previously verified claims, now we need to retrieve evidence. Given a tweet and a list of previously retrieved web pages, we need to re-rank the passages in these web pages which are useful for verification. And finally, the task 4 is given a tweet and that set of web pages that have been identified in step 3, finally estimating this claim is factually true or not. This was the original plan we had. You can see on top we have the 5 tasks, and on the left we have the languages, the working languages, Arabic, English, and Spanish. This was our plan. For instance, for English, we had task 1, task 2, and task 5. Because of the current situation, this is our scenario nowadays. So we had to cancel Spanish completely because we managed to partner with a Spanish fact-checking company, but we had 2 problems. The first of them was that between December and January, there were the Spanish elections and they were trying to to make up the government, and they didn't manage to, so they were super busy. Eventually, they elected a president in Spain. We were ready to start with the annotation and COVID came up. So we didn't manage to create any data set in Spanish. But we are still running English and Arabic. In particular for task 3, we are a little bit late, but we are almost there. So you know what is the deadline for the registration. Here you can see the deadlines for the English task, which are task 1, 2, and 5. All training data is already available for you to start learning your models. Just have a look here. We are going to release the test data set roughly by the end of May. So that's it from my side. Please go visit our website if you are interested, get in touch with us. And also thank you very much to the CLEF 2020 organizers. I think you're doing a very good job in converting CLEF into an online conference. Thank you very much.
Thank you very much, Alberto. Any questions for Alberto? Okay, there is Diego. Okay, you can talk now.
Yeah, hello, thanks guys. Thanks Alberto for the talk. My question here would be, how do you define the source of truth for your for your claims? Is it manual notated?
Yes, it's manually annotated. Okay, cool. So some of the steps are obviously automatic, like for instance, the retrieval of some of the evidence, but the final decision is manually made.
Yeah, I was wondering how you decide whether it should be double checked or not, based on like automated fact check systems or like manual, because would be a total would change everything here.
It's all manual, and this is why things have been complicated, because as I said, in this partnership with a Spanish company, the idea was having, or the plan, it was already in place, it was having 3 or 4 journalists full-time annotating this kind of inputs, and then to create a good gold standard. So this is why at the end didn't manage to do it for this year.
Yeah, amazing. And just out of curiosity for now, how many claims, how big is this data set?
As far as I remember, we're talking about a few hundred claims for the 2 different languages. But if you can go to the website and have a better look.
Yeah, absolutely. Okay, yeah. Thanks a lot.
Thank you very much. Let's thank Alberto once more. And
there is still a question from Juan, if you want to take it.
Okay. I was thinking it was from the previous. Okay, so Juan.
Okay. Yeah, first, I'm sorry to hear what's going on with the political parties. And second, how has your proposal been received by journalists? Are they interested?
Yes, they are interested. As I told you, we got in touch with this Spanish company, I think by September last year. It took some time for them to be in, but eventually they did buy the idea, and they are very interested because actually they are building their own fact-checking systems. And they were very happy to see that there was a community already. This check that has been around for 2 years now. So I have to say they were not aware of it. So it was nice to make them aware, to share with them the proceedings from the last 2 years, and they have started to make a more robust system of their own. So yeah, they were very interested.
Congratulations. And your group is the only one that is automatizing fact-checking in the world?
No. Well, as I said before, this has been running for 2 years now, and there are many different groups working on this. For instance, there are people from Finland, from France, from Italy. So if you're interested, once again, if you go to the website, we have links to the proceedings from the previous 2 editions, and you can see all the approaches. There are roughly, at least I would say, 7 or 8 active teams working on these kind of topics, besides the one that we are going to take part of it this year.
Okay, thank you.
Thank you very much. So let's thank Alberto once more, and let's move to Lorraine. She is the next speaker, and she will talk us about e-health. Guys, not only you, Lorraine, everybody, please try to be compact with your talks, otherwise we run late. Thank you.
Hey, can you hear me?
Yes.
And can you see the screen?
Yes.
Perfect. All right. So I'm going to present you CLEF, which is run since 2013. So I'll start with a COVID example as well. Let's see, we've had a lot of debates about chloroquine in France, I guess in all the countries. So as an example, I wanted to check what were the side effects of chloroquine to treat COVID. And within the first 10 results, I have an article telling me what Rita Wilson thinks about chloroquine. And I also have an article on PMC, a very technical paper about the side effects. At the end of this search, I don't really know what to think about that. And that's the purpose of CLEF, is to help people get a better understanding of health information and also find results to their search that is better suited to their needs. So we've organized some tasks that are focusing on information retrieval as well as information extraction. And the ultimate goal would be to be able to understand a text like the one you have and get on this text some information, some links, and also well, some semantic information, some linguistic information, and as well some link to further information. So we would like to go from the first part, the small text on the left, to the one on the right. So we're gathering a lot of methods to do that. So since 2013, we've had over 240 task submissions, over 20 tasks. And we did a little analysis of all the papers that were published around CLEF, and we had over 180 papers and more than 1,000 citations for all these papers, so that we're happy there's a great community that is interested into that. So our purpose is to develop processing methods and also resources, and we're looking at multilingual settings. So we've organized tasks in different languages and also provide valuable documentation, obviously, and reliable access to health information, and create evaluation settings and release evaluation results. So on this diagram, you can see all the tasks that we've organized through the past years. I won't go into the details, but as you can see, the green part has all the information extraction tasks, and we've had some tasks in English, in French, German, Spanish and other languages, and most of the data sets are free to download on our websites. And the blue bar that I'm going to talk about as well today is the information retrieval tasks. So this year we have 2 tasks running, and I'm going to present them now. So the first task is a multilingual information extraction task organized by the Barcelona Supercomputing Center. And this task is an ICD coding task on Spanish clinical documents. The second task is the consumer health search task, which has been running since the beginning, and changes from 2018, which was the last edition, are a new pool of documents that would be assessed, new relevance dimension, and also we've added spoken queries. So I'll give you details on all these tasks in the following slides. So the first task, the multilingual information extraction task. So the purpose of this task is to transform clinical texts into a structured format using internationally recognized concepts. ICD code. So basically, Karen went through the extraction process already, but we're trying in a text to recognize some entities, and these can be a patient complaint, a problem, diagnosis, treatment, etc. And the purpose of these is to provide information for decision-making process, but also provide standards for recording clinical information. And obviously it allows statistics and data mining over this data. This task is going to be based on a corpus of 1,000 clinical cases that were anonymized, and they were all selected manually by professionals. Thanks, Nicola. Then the would be 250 tests each. And you can see on the image here that we're trying to identify in those texts the diagnostic, which is from the ICD-CM codes, and the procedimiento, which is the procedures codes from the ICD as well, but the Spanish version. Task 2, the consumer health search task. So we have 50 topics that were the same as 2018. The purpose is to extend the pool that we were using. So the topics are from query logs from Health on the Net websites, and the queries were also provided spoken by different speakers, and we also provide the transcription with the queries. The documents, that's a big roll of web documents in which we included documents from the common crawl, as well as a list of trustworthy and untrustworthy websites. And the assessment is manually made to, so the purpose is to judge the relevance over 3 dimensions: the topical relevance, the understandability, and the credibility of the documents. So we will extend 2018 pool in order to get a bigger evaluation over the entire corpus. And we have 2 subtasks. The first one is ad hoc IR, and the second one is using the spoken queries or their transcriptions. The timeline, as for most of the tasks, so there's still 10 days to register, and then the evaluation cycle ends on the 5th of June. And the submission of all the participant working notes will have to be done in July, and we'll all meet online in September. Now, if I have a few more seconds, why should you consider joining CLEF if you're not working in the health space? Well, first, because you can show that your techniques are working across different domains and data. And also the problems in medical IR are fundamental problems that you'll find in many other domains like the semantic gap, the query formulation, the result understanding, and the cognitive biases. And finally, your work can have a large societal impact, as you can probably see now if you're all Googling stuff on COVID. And that's it. So please join us. Feel free to send us questions, follow us on Twitter, etc. Thank you.
Thank you very much, Lorraine. One quick question for Lorraine. Okay, so everything was super clear. Thank you so much again, Lorraine, and we can move on to David Lozada and the e-risk lab.
Hello.
Hi, David.
Can you see my screen?
No, I see. Double click to enter full screen mode. Okay.
You can see it now.
Yeah. Thanks.
Okay. Thank you and greetings from Spain. I'm going to talk about the e-risk, the lab on early risk prediction on the internet. Oh, sorry. Okay. This is a lab that is organized by me together with Fabio Crestani from the University of Lugano and Javier Parapar from the University of Coruña in Spain. And well, the main goal of the lab is to explore issues of evaluation methodology, effectiveness metrics, and other topics related to the creation of benchmarks for early risk detection. And we approach early risk prediction as a process of accumulating evidence. For instance, evidence coming from social media submissions, and the algorithms have to analyze these alerts, these submissions, and decide whether or not they want to emit an alert when there is enough evidence about the signs of a certain type of risk. So we started in 2017 in Dublin, where we proposed two main ways to participate in the lab. One of them was, an open workshop where we received submissions of papers describing different topics or collections or algorithms related to the topics of the lab. And we initiated an exploratory task on early risk detection of signs of depression, where we essentially provide data coming from social media and ask the participants to make this early risk detection. So we continued in 2018 in Avignon, where we had another round of this task on early detection of signs of depression, and we included a new task that essentially had the same format, but it was oriented to data about anorexia. Last year in Lugano, we proposed three tasks, and one of them was the second edition of the task on early detection of signs of anorexia, and we included two new tasks, one of them using self-harm data, and a third task on estimating level of depression using the full history of social media submissions, and the participants essentially had to analyze this full history of messages or posts or comments made by social media users, and they have to fill a standard depression questionnaire. So this year in CLEF 2020, we had two tasks. One of them is essentially a continuation of the task on self-harm data that we had last year. We have provided the 2019 cases as training cases for the participants, and we collected new data for this 2020 edition of this task. And we have a server that gives these user writings to the participants in a sequential way and waits for their responses. So we use data from Reddit, because in Reddit there are, for instance, many communities with multiple users that are very active and talk about different medical conditions, including depression, anorexia, or self-harm. Typically, the messages, the texts are long, and we can get a large history of messages from each user. And also the terms and conditions allow the use of this data for research. So we approach this as a two-class classification, and then we had to split the data into two groups: a positive group of self-harm users and a control group. And to this end, we employ existing methods that have been proposed in the past, where we essentially run some manual queries trying to search for explicit mentions of self-harm, so users that explicitly mention that they have done some sort of physical self-harm, and then we manually inspected the results in order to get this positive group. And the control group, we essentially got a set of random users from the social media website. So the task, as I said before, it's based on a server that we set up in our lab, and it gives user writings, and waits for the response of the participants. The participants get, for instance, the first time they get the first writing, and they have to decide whether or not they want to make an alert or they want to see more. And this is a loop with our server, and essentially the evaluation takes into account not only the accuracy in terms of the final decision, but also the delay that they took in making this decision. And the second task that we are running is based on giving the full history of user submissions made by these social media users, and we ask the participants to fill a standard depression questionnaire. We have the real depression questionnaire, the questionnaires filled by these users, and we ask the participants to analyze the full history of messages, try to see, for instance, whether or not they find evidence about sadness, pessimism, or 21 dimensions that are mentioned in this standard depression questionnaire. So both tasks are still, you can still engage into these tasks. We will be, receiving results until May. So if you are interested, we will be very happy to have you register at eRisk and participating in these tasks. Thank you very much.
Thank you very much, David. Any questions for David? Okay, thank you again very much. So we can move to the next speaker, Matteo Romanello, who will talk about HYPE, a new activity in CLEF this year.
Hello, can you see my screen?
Not yet.
Let me share it. Here we go.
There is still, okay.
Okay.
Perfect, thank you.
Hello, my name is Matteo Romanello. Together with Maud Herman and Simone Clematide, I'm one of the organizers of the HYPE share task on identity recognition and linking on historical newspapers. So HYPE stands for Identifying Historical People, Places, and Other Entities. It's the first time we organize it at CLEF, and also is the first identity processing share task on historical documents. We focus on digitized newspapers in a multilingual setting and with a wide time span, going from the beginning of the 18th century to nowadays. We are proposing two tasks, the first one on name identity recognition and classification, and the second one on linking against Wikidata. And currently we have 25 registered teams. One word about the motivation. So the recent massive digitization initiatives left us with quite a lot of large-scale archives of digitized contents, and NLP is key to enable a better access to these contents. At the same time, NLP on historical text is hard. It's intrinsically multilingual. There are spelling variations to deal with. there is often noise coming from the OCR, and then gazetteers and knowledge bases suffer of limitations. Older entities or entities that are now disappeared, like places, may not be found in these resources. So historical data for NLP, they need robust solutions. And so far, there wasn't even a data set to benchmark currently existing solutions for net entity processing on historical text across languages. So this shared task was developed in the context of a research project called Impresso, where we are using NLP to transform a large archive of Swiss and Luxembourgish newspapers into a tool that users can use to better access this information. Historical entities are very important for historical research. So users can search, for example, for Robert Schumann and find in our archives all the passages that mention him and go and read the articles. About the task overview, we divide the first task into two subtasks of different complexity. So the first subtask only deals with coarse-grained entity types. For example, we have different types of locations. Here, they will all be recognized as locations. And in the second subtask, we go for a more fine-grained distinction of the entity types. And then the second one is on the linking against Wikidata. To provide the greatest flexibility to participants to decide what to compete for, we came up with a system of bundles where they can mix and match basically the tasks and subtasks. And each team picks one bundle and can submit up to 3 runs for it. So we annotated 500 newspaper articles for a total of about 300,000 tokens and 24,000 mentions linked to Wikidata. This was annotated by bilingual annotators using the platform called Inception, which was extended for this task to be able to display side by side the original image and the OCR text on which the annotation is performed. To overcome a bit the limitation of the size of the dataset, we provide also character and word fast-set embeddings, which are useful for the neural solutions. There are more information about statistics on the dataset and the annotations guidelines online. So for the first task, we ask participants to recognize entity mentions. So for example, here you have an example, the editor of the Figaro, Dr. Depin. The coarse type would be the person, the fine-grained type would be a person individual, because you can also have person collectives. Then we recognize the components, like the role of being the editor or the honorific title of being a doctor and the name. But then in the two subtasks, there are different levels of complexity. So in the first subtask, we are not going for the nested entities like Figaro in this example. We are not going for the components, and we only go for the coarse types. Whereas in the second subtask, we tackle the whole complexity of the task going for all of it. One word about the second task. So we distinguish between the metonymic and the literal sense of a mention. So take, for example, La Chaux-de-Fonds, which is a city in Switzerland. It can be mentioned in relation to the city or in a sports article in relation to the hockey team. So here you have both for the type and for the link, a distinction between the metonymic sense and the literal sense. For the evaluation, we go for the standard macro and micro precision recall and F-score. We provide for the recognition and classification 2 scenarios, a more strict with exact boundary matching, and a more fuzzy one where at least one token of overlap, it's enough for a good answer. And similarly for the linking, we have the 2 scenarios where we try to overcome the difficulty a bit, to accommodate the difficulty of linking the metonymy. So in the strict scenario, only the metonymic link is considered as correct. Whereas in the fuzzy scenario, we take both answers, both links, the metonymic and the literal, as good answers. We release the scorer the participants can use to evaluate their systems against the development set. And this comes with a baseline for the net entity recognition and classification at the course level based on the conditional random fields. So just to wrap up the talk, we believe that HYPE is a good opportunity for developers of NERC and entity linking system to test the robustness of their solutions. The results are going to be useful to the DH community to evaluate the state of the art of solutions. There is this new data set to benchmark the solutions, and annotation guidelines have been already adopted by other projects. There is time until 26th of April to register, and more information about the task is on the website.
Thank you very much, Matteo. Any questions for Matteo? All right. So thank you very much again. And the next speaker is Philip with the LILAS activity, which is a pilot new activity in CLEF this year.
Okay. Hello, everybody. Can you see the slides?
Yeah.
I hope so.
Not full screen yet, but
now we're there.
Now I see your presenter view.
It's always the same. Give me a second. Let's swap that. Better?
Better.
Perfect. All right then. Yes. Hello, everybody. Philip Scher. I'm with Technical University of Cologne, and I would like to present our pilot or workshop lab we will hold at CLEF this autumn. And this is joint work together with colleagues from GESIS and ZBMed. GESIS is one of the largest, or the largest social scientific institute in Germany, and ZBMed is the National Library of Medicine. And both are collaborators here in our pilot lab. So there are two parts in this lab. And as you can see from the title of the lab, the first part is about building up a living lab infrastructure. And the second part is about the area or domain we would like to work on, which is academic search. So let us have a look at these two parts. The first part is the living lab infrastructure that we are currently building up. This will be an environment where participants can have their algorithms and systems be evaluated within the portals and live search systems of our partners. So namely the National Library of Medicine here in Germany and the social science search environment of GESIS. Both are willing and able to open up their systems and to allow us to run evaluations on their live and running platform. Since both of them are from the academic domain, this means that we'll have the opportunity to go beyond the classical paper retrieval scenario, which means both of them offer different kinds of data sets. So scientific data sets, questionnaires, survey data, medical records, and so on and so on and so on. All these platforms allow for cross-language retrieval and so on. So there are different use cases we can pick up that are relevant and interesting for the academic search community. Citation-based search is another use case, and so on. So you see the possibilities are there. So who is the perfect participant for this lab? So first of all, so maybe you are an earlier participant of one of the Living Lab campaigns that were held at CLEF or TRAC in the recent years. So namely the Living Labs for AR workshop, Newsreel was running for a few years, the Open Search track at TRAC, and so on. So there were different approaches where we picked up the parts that worked and tried to skip those that were not that satisfying. And on the other hand, so maybe you're not yet there in the Living Lab community, but you're interested in the use cases around academic search. So namely the BUR workshop that was held here at ECIR 2 days ago, and which is running for the 10th time now this year. Or maybe you took part in the TRAC Precision Medicine or clinical decision track or the domain-specific track many years ago at CLE, and so on and so on. So there are a lot of endeavors who are focusing on academic search, but all of them are mainly focusing on classical offline evaluation. And this is something we would like to bridge, because we think that there is a lot to gain by combining these two directions and approaches. So how can you participate? So since this is a pilot lab and this is a classical workshop lab in the beginning, so we are not having some typical evaluation task at hand right now. This is something we will do in the next year, but to kick off everything, we would like to have this pilot lab in this autumn. So this means if you have participated in one of these living labs before, tell us about your experiences, tell us about your lessons learned, what could be preserved, what do we have to change? Yeah, so we are already in contact to some of the previous organizers of the previous workshops, but from a participant side of view. So what were your experiences? Tell us about them. If you're working on academic search in the living, in the life sciences, biomedical sciences, social sciences, whatever is relevant to these two portal systems we have at hand, tell us about your ideas, about your use cases, about maybe previous evaluations in the offline world you have done. Huh? So what of these can be transferred to our living lab? So we are very interested in your use cases and your ideas. So the roadmap is, all right, the roadmap is to have in this year, have some invited talks, have the opportunity to bring together people interested in all of these, give an introduction to our Docker-based platform we are building, to the portals and the data sets available, and to gather ideas and use cases. And then in the next year, we'll have an ordinary evaluation lab where you will have the opportunity to gain access to these portals with more than 70 million documents, data sets, and so on. Okay, to sum it up, join us, please. Tell us about your experiences, use cases, and ideas. Write up a short paper if you would like to, prepare a short demo, whatever. We are totally open to all the ideas. So since this is not a classical evaluation lab, so we are quite open for different kinds of participation. If you have an idea, just contact us, reach out. We have an open ear for everything. And yeah, in the end, be a part of a very interesting online scenario and new and interesting evaluation technology. Yes, all the rest of the details can be found online. And yeah, would be great to see you virtually in autumn. And yes, if there are any questions, please.
Thank you very much, Philip. Any questions for Philip? So guys, one side remark, you see that we have a kind of incubator model in CLEF for growing activities. Lilas this year is piloting and training for becoming a lab. David explained you that eRisk was born in that way, and also eHealth started as a pilot activity. So this is also for you, if just not for participating in CLE as lab participants, but also if you want to think about proposing an activity, you can go in a smooth way from zero to a full-fledged lab.
Nicola, you have one question in Q&A.
One question where?
In Q&A.
Sorry. Okay, so just a quick question. How would it be different from interactive tracks at Track? This is for you, Philip.
Yes. Yeah. So we are not actually interested in the real interactions on the platforms at first hand, but we would like to have the opportunity to implement your algorithms into the portal systems, which means, so therefore we build up this Docker-based infrastructure where you can send us your running or pre-computed systems in form of a Docker container, which we run on their platforms of the National Library of Medicine, for example. So this is more or less related to the newsreel or the Living Lab for AR scenarios from the previous years.
Thanks. There is also another question. Thank you for your talk. Do you also support real-time query monitoring?
Not in the first iteration.
But is it relevant to your scenario in the future, maybe?
Yeah. So this is a very interesting aspect. So this would be something what we would like to know more about. So what are your requirements for this? So we are open to pick up these ideas and maybe have them implemented for next year's evaluation round. Yeah, perfect. That's the spirit.
So because Amit says it's because we can do real-time data collection for user queries. So I take this as a volunteering thing, and he may send a position paper for Lilas to discuss this.
And here we are. Amit, I'm going to contact you.
Thank you so much, Philip. And let's move to the next speaker, Martin Pottast, who will talk about PAN.
Hello, can you hear me?
Yes.
Great, then let me quickly share my screen. I hope you can see the slides now.
Yes, perfect.
All right, thank you. My name is Martin Pottast. I'm with the University of Leipzig, and I'm part of not only a large, but also a great team of people who are all working on the same subject, more or less, or the same domain of subjects relating to questions of the style of text, stylometry, and digital text forensics. And we've been running PAN now for a couple of years, and I want to give you a bit of a background on what PAN is and what kinds of tasks we are interested in. So as you can see, we've been running since 2009 in several ways, shared tasks, and we have organized these shared tasks in 3 dimensions, one might say, or 3 topic groups, which can be seen as swim lanes here. And the first one is about the originality of text. We asked the question, is a text an original? Is it written by the author who claims to have written the text? And applications of this are rather obvious. One is given right here, plagiarism detection, or basically ensuring the academic integrity of scholarly work, but also copyright enforcement. So given that we maybe have a text which has actually been written by one author, we might ask further the question, and this is the biggest swim lane relating to authorship now, who is the author of a text? And of course, one might look at metadata of the actual file. One might look at the author who's written at the top or at the bottom of the document. But we are very much interested in figuring out who is the author of the text just based on the text itself, namely the style of the text. So what are the unique text markers that may be identifying an author? This is not a task that we invented. This is a very old task, has been studied actually since the 19th century. And applications of technology in this regard that might solve this task are found in forensic linguistics and literary research. A little bit more broader than just asking who is the specific author of a text, we might also ask what is the profile of the author? What are the traits of the author, or to which group of people the author belongs? And this is then grouped into the author profiling swim lane here. And here we not only have forensics applications, but also applications in marketing. And basically also, and in both cases, in identification and profiling, we ask the psycholinguistic question whether the psyche, basically the personality of an author in one way or another, can be found in his or her writing. This question is not altogether solved yet, although, as I said, for more than 100 of years, people have been toiling away at this problem, and for the past 30 years also in computer science. It is not very clear where the style in a text can be found and what are the specific markers and how are they related to what we usually want to avoid, namely topic. As a counter to all of these tasks, we also study the obfuscation of text, which is not an analysis problem anymore, but a synthesis problem. And here we want to rewrite a text, paraphrase it, only changing the style of the text in order to basically find out whether a computer, or also maybe a human, although we are more focused on text generation by computers, is capable of undoing all the analysis technology that has been developed throughout the decades. There has been much less focus on obfuscation as of yet. And a little bit further afield, we are also studying whether the writing style of text can be exploited in order to study problems relating to computational ethics. For example, here we study whether a text has been vandalized on Wikipedia. We study whether some news is hyper-partisan, so meaning it's extremely left or extremely right-oriented. Or also we look at whether some piece of news is fake, or whether some person on Twitter spreads fake news, as we shall see in the tasks that I'm going to show you. So there have been a lot of tasks that we have been organizing throughout the years, and I'm not going to read all of them to you. You see there are quite a number. But I would like to rather switch to another window showing basically the webpage of the conference. I hope you can see the webpage now. My browser. Nicola, can you verify?
It is okay.
Okay, great. So on this webpage, we organize now all our shared tasks, and they are maybe a little bit better organized than on the graphics that you saw before, and you can now easily filter for the ones that run in 2020. And I want to quickly run you through what are the basic tasks that we show. Okay, here we go. Authorship verification. The basic task is, given two texts, determine if they are written by the same author. This is at the core of the authorship identification problem. And we just ask, have the two texts been written by the same author? It's not even necessary to know who the authors were. I'm not going into many details here, but we came up with a 3-year guide for this task, or 3-year research agenda for this task, which studies the problem in different and interesting and new settings which have not been studied before. You can learn more on the webpage at pan.webis.de. The next task is profiling fake news spreaders on Twitter, which is sponsored by Symanto. And here the task is, given the Twitter feed of a person, determine whether its author is keen to be a spreader of fake news, as opposed to not being a spreader of fake news. And here, Paolo and Francisco and their students, they have assembled a multilingual data set, which will allow to study the problem in Spanish and English. And even an award will be given out by Symanto in 300 euros to the winning team. In the celebrity profiling task, we also look at Twitter feeds and want to find out whether an author can be profiled by his followers. Looking just at the followers of an author, we want to find out whether the traits of the author himself can be determined. And the final task is the style change detection task. And here we ask the question whether two consecutive paragraphs have been written by the same author. Here we look specifically at multi-author documents, and we want to find out where the author changes in the text. So this has been a very quick overview of PAN and the tasks we are running this year. And I'm running out of time, so I'm wrapping up very quickly. not only have we organized the shared task, we have also organized the data that we've been compiling throughout the years. You can see the table is a bit longer than the shared task table itself. And you can find now all data sets also on Zenodo just by clicking here on the Z link. So this is very quick, an overview of PAN, and I hope you can still now consider to participate. Thank you very much. Oh, I can't hear you, Nicola.
Okay, now. Thank you very much, Martin. Any questions for Martin? Okay, so it seems we are done. Thank you. And we can move to the next speaker, Alexander Bondarenko, and we'll talk about Touché, a new lab starting this year.
Yeah, hello. Martin, you need to unshare your screen.
Nicola assigns it to you, or do I have to do it?
Nicola? Oh, yeah. Okay, nice. Right. So I hope you can see my screen now.
Yeah.
Very nice. So thank you, Nicola, for the introduction. Hello, everybody. Alexander Bondarenko. There is a French exclamation one sometimes uses when an argument has touched us to the extent that we may change our mind. And we'll use that to refer to our lab, Touché. We are a group of experts in retrieval, natural language processing, and argumentation, having worked in either of these subjects for years. And we hope you will consider participating or spread the word. At CLEF last year, we saw a brilliant keynote by Bruce Croft, and he presented this slide right at the beginning of his talk. It gives the overview of how the field of answer retrieval has been developing over the time, starting from the passage retrieval and up to the complex answer retrieval within today's focus on conversational search. As you can see, there is still some free space at the bottom left, indicating that some room for future developments. And we believe that the next key component to conversational agents is already on the horizon. Natural language processing, argument retrieval has been a thriving research field for years now. And we believe that argumentation will be and becoming a key component in conversational agents. Therefore, we need to study argument retrieval. So we are motivated by the decision-making processes which come eventually to the point where one side will challenge with the other side with a why question, which is prompt to justify one's stance. For CLEF 2020, we organized the first lab on argument retrieval featuring 2 tasks. The goal of the first task is to support users who search for arguments to be used in conversation. For example, getting an overview of pros and cons, or just looking for arguments in line with the user stance. Given a query on a controversial topic, the task is to retrieve relevant arguments from a focused scroll, from the focused scroll of online debate portals. And the goal of the second task is to support users facing some choice problem from everyday life. Given a comparative question, the task is to retrieve and run documents from the CLEF Web 12 that help to answer the comparative questions with arguments and help the user make an informed decision. So we will encourage our participants to use Tira for their submissions to allow for a better reproducibility. Tira is currently one of the few platforms that support software submission with little extra effort. So I hope that I was able to convince you that the argument retrieval is a worthwhile subject to study. And now let me give you some more details about the Touché shared task. So we have created 50 topics for each task, which reflect real users' information needs, where title represents a search query as it would be used by a human. Description serves to provide more details on the particular search scenario, and narrative aims to provide insights to the human assessors about the document relevance. Similarly, the topics for the second task follow the same structure, but now they reflect comparative information need. One of the core components of the shared task is evaluation, and it is quite common in information retrieval to manually judge retrieved documents based on their relevance to a search query. Argument retrieval, however, requires some additional evaluation dimensions to answer the questions, how good are the arguments? But still, relevance is surely important for argument retrieval. In 2017, Waxmont et al. Published a survey on more than 10 different argument quality dimensions. We selected 3 of them, which are important in the settings of the conversational argumentation in our first task. The retrieved arguments should be logically cogent, rhetorically well written, and contribute to a stance building. And for comparative argument retrieval, which reflects a choice problem, to justify one's opinion, it is important that arguments provide sufficient support and come from credible sources. So now, when we know the settings of the 2 shared tasks, let me show you very short statistics about the lab. So far, we have received 25 valid registration. The majority of the registrations come from Germany, but there are several registered teams from other European countries and also from Asia and from the United States. And if you feel at this point that your country is underrepresented, consider participating or spread the word. Thank you very much.
Thank you very much to you, Alexander, for the super compact presentation. Any questions for Alexander? Okay, so hopefully people will join to share. And the last but not least speaker of the day is Alexis Joly, and they will talk about CLEF.
So hello everybody, sharing my screen. Okay. Oops.
This is a bit of overlay.
Yes, seems so. Right, here it is, sorry. Is it okay?
Yeah.
Thank you. So my name is Alexis Joly. I'm from INRIA in France. And so I'm going to present the 6th edition of CLEF. And so this is a joint work with all these colleagues, mainly from Europe and the US. So the motivation of the lab is that biodiversity is playing a crucial role for the equilibrium of the planets and also for human food safety and health. And I give here 2 examples of recent articles about the subject, but you can find many of them showing that we urgently need a better knowledge and a better management of biodiversity. In this context, IT and AI technologies have really a role to play and can help in this regard. And CLEF tries to evaluate such technologies, and around 4 main tasks this year. So 1 on plant image identification, 1 on audio bird species identification, 1 on the prediction of species based on their environments, and 1 about snake identification. And I'm going to give a little bit more details about the tasks. So starting with the plant CLEF task, so which is the oldest one. It even started before CLEF in the context of image CLEF in 2011. And along the years, we increased the number of species and the difficulty of the task, and as the performance were increasing. And last year in particular, we were focusing on the species that are the less represented in the data, which are mainly tropical floras with the highest biodiversity, but also the least data. And since performance are still very low on this species in the long tail of the distribution, this year we try to identify them using different kind of data, which are herbarium sheets. So these are dried specimens in museums and collections. And so this is a cross-domain plant identification task, meaning that the training data is this dried and pressed specimens, but still the test set is some classical plant pictures in the field. And so the task is evaluating that. Okay, so regarding the bird task, so the scenario is to identify all the species that are singing in audio soundscapes, meaning that you have some device that are recording all what is happening in the neighborhood. And so to do that, we have the big training set of bird sounds, which comes from the Xenocanto Citizen Science Initiative, the largest in this regard. And we have about 1,000 species in this training set, and the test data mainly comes 4 recording sites in the US, in Peru, and in Germany. And so some of them are very intensive acoustic scenes, meaning that many birds can sing together, up to 8 species, and sometimes even more individuals, which makes it a very challenging task. And so the rules is that you only should train on the monospecies recording. And so we also provide some soundscapes for validation, but that should not be used for training because we could not have such data for all species. And also this year, we forbid the use of model ensembles to really focus on the methods themselves and the network architecture and so on in particular. We are open to input from participants, but they have to indicate that in the run metadata. Now, so let's move to the GeoLifeClef task. So here the goal is to predict all the species that could be observed in a given environment, so at a given locations. So based on the location of the site, but also on a lot of covariates describing the environment of this site. And in particular, high resolution covariates, so either satellite images or altitude rasters or soil occupation information. And this is the first time that such remote sensing imagery and high resolution environmental covariates are paired with species observation. And and we do that at a very large scale with 2 million species occurrences from PlantNet and iNaturalist. And so the data is split in a training and a test set according to some spatial blocks on the spatial grids. And for the metric, we use a variant of classical accuracy, which is an adaptive set-valued evaluation matrix. So you can find more information about that on the task and the challenge description. And so the last task is about snakes. So this is the first year we have this task in LifeClef. And so the goal is simply to identify the snake, the species of the snake in a given image. But this is the first time we do that on a so large scale. So with 783 species of snakes and 245,000 images coming from a lot of variety of sources that have been aggregated by Geneva University, who is organizing this. So, and that's it. I really thank a lot all the organizers of this test. This is a very huge work to collect all this massive data that are used in the challenge. And so that's it. Here are some logos. that are financing the challenge. Thank you.
Thank you very much, Alexis. Any questions for Alexis? Oh. Is it possible? Yes, Stefan, good question. Is it still possible to participate? Alexis, can you turn unshare your screen, please?
Yes, if I find where.
From the Zoom page. Okay. Okay.
I did.
Great. So let me go here. You should see these are the main dates for CLEF this year. The registration to the activities, to the labs is still open until late April, which means that you can ask for participating, and the evaluation cycle will run until early June. So there is still time to participate, and from when you register to when you have to deliver your work, there is enough time. And by mid-July is expected your paper about your participation. So as you see, you have the possibility to take part in the CLEF activities for this cycle. I would really like to thank a lot all of you for participating in the session, and for and the ECIR 2020 organizers for making this event possible online. They are our pioneers. As you heard, also we as CLEF have decided to go for an online event only in September, so we will really build on their experience and advice. So thank you very much to everybody, and I think now it's lunch break. I don't know, Joao, if you have any advertisement to say.
So now is the lunch break. We're going to start at 2 p.m. with Jamie's talk. And during lunch break, I suggest you to go to Slack and talk to sponsors and to other people that are there. They are keen on having one-to-one conversations with you. Okay, so sponsors are keen on that. So thank you very much to all of you, and hope to see you after lunch here for Jamie's talk.
Okay.
Thank you.
Thank you. Goodbye to everybody.
Thank you.
I'm going to change to session B.
Thank you.
Jamie.
Yes, hi.
Hi, Jamie.
How are you?
Fine. Hey there.
Jimmy.
Morning
Pablo.
or afternoon, Pablo.
To see you.
All right, I'm going to share my desktop.
I'll be in the background. Just one thing, Joao. If everything goes as planned, maybe some people from the award announcements are going to show up already. So if I see them, I will let you know so that we can upgrade them to panelists in advance, because there is no break between the keynote and the awards.
Fine. That's fine. So
I'll be taking care of that. In the meantime, I'll be in the background.
okay. Okay.
Yeah, actually, Joe, I'm starting to see people. So maybe you can give me temporarily the host.
Pablo, can we talk a little bit of?
Sure. Sure.
Oh, okay. Okay. All right.
Hello. Hello.
Hi.
How are you?
Good. How are you?
Good, thanks. Joao, we can't hear you if you are talking.
No, I'm talking to Pablo.
Oh, okay.
Two conversations at once.
Too many.
Hello, hello.
Hello.
I'm going to.
Hello.
Hello.
Hello, Maricela. Welcome you all. So,
Hi, Dia. Hi, Maricela.
Hello.
So as you know, we're going to have Jamie's keynote first, and then right after that, we will go for the award-winning announcements. So this is why you can, we enabled your web camera just to be ready when Jamie is finished. So you can be there. You can turn off your camera if you want anytime until the time comes that you make the announcement.
Jamie?
Yes?
Jamie, so the other panelists are here because the next session is immediately after, and it's the award ceremony.
Okay, that's fine. So when we're done, if there's time for questions, will someone be responsible for unmuting people and letting them talk, or how's that going to work?
Yeah, I will handle that for you, Jamie.
Great,
no
thanks.
Okay. I will mute and then mute, but
okay.
Emil will be talking to you. Okay, so and if there are no hands raised with questions to be asked, so Emin will read some of the questions for you.
Okay.
Okay.
The questions can be asked in two ways. One is raising hand, one is Q&A at the bottom.
Okay.
And yeah, I'll help with that.
Great, thank you.
Hi. Just wanted to check my microphone for later.
It works.
Great, thanks.
Hi, Nicola. So your hand is raised. So
yeah, it was just to check that everything is okay.
Okay, good. So I think we are all here. Everyone's here now.
I'm going to go refill my tea. I'll be back in just a moment.
Sure.
Anna, can you turn on your camera for 1 second just to make sure that it works?
Yeah, sure.
Ah, great. Thanks.
How did you make to have that background?
It's easy. Sometimes. Okay. Jomon has arrived.
Okay. Let's get rid of email.
Pablo, Joe. Hi, Emily.
Hi, Jomon.
How did the morning go?
Everything was fine. Yeah, everything went quite well. So
the other section, I was in the play reproducibility track. It was very good. Hi, Jamie.
Hi.
Is that good morning for you?
Yes. Good afternoon for you.
Yeah.
Excuse me, a printer is just going off.
Right. So this goes up until 3:30, right? Including
no.
awards?
Including the awards.
Yeah.
Let's see.
Steven is around.
Jomon, can I talk to you on WhatsApp?
Right. Okay.
Or by email? By email.
Okay.
Okay.
Could you promote Steve to panelist? He's just raised his hand.
Wait a minute. I'm going to take care of that.
Pablo?
Yes.
Yeah. Can we talk, or how do we do?
Yeah. Let me do one thing. 1 second.
Can you? Oh well. Well, yeah, there's not much we can do.
Oh yeah, no, it's okay, Joe. It's
Yeah,
okay.
so we...
Yeah. Trust me, it's okay.
Yeah. Jamie, sorry. It was supposed to be like surprise for everyone.
Sorry?
No, it still is.
It still is. Yes.
Yeah.
Okay, thank you very much. I'll mute myself now, but good to see everybody. Hi, Jamie.
Hey, how are you, Steve?
Good.
Good to hear your voice.
Hey, Steve.
Yeah.
Hi, Steve.
Hi.
Hi, Steve. Hi.
Hi. I'll switch myself off now till the award ceremony.
Very good.
Joe, did you send me an email?
No.
You can Skype me also, Jenny.
I don't have more computers to use microphones and cameras.
One of every app.
Yeah.
Okay, shall we get started?
Fine with me.
Okay, great. So before we start, just a few announcements. One is, as many of you know, there will be a award ceremony right after this, and there is no break in between. So if there is anyone who is involved in handing in an award, if they could please raise their hand, they will be promoted to panelists so that they can present the award later on. And for authors, any one of you could be the winner. So please be ready during the award ceremony. And if you did get the award, you will be promoted to panelists as well, so everyone can see your face. And if you want to do something interesting, like wear an interesting pajama or an interesting hat, you are welcome to do that as well. Okay, with that, I think we can start the third keynote of ECIR 2020. So it's a pleasure and actually more an honor to introduce Professor Jamie Callan, who is a professor at the Language Technologies Institute at the Computer Science Department of Carnegie Mellon University. So Jamie's work doesn't need any introduction to many of you. He has done a lot of work that have had very big impact in the community. So I'm sure most of you have either read a paper by him or at least cited a paper by him. But in general, his work covers a broad range of areas, including search engine architectures, neural search, conversational IR, use of semi-structured knowledge for search, large-scale distributed search, among many others. So today he will be talking about some of the recent research activities he's been leading at CMU's Language Technologies Institute. And in particular, the talk he will be giving is actually quite complementary to the lecture we have had yesterday, the Karen Sparks Award lecture. And today he will be talking about better representations for search tasks. So with that, I won't be taking more of your time. I'll let you enjoy Jamie's talk. Thanks, Jamie.
Thank you. All right, let's get the screen shared here. Okay, hopefully you're all seeing the presentation now. Yeah. So thank you. It's a pleasure to be talking with you today. Let's go ahead and get started. There we go. So I've been doing IR research for quite a while, almost 30 years, which is kind of amazing. And I started out working on inference networks, the inquiry system in the beginning. And over the years, I've worked on a wide range of topics. And during this time, I would say my career has spanned several waves of innovation in this field. I list some of them here. I won't read them all. I've worked on many of these topics, although not all of them, and many of you have as well. One of the things I'll point out is the first wave of neural networks research done in the 80s and 90s, which were a very inspiring and interesting group of systems. They gave amazing demos, but they really weren't competitive in environments like Trek or in most commercial settings. But now we're in the middle of another wave of neural research. And these are things, I don't need to read all of this, but these are things that probably most of you are familiar with now. Word embeddings, backpropagation, which actually was a technique developed when I was a grad student, continuous representations. And these new models are winners at Trek. They dominate the Marco leaderboard, and they've shown in research presentations at SIG-IR, here at ECIR, other venues, that they're really quite competitive with the older models that we have. So to me, this wave of innovation feels different than some of the other waves that I've seen over the last 30 years. Much of this innovation in IR right now, I would say, is being driven from outside of our community. It's being driven by the machine learning and natural language processing communities. And IR has been reacting to developments in these other communities rather than leading. And some of that's to be expected. Neural was late to come into the IR field compared to some of our other language technologies colleagues because it just didn't work as well for a long time. Now that it is, we're all scrambling to catch up and really understand this new technology. Also during this wave, the boundary between IR and NLP is much less clear than it has been in the past. I've been teaching information retrieval for years, and I often could draw a fairly clear line between what I considered IR, which is shallow language understanding, and what I considered to be NLP, which is a deeper or more detailed language understanding. But now NLP has adopted many of the techniques that we considered IR techniques, statistical representations and similarity, and the boundary between these two fields is less clear. So it makes me think of a talk that Ed Hovey gave almost 20 years ago at CLEF 2001. He was a keynote speaker there. And if you've ever seen a talk of Ed's, he often starts with an outrageous claim. So this was his outrageous claim of the day. He said, IR is over, a victim of its own success and of its limitations. And I thought this was a great talk. I really liked this talk. Ed is a good friend of mine. His office is just across the hall from mine, and I've used this slide with his permission. What I really liked about this talk is that at the time, web search engines were emerging as a major cultural force. And the IR community felt pretty proud of itself. We had just taken over the world. We had taken a technology that was important to specialists, and now your grandmother was using it, and everybody was using it. So we felt pretty good about ourselves. And here's this outsider coming in and telling us, yeah, but you're done. And he was very nice about it, as Ed always is. He said, thank you for the web search engines. Those are amazing, but what will you do next? And so he focused in his talk on the inherent limitations of discrete term matching, which has been the foundation of our field for a long time. The word cat matches the word cat. It doesn't match the word kitten. And he focused in his talk on better understanding of text. So he talked about semantics, which has always been important to Ed. He talked about concept signatures, recognizing the same concept in its many different guises when it's represented slightly differently. And he talked about machine reading, pouring large amounts of text through NLP systems to build knowledge bases and better understanding of semantics. And what else do I want to say about this? I want to say when he talked about discrete term matching, he wasn't just focused on ad hoc search, which is what we often think of, but he also focused on the limitations of the question answering systems and extractive summarization systems of that time, which also use discrete term matching. If you go back and look at that talk, some of the details turned out wrong, as they will in an old talk, but actually a lot of what he was saying still is relevant today. And so with that in mind, this seems to me like a good time to be thinking about what distinguishes IR from other fields. What are our strengths? And we have a number of them. One of them, of course, is scale. We're known for that. That's probably how many of the other language technologies think of us. Big data, go fast, right? And we don't focus a lot on that in our conferences, but it is something that really distinguishes our field and is fundamental for us. Another is that we're very good at modeling. We build shallow and flexible models of text, and those models are very robust and very effective. They've been very hard to beat. And we're often embarrassed about our shallow models, but they are very flexible and robust. We're very good at modeling the corpus. Really, that's the roots of our field in taxonomy building, building ontologies, understanding a document or piece of text within a broader context. And we build models of tasks and users. Sometimes these models aren't as rich as they might be, but that's something that, again, is really in the roots of our field. We understand our task very well, the kinds of things that people do, and well, I would say we're not great at user modeling. A few people are, but the large search companies are probably very good at modeling tasks and users, at least at the population scale. They know common tasks that people like to accomplish. They know the documents that satisfy the typical user in different subject areas. And finally, our success criteria, I would argue, is really unique to our field. It's all about making someone happy, right? We're really one of the only computer science technologies I can think of that takes this view. Most of the other areas of computer science say, if you give the user what they asked for, you've done a good job, you were successful. And we don't do that. We say if the person formed a bad query and you gave them a bad result in response, exactly what they asked for, it's the system's fault, not the user's fault. And I think that's something that we don't give ourselves enough credit for. The founders of our field did a really good job in establishing that as a criteria. And I would say all of these are core strengths for our field, and we don't always recognize or build upon that. So what I'm going to do today is talk about some of our recent work at CMU on better text understanding. I'm going to talk about a neural model that learns search vocabulary patterns, one that is better at estimating term importance, and then I'm going to talk about a task that requires understanding the search context. The goal in this talk, we'll see how well it works, but the goal is new tools, but essential IR problems. I really want to focus on things that I think are unique IR issues, and talk about how we apply neural techniques to these or other opportunities in this wave of new innovation. So that's the plan. Let's get started. So understanding search vocabulary patterns. A lot of the recent innovation in our field is based on large-scale corpus analysis, often larger scale than we can easily accomplish in our own research labs or in small organizations. And so often we wind up using language models or models in general that have been developed by other people. Examples of this include Word2Vec and BERT, but there's many of them. I'm sure you're all familiar with them. And so the result of this is that we get a large task-neutral language model of language usage. And this shows an example. This is a fairly typical example of Word2Vec. I've got 4 words here, and for each of them, I show the top 5 or 6 words from the English news, Google English news corpus. So for Apple, I get a bunch of fruit words because they all tend to be used in similar contexts. For pie, I get a bunch of dessert terms because they're used in similar contexts. For cat, I get a bunch of dog and cat terms, and for men's, I get a bunch of gender terms. So this is not new to most people. But some of these similarities don't match search expectations. So if I put in a query for men's shoes, I really don't want to get back web pages that are about women's shoes. And if I put in cat videos, I'm really not interested in dog videos. Some people are interested in both, but I'm not. I'm not a dog person, I'm a cat person. And so these are areas where the language models that are built from large-scale corpus analysis don't always match our tasks. So this is some work that we did 3 years ago. Some of you have probably seen it, and so I won't spend a lot of time on it. This is a system called KNRM that uses relevance signals to update word embeddings. So we start off with generic Word2Vec embeddings here. So this is the 300-dimensional embedding for the first query term, the second query term, the last query term. And then I also have the embeddings of the document term. So there's the first document term, the second document term, and so on. I'm going to compare every query term to every document term. So that gives me a similarity matrix or a translation layer that says how well each query term matches all of the document terms. Those get pushed through a network that has a Gaussian layer and some pooling layers. And at the end, I get a final ranking score that says how well this query matched this document. Now, what's interesting about this architecture is that it's end-to-end. And so if I have relevance data, I know, for example, that this document is relevant to this query, then I can take the relevance signal here, I can push it back through the network and tune or adjust the embeddings for my search task, resulting in somewhat different embeddings than I had from Word2Vec. And if we do that using a large search log, we find that many pairs become less similar. So for example, wife and husband get pushed apart, which is good because if I'm searching for gifts for my wife, I'm not interested in pages about gifts for your husband. It also discovers new soft matches. You can see some terms that are pushed closer together. This was trained at a time when the Malaysian airliner had gone missing, and so we see a similarity between the airline ID and the term search. We see the common router address and the word router, and so it's learning some similarities that are probably useful for search. And in fact, more than 50% of the word pair similarities change enough to affect search. So we wind up with a model that's really tuned for our task rather than for the original large text corpus that it was developed from. It also learns patterns that we might not expect. So in particular, it learns term site preferences. So for example, it learns that the word cancer is similar to the site name Medline Plus, and that integrals is similar to Khan Academy. That's probably something we didn't expect. And it learns that because at many websites, the HTML title is a concatenation of the site name, a colon, or some other separator, and then the title of that page. So our model just sees a bunch of text and it learns these similarities. Now, these are helpful to the search engine. They improve retrieval quite a bit, actually more than we might have expected, but they're not necessarily the behavior we expected from our language model, and they might not even be what we want. We might really want to separate out the site preferences from the word similarities that we were expecting the model to learn. And so my point here is that, I mean, we all know that task-specific tuning of general models for a particular task improves accuracy. That's a recurring theme in recent research, and I think probably none of us are surprised by that. but I think it points to some important open questions for our field. One of them is, how should search-specific tuning be done? And I think we don't really have a robust methodology for that. We have a bunch of positive examples. I can look at a bunch of research papers and see where people have done it successfully, but we don't really have a good off-the-shelf methodology for this. In fact, a common experience in my lab, and I expect in many of yours, is that a new student joins my group. I hand them a recent paper. I say, go reproduce this result. I'd like to learn more about how it works. And they go off and spend way more time working on that than I expected. And part of it is that they're inexperienced, but another part is that there are really important details about how that model was trained that are either not in the paper or that are given very little attention in the paper. And I don't think anybody's hiding anything. I think it's that the authors of the paper don't necessarily know what's important to the success of their model. And that's a common theme. You know, we are trying to beat BM25 or some other strong baseline by 15 or 20%. We get that result, we go, yay, we win. We publish our paper and we move on to the next problem. We don't really dig into the causes of those wins. And as I said, you know, usually we don't know what search-specific tuning is teaching the model. Often we don't even really look for that. If you go back and read our KNRM paper, it doesn't mention this, this term-site relationship. And that's because it's something we discovered later when we were applying the model to a somewhat different problem. And it's tough to get papers published on something like that. It's just, it's a small result in a way. And so it's something we know, but other people probably don't know about our model. And I expect that that's true across our field. So I would say that this is an understudied topic, taking models and tuning them for particular tasks and understanding what they're really learning for those tasks. And if our goal is to have really robust off-the-shelf systems like we've had for many years, we really need much better understanding of what's going on under the hood in these systems. The second topic I want to talk about is understanding the text. So we have a long history of shallow text understanding, and it operates essentially as shown here on this slide. We represent objects, information objects, documents mostly, by index terms, and we organize different concepts under the same index term to improve robustness or reduce the vocabulary mismatch between the query and the document. So we do things like organizing related concepts under the same term using case folding and morphology. We'll drop unimportant concepts. And we mostly ignore text structure, intentionally, I would say, ignore text structure and organize the terms into a bag of words. Now, there are some things we know are important. So distance is important, and many of our systems include distance in some form. Maybe we have n-grams, or we have phrase operators, or we have window operators. We know that those really improve accuracy. And although it's not included on the slide here, we also make use of document structure by paying attention to the source of a term. So terms from different fields may be weighted differently, or terms that are related to a document in different ways may be organized into different bags of words and given different attention. We also focus on term importance, although usually we organize that in the retrieval model. Usually that's represented as some kind of a term importance weight that's based on frequency. And this model of shallow text understanding has been effective for a surprisingly long time. This basic model has been sort of the state of the art in our field. Well, I shouldn't say state of the art. I should say widely used in our field for almost 50 years, which is really an amazing accomplishment. But these older models are becoming uncompetitive. And so one of the things that we've gotten interested in is whether they can be updated to remain competitive. One of the lessons that my generation learned from the first wave of neural network research is that those older models could do some really interesting things. But the more we understood what they could do, we were able to find a way to do those same things in simpler models and in a way that was more predictable or easy to control. And so I'm interested in that same thing. Can we update our older models to be competitive or at least useful in this neural era? So many of us have been working with BERT re-rankers over the last couple of years. They've had an enormous impact on our field. Typically, there's an initial ranking based on BM25 or INDRI, and then you re-rank the top end documents using BERT. Over on the side here, I've got an architecture for a standard BERT re-ranker. This diagram comes from Devlin et al. And so what we've got is a set of tokens here from the query. So these will be embeddings using Word2Vec or some other form of embedding. We have document embeddings for document token embeddings here as well. We also have embeddings for positions and segments. So these indicate that these terms are the query so that the model knows which terms are query terms in documents. We have the document embeddings here, and we have position embeddings so that the model can learn where words are in the query and where they are in the document. So we feed these in through a bunch of layers. These are transformer layers that are building new representations of each token, and attention matrices are controlling what evidence is used at each layer. And then at the final layer, we have a multi-level perceptron that's going to map these signals to a probability of relevance or a relevance label. This is a fairly standard architecture that people have been using recently. And I don't really want to go into details on the architecture itself. Instead, I want to make a couple of points about using it. So one is that text representation still matters in this world. We often act like it doesn't. The hype here is tokens are raw text strings, and this is taking raw text strings and producing signals out of the end. And that's true, but we do some other things, right? We divide the documents into passages. We do that because it reduces the computational cost, and it also improves effectiveness. We add the title to each passage, because when we take a document and split it into passages, we often lose the global context. It becomes less clear what each passage means. So by adding the title, it adds some brief document level context to each of these passages, which improves results. We also do things like tuning with a large search log. That gives us effects similar to KNRM, pushing husband and wife farther apart, pushing dogs and cats farther apart, so that we get the kind of behavior that's going to be important for search tasks. And then finally, at the end, we'll train this for a specific data set for CLEWeb or Robust, or pick your favorite data set. And this is a small amount of training data. Primarily, that's affecting this last layer here, right? So the search log, that's affecting our model. And then our small amount of relevance data is really used at the very end. So this is something that we don't always really think about how we're taking this model and adapting it to our task, and especially the representation of the text that's going in. So I think BERT re-rankers have a reputation as making better use of all of the text, and I think that's true. How are they doing it? We have continuous soft match among the query and document terms, so we can recognize that cat is similar to kitten. The model isn't sort of inherently sequential, so we get things like n-grams for varying n that's built into the model, which is nice. And we also have better understanding of the importance of each term in context, which is also nice. The representation of this token depends on the tokens that are around it, and so we just get better models of what everything means. These are also better with long queries that have mixed term quality. That's something we often don't see in IR. So over here, I've got the Robusto 4 data set, and I've got the 3 types of queries that we often get with that: title, description, and narrative. You can see the average lengths of each type of query. Sequential dependency models, which were a very competitive model for a long time in our field. You can see the accuracy here. It goes down as the query gets longer. Coordinate descent, which is a pretty good learning to rank system. So this would have been state of the art 4 or 5 years ago. You can see that it's actually pretty consistent with queries of different length. So this is an advance for our field. We got better at dealing with these queries that had a bunch of terms that we always viewed as junky, but at least our system got better at ignoring the junky terms. With BERT and using the best passage as the score of the document, we're able to get a significant improvement with the description queries. And the narrative queries also are better than title. Not dramatically better, but better. And this is an unusual result. We really haven't seen very many papers in our field that say long queries makes retrieval more effective. When I joined the field quite a while ago, that was something we thought we knew. Coming out of the Boolean era and the structured query era, I think we felt like long queries generally lead to better retrieval performance. And then over the last 20 years, that hasn't been consistently true. I think with BERT, we see that there's an opportunity here again. Our models are still not doing as well as they could with the long queries which have abstract descriptions of relevance and other information that's harder to use. But we see an improvement, and I think there's an opportunity here to make better use of long descriptions of information needs than we've had in the past. So I think actually this is an exciting result about how more sophisticated text understanding is used in our systems. BERT shows that frequency signals are no longer enough for understanding the importance of each term in a passage or a text. So here I have two passages that both contain the word stomach twice. Here we have a passage that is about upset stomachs. This is a passage about how our bodies acquire energy. Stomach occurs in this as well, but it's more of an incidental concept. The color coding shows which terms BERT thinks are more important in each of these passages. And you can see that it's doing a better job of recognizing which terms are more central or more descriptive or important in these passages. So in the DeepCT system that Julian Dai, one of the grad students in my lab, developed, the goal is to take this better text understanding and in a way retrofit that or put that back into our older models, use this information to make the older models more effective. So we'll train a BERT re-ranker as before, and then train a model to map token embeddings to importance scores. So given a token T and passage P, how important is it? And we'll just have a simple model. We'll take the token representation of that token in this passage, we'll multiply it by a weight vector and add a bias term, and that will give us our score. And then we'll just train the model using standard maximum mean squared error loss here. So this is a fairly simple model. Now this is interesting because we don't usually think about how important is this word in this document. We don't have those kinds of signals usually. What we know is that this document is relevant. So how do we know which words are really essential to that model of relevance? So we train this model in a couple of ways. We can do it in a supervised fashion or an unsupervised fashion. In a supervised fashion, we've got all of the documents that are relevant to this query. We'll look at what percentage of those documents contain this term. Terms that are in more relevant documents will be considered more central or more important. We can also do this in an unsupervised manner. We'll consider the terms in the title to be the important terms. All of the other terms are not important, and we'll train our model with that. And because BERT is learning weights based on the words around a term in context, this will propagate to other words in the passage. We'll learn not just that the title words are important, we're teaching the model how to recognize these title words, but it will also recognize other words that are important in each passage. Great, so now we have this signal about which words are important in the passage. What we'd like to do is, our goal is to retrofit or improve these older models. So what we need to do is transform these scores into integer weights that will fit into our older models. The scores tend to fall into the range of 0, 1 because they were trained with 0, 1 signals. So we'll take those scores and map them to integer scores using some heuristic method here. This is fairly simple. We could multiply the weights by 100 or by 100 and then give them the square root. So kind of flatten that curve. We can do different things here. And once we've done that, we'll just we'll truncate these to integer values. And then we'll stick these into a typical inverted index and just replace the term frequency in that index with these learned importance weights. And once we've done that, we'll just run a standard off-the-shelf ranker, BM25 or INDRI on this new index. So what we've done is we've done BERT analysis of documents, we've taken the BERT weights, transformed them into integer weights, and then just stuck them into an old retrieval model. This shows you some results. I only have 2 slides with results in this talk because it's not that kind of a talk. But here we have the index that's using DeepCT term importance weights and standard off-the-shelf BM25 ranking. We have, this is on the MS Marco data set. And so we have results for the dev set and the test set. You see the official BM25 ranking here. You see doc to query, which is another approach that uses deep analysis to update the text representation and then use BM25 for ranking. Nice work. And you can see that, so these are all old single stage rankers based on BM25, and you can see how they've done. And then we have some multi-stage rankers here that use machine learning. So you can see feature-based learning to rank, which we would have considered state-of-the-art a few years ago. You see KNRM, the system that I mentioned, the neural net system that I mentioned, and some newer models. This is a convolutional model, a version of KNRM, and some very new and more sophisticated systems. So you can see this updated index with BM25 is actually pretty competitive with these systems. It's not the best, right? Clearly, there are systems that are better than this, and you'd expect it. This is all of our latest rocket science. But updating BM25 with these new term importance weights makes a real difference. It really improves the accuracy of BM25, and we retain all of the advantages of BM25. We have discrete term matching, it's very efficient, and we can apply this in a wide range of scenarios. So better text understanding can improve older retrieval models. As I mentioned, we've also seen this in some other work recently. What we're doing is we have better text understanding leading to better term weights. And better initial retrieval also leads to better BERT re-ranking. I didn't show you that on the previous slide because I don't want to have a lot of numbers in this talk, but 3 of the top 4 Marco leaderboard systems are using DeepCT. So this is one of those cases, we always worry about whether effects are additive in information retrieval. And in this case, they are, or at least they flow downstream. If you improve your ranking at the initial stage, this improvement propagates down your pipeline and you have improvements out of your more sophisticated BERT re-ranker as well. So why is this important? I think this is important for several reasons. One is that these models are still used widely, and they're used often alone in enterprise settings or in smaller organizations that don't have the resources or the expertise to do learning to rank or more advanced neural models. But they're also used as the first stage of every re-ranking architecture that I know about. So they're still in wide use, and they're going to be for some time. So improving their accuracy, it's a big win for everybody. I think, though, one of the reasons I'm really excited about this work is that text understanding in these older retrieval models hasn't changed in a long time. It really hasn't. The state-of-the-art models in our, well, let's say close to state-of-the-art models in our field have been around for 25 years, and the text representations that they use go back much further than that. There's been quite a lot of research in our field over the years. We've all published papers on this, BM25 plus 10%, but they haven't really changed things too much. And this, I think, is an opportunity to really make big gains and in these older retrieval models. And finally, this is deep text analysis plus efficient matching with inverted indexes. So we're taking a computationally complex task and shifting it back in the pipeline to the indexing stage, moving that offline. I think that's something we often like to do to retain the efficiency of our systems. And this encourages us to explore a wider range of hybrid indexing strategies that combine deep or more complex text analysis methods with our more efficient indexing and retrieval methods. So I think there's a lot of opportunity here. I think certainly for many of us, me and many of us, I think we had just sort of gotten used to the bag of words model always winning. Well, I shouldn't say bag of words. I should say this particular style of text representation, shallow text representation, always being the state of the art for our field. And now I think we see that there are opportunities here to make large advances. And I think DeepCT is interesting work, but as I said, it's pretty simple. And I won't be surprised if over the next several years, we see a lot more attention devoted to trying to develop better term importance weights for BM25 and older rankers. All right, the last of the main sections here. So we're living in this era when text and voice-based dialogue systems have become common, virtual assistants, customer assistants, and so on. Usually these have strong models of common tasks, and they rely on extensive curated domain knowledge. And when they don't know what to do, they'll do search as a last resort, but they're often doing search on a small curated corpus, Wikipedia or something else where you can be fairly confident that they won't return poor results. But they're also becoming a common way to access search. All of us walk around with these in our pockets all of the time. Many of us have these Cortana or Google Assistant or Alexa in our homes. And we hear, and I believe, that there is less and less usage of desktop systems and laptops and other devices that have large screens. So accessing search this way works well for easy search tasks and popular information needs. So if you want to know how old Beyonce is, there's no better way to get that information than looking that up out of a knowledge graph. But for complex open domain information seeking tasks, which we all need to do on a regular basis, these are not a good way to access information. they're really poor at summarizing a large amount of information. They're poor at giving us a sense of the information landscape and how to navigate around in it. You know, we always, I can't tell you how many talks I've sat through where people are making fun of 10 blue links. But the reality is that there's often times when I'm really happy about 10 blue links. In fact, really, I'm going to look at 100 blue links, right? My goal is to learn about an area and really to come up to speed quickly in that topic area. I'm expecting to look at a lot of documents in order to understand how information is laid out, what's important in this domain, what's the important vocabulary or concepts, how things are related, and then I'll drill down into stuff. And we really can't do that with today's systems. Now, we know we can do that conversationally, right? We all do that. We sit across the table from somebody who's an expert and we have a 10-minute or 15-minute conversation with them. They help us understand the broader picture in that field or that subject, and then they guide us down to the information that we're interested in. So we know it can be done, but today's systems really don't do that very effectively. So over the last year, Jeff Dalton, Jianyan Zheng, and I have developed the TREC Conversational Assistance track. And the goal is to model someone trying to learn about a subject using one of these conversational assistants and doing a deep information seeking task. So we might start off with what is throat cancer. So imagine that someone in your family has been diagnosed with throat cancer or thinks they might have it. I don't really want just a little paragraph about this. I really want to know what's going on in this area. So the next question might be, is it treatable? Tell me about lung cancer. What are its symptoms? Can it spread to the throat? And you can see the other kinds of questions that someone might ask about this topic. So this is someone doing a complex information seeking task to come up to speed on a new area that they may not know very much about. So for the systems in the first year of the track, they needed to solve a set of problems that is listed here. They needed to deal with pronouns and implied references, context, understanding something in context, and also understanding when that context shifts. So for example, for what factors led to a breakdown of trade, you need to know what the context is there. But in some of our dialogues, in many of our dialogues, the context changes. So if your system knows that it's talking about the Stanford experiment, at some point in the conversation that changes to the BBC experiment, and the system needs to know to forget about the Stanford experiment. The typical system this year had several elements. Most of them had query rewriting to disambiguate and contextualize the queries. So is it treatable becomes, is throat cancer treatable? What is the largest becomes, what is the largest shark? Not all of the systems produced beautiful queries like this, but they had these words in their bag of words, and most of our systems don't care very much about the word order, at least initially. So just doing a simple form of query writing that looks kind of like query expansion would be enough for many of these systems. They use passage re-ranking with an off-the-shelf system, BM25, INDRI, and Serini, and then maybe BERT re-ranking or something like that on the back end. 9 of the top 10 systems use BERT or something similar to that for their re-ranking. So I'm going to take a moment and do a shameless plug here, actually 2 shameless plugs in the middle of this talk, and then I'll finish telling you about CAST. The first one is, well, it's CAST related. This track produced a reusable data set for studying conversational search. So if you're interested in conversational search, take a look at the data set. It has 30 training topics or 269 questions with shallow assessments and 50 test topics with almost 500 questions. This is a lot of questions or queries compared to most tracks in TREC for the first year. Now, due to resource constraints at NIST, only 20 of the test topics were judged, 173 questions. That's still pretty good for first year TREC track. And so there's about 300 questions that have not been judged. But this is still a good data set for studying conversational search. And it leads me to my second shameless plug, which is we're gathering TREC style assessments for all 50 of the test topics, we the track organizers. And we've designed this in a way that is that can be sort of crowdsourced or research group sourced across the research community. So we have a framework that is Mechanical Turk with known people. So for example, these could be students or other people in our lives that we know, and they're going to be the Mechanical Turk assessors. We're not going to take random people off the street. These are people that are vetted and that we know. We can train them. So the advantage here is we have Mechanical Turk as our distributed assessing infrastructure. It manages payment, it collects data, it handles all of that stuff for us. The known assessors give us higher quality assessors and lower cost. We don't have to judge everything 5 times. So that actually turns out to be an advantage for us. The shameless plug part of this is that you can help fund this effort. Because it's Mechanical Turk, it's very easy for us to pick this up and move it to your research group. If you have $1,000 or so on your one of your projects that you could devote to this, please talk to me or Jeff or Chen-Yan. We can hook you up with this. You can pay your own students to do assessing. You can pay our people to do this. But the goal is within the next month or 2 to get all of these CAST topics judged so that we have a much larger conversational data set for the community. And I think this is interesting in general as a way of collecting data. We in the community have really been reliant on TREC and NTCIR FIRE, a small number of resources to create data sets for us. And that has limited what we can develop as a community. We see other communities making big jumps by developing other more interesting resources. And I think that we could be more imaginative as a research community about how we develop data sets to push us forward. TREC is an amazing resource, but it can only do so much. And we could also do some things on our own. Okay, so back to the regular talk. So CAST is a simple model of complex information seeking. There's a lot that it doesn't have in it. For the first year, we needed to make the task something that people could do and that was reusable, that would produce a reusable data set. So we don't know anything about the person that's doing the seeking. The questions are in a static order. You can see the other restrictions here. We'd like to make that better in the future years. It's not a bad place to start, but we know we need more realistic models. Some of the things that we're contemplating for the future are shorter and more natural conversational questions. We're being guided here by what we see in the logs of real systems like Cortana. Questions can refer to previous answers from a reference system. In the first year, questions could only refer to concepts that were raised in previous questions, and we did that to make things reusable. What we're going to do this year, I think, is give everyone a reference system, a good reference system. And so a question could refer to a concept that was raised in an earlier question or in an earlier answer from the reference system. There's other things that we can do here. I won't read them all. This is an area where we really need input from the research community. What should we be focusing on? Do we need richer and more varied question types? What should those look like? One of the things that I'm especially interested in is, could we have context-based clarification questions? So imagine that your system is allowed, these dialogues tend to be about 10 questions long. So imagine that your system is allowed to ask 2 clarifying questions. So in this dialogue, as you're looking at each question, you need to predict how well your system will do on that. We already have query difficulty prediction, so we could imagine doing that. And then if it thinks it's going to do poorly, it can ask a clarification question to improve what it knows about this question. Now, we don't really have that history or that experimental methodology in our field, but these are the kinds of things that we might be able to do in this setting. We also don't really have the metrics for evaluating these things. So imagine that I have 2 systems. They both get 0.8, so their scores are the same based on some accuracy metric, but one of them asks fewer questions. It's able to do the task more on its own. How would we reflect that in our metrics? We don't really know. So I think that there are a lot of opportunities here over the next couple of years to build richer and more realistic models of conversational search, and we as a community should be working on that. Now, I'm here talking about that. Certainly, I'm not the first, or we 3 are not the first to recognize the importance of conversational search. Nick Belkin has been arguing for years that search is a dialogue between a person and a system. And I would argue that most of us haven't really made very good use of this insight. In the conversational world, in conversational search, that conversation is just explicit. And I think that it may be easier for most of us to see how we can make use of that insight to produce better systems. There are also, I just want to give a shout out to other people or other forums where this has been discussed. So there's been a bunch of workshops over the years. And here at the conference tomorrow, there's a panel on conversational search. So people interested in this topic should go listen to that panel. So I would argue that the reason we should be focused on conversational search is that it requires capabilities that are our strengths. And so I list a bunch of them here: ad hoc search, All of these systems require good ranking, corpus modeling, task models, user models. We talk a lot about task models and user models in our field, but I would argue that not all of us really take that seriously. It's something that a small number of our researchers look at, people like Diane Kelly and Rob Capra and other people, but most of us really don't do very much with that. And it's something that we know is important at the large companies where they have large amounts of data to analyze. This is a task where these models really make a difference to the accuracy of your system, and we could do much more. We could also imagine having longer term models of a person. I don't really want Google or Amazon building a complex multi-year model of what Jamie knows, but I have a device sitting in my kitchen, and I don't mind if that device knows about me as long as it doesn't export that model up to the cloud. And so we might think about what we could do with more detailed models of individuals. And that's something we really haven't done a lot with. And finally, evaluation. As I said before, our evaluation criteria is really different than other fields. And I think that's something that we can exploit in this area. Also, I think we should think about how we partner with colleagues in NLP and dialogue systems. Probably they're going to sit between us and the person seeking the information, right? I don't run Alexa or Cortana or other dialogue systems. So we need to think about what their systems need from ours. In the question answering era, I would say we fumbled this. The question answering systems didn't really want much from us. Just give us your rankings using bag of words search and we'll be happy. I think we could do more in this environment. The dialogue systems, most of them are driven by strong models of the task and of the domain. When we go into open domain conversations, then we don't have those strong models anymore. So one thing we might ask our friends in the dialogue community is, can we help you with approximate models? We're very good at pseudo-relevance feedback, getting a bunch of documents that are about this topic and then analyzing them in some way. So could we do something like that where we identify the important concepts and relations in this subject and hand that off to the dialogue system? Now, it's not going to be as good as a curated model, but it might be better than nothing. And so we have opportunities to collaborate with our colleagues in these other fields to help them make their systems better. And we're doing this with things that the IR community is very good at. Okay, so it's time for me to wrap this up. I've talked about 3 different things: vocabulary understanding tailored for search tasks, document understanding tailored for search tasks, and context understanding, and perhaps eventually more, exploiting stronger corpus models and producing approximate domain models in conversational search. So I think all of these are examples of ways that we use the newer technology to focus on problems that are uniquely IR, or where a uniquely IR perspective on something delivers an improvement that wouldn't necessarily have come from our adjacent research communities. I think this is a really interesting moment in IR. The discrete representations, the bag of words representations that we have been reliant on for 50 years are being updated and replaced. And I just think that's amazing. As someone who's worked in computer science for a long time, there aren't many things that last that long. Really great respect to the people that developed those in the early days of our field. Many of us have tried to improve upon these things, but it's been really difficult. They've been really strong and robust methods. And now finally it looks like they're being replaced, and that creates a lot of uncertainty, but also opportunity in our field. As I said, I think a lot of the fundamental improvements right now are coming from NLP and machine learning, and the IR community is reacting more than leading. And I think that's a little bit to be expected because we were a little bit late to the neural era. As I said, the neural models just didn't work well in our field until a couple of years ago, well, 3 years ago, I guess. But now that it's here, we really need to take control and control our own destiny. So I think it's a good time for us to think about our core values and strengths, especially in a time when the NLP community is doing a bunch of things that we typically thought of as IR problems or IR approaches to problems. And to be fair to the NLP people, they're doing a good job. So we really do need to up our game. We need to think about what will be our unique contributions to this new wave of technology. Now, I don't want to end this on a negative note. I don't mean to say, oh, we're suffering or we're doing quite poorly. I think, as I said before, we have this wave of new technology coming over us, and we're thinking about how to grapple with it in our field. And I think it's a really exciting time to be an IR researcher. One of the things I love about computer science is you can never stand still. It's constantly changing, constantly new technology coming along and changing the way we do things. This is one of those moments in our field, and this is an opportunity when the research that people do can really make a difference for the next decade. So I think it's a great time to be doing work in this field. With that, I'll stop. I want to give a thanks to some of my collaborators on the work that I talked about today. There are references there to some of the things I talked about. Thank you very much for your attention through the talk, and I would be happy to take any questions.
Thank you very much, Jamie, for a very interesting talk that raised lots of interesting questions for all of us, actually. There are several questions that I can see in the Q&A, and again, a reminder to participants, you could either type in the Q&A or you could just raise your hand. So we have our first question comes from Fabrizio Sebastiani. Can we unmute him, or maybe I can just read the question because it's a rather long one. So, Joao, we can't hear you. Okay, so maybe I'll just read the question. So what Fabrizio is saying is you mentioned that in recent wave of research driven by deep learning, ML and NLP have been leading while IR has been trailing. Do you think this is also due to the fact that those two communities have all, or to a large portion, of their literature as open access, while the IR literature is still 100% behind paywalls? Not still, but it's been a lot.
No, I don't think it's an open access problem. I think our community has a long history of people posting their papers on their websites. We've, over the last few years, more of us have adopted arXiv as a way of getting our research results out into the community. And so I feel like we have pretty good access to information. We also have a long history of sharing data sets and also sharing software. So I feel like we're a pretty open community. So no, my personal opinion is no, that hasn't been a factor.
And we have a question from one of the attendees, Juan Basco.
Juan?
Yes,
Yes,
you said that the search is a dialogue between the tool and the user. So do you think that it's possible that one day we have a standardized evaluation protocol for user tool interaction, the same that we have for all the other tasks?
Yes, I do. I really do believe that. I think we could already do that in some ways with the metrics and the methodologies that we have now. I think one of the things that makes it difficult is making reusable data sets, which is one of the great advances that Trek gave us. Well, it was around before Trek, but Trek became a machine for churning out these reusable data sets. And so I think it's harder to know how to create reusable data sets when user interaction can change the flow. But I think we'll be able to do that. In fact, I expect we'll do that over the next few years.
Hopefully.
Yeah, hopefully. Well, I hope you'll help.
Thank you.
Thanks. We have a follow-up question from Fabrizio Sebastiani. Just raise the hand.
You're unmuted now, Fabrizio.
Fabrizio, can you please unmute if you can hear us?
Yes. No, it was just the question that you asked him in. So it was not a second question.
Oh, okay. It just appeared. Okay, great. Okay, great. So then we can switch to the Q&A part. So Andrew McFarlane has a question. He says, you mentioned the prospect for long queries. Do you have a view of how very long queries in systematic reviews could be supported by re-ranking methods?
I think that so when we look at the narrative, one of the things that's interesting about the narrative is it gives actually usually very detailed instructions to assessors about what makes a document relevant. And I think we we as a community have never really loved the narrative or tried to make use of that structure that's in there. We have usually thought of it as a source of keywords that we could drop into our bag of words models. And so I think it requires a better understanding of how these things are organized, which terms are sort of abstract terms or higher level descriptions of what it means to make a document relevant, and which ones are more specific requirements that are more like the keywords that we see in titles and descriptions. And I just think most of us have not really looked at the structure of the narrative at all. But you know, that the structure of the complex text topics comes out of library science. So there they have a methodology for asking people to describe their information need at different levels of abstraction or different levels of detail, and so there is a method to the madness in the narrative, but most of our systems just don't know anything about that. And so one of the reasons I focus on the narrative, first, I think it's cool that we can even make it work well, but also we trained the last generation of search users, the people who came on the web, to describe their information needs with 2 or 3 words. And that's what everybody does when they go to the web, right? They enter short queries. In the conversational world where people are talking to devices, there's an opportunity to train them that more detail gets you better results. But then we need systems that can make better use of that detail. So I just think we need to focus on that.
Thank you. And one more question. This is from Sergio Nunes. So how can we avoid the privacy challenges that exist in building our systems and research over private companies that work in a surveillance capitalism model? Do you think that we can have open source infrastructures for conversational search?
So I think that we, as I said, well, I think there's 2 answers to that. One is in something like CAST, we're building a model of an artificial user, and that's easy to share. But as I said during the talk, I'm okay with my laptop computer or my own personal Cortana or Alexa knowing all kinds of stuff about me, right? The computers that I use today are descended from computers that I used 3 years ago, and 6 years ago, and 9 years ago. I've been using computers my whole professional life, and so there's an opportunity for them to know a lot about me, and I'd be okay with that. I just don't want that information being exported off to Google or Amazon, right? That's where the privacy problem is. And so I think if we worked on models where we have let's say a user model or a task model that has 2 components to it. One of them is a population component that can be learned at Google or Microsoft or Amazon using huge amounts of data. And then there's the Jamie model that lives on Jamie's device and that smooths the results coming in from the population models. I'm okay with that. And I think many people would be okay with that. And I think we could develop that framework, and then we could work with individual users, and we could still measure success. We just don't export the personal model.
Yeah, I agree with that. So one more question, Martin White. So the question is, at present, the research seems to be focused inevitably on questions in English against an English corpus. In the enterprise context, users may be querying in their second language, like German, against an English corpus that might not be able to frame a good English query. So is this a challenge on the research roadmap?
Yes, and I think it's also an opportunity. I think cross-lingual IR was a hot topic in IR 15 years ago or so. And then I think for a while we felt like it was a solved problem. It was important commercially, but most of us didn't really work on it in the research context. I think that in conversational settings, that's going to become more important again for a variety of reasons. The language is very different, and the expectations for what is returned are also very different. And so, yeah, I think there are interesting opportunities here.
One more question by Muhammad Ali Norozi. So when it comes to alternative or better representations for search tasks, isn't it also time for IR to get out of the evaluation metrics boxes, the famous ones, get out of those numbers which tells that one approach is better than another by like 0.001%? therefore statistically significant.
Yeah, I agree. But I also think this is, I think this is a time when, as our tasks shift, we should be developing new metrics, and we should also be focusing, well, I said, our roots are in make the user happy. And I think sometimes we forget that. We focus on improving a metric by a small amount, an amount that probably our user would never really notice. And so I think that that is something that we as a field should maybe be a little more careful about. But I also know, or I believe, I don't know, I believe that when we look at web search engines, we have seen them rolling out a long sequence of 1% or 2% improvements. And over the years, those systems have gotten much more effective. So there may be value to an accumulation of small improvements that we in the research community don't really appreciate or value, that nonetheless have a big effect commercially.
We are reaching the end of the session actually, but I just wanted to finish with one last question, which I thought is quite interesting. So it's by an anonymous attendee, and the question is, could you share your thoughts in incorporating BM25-like formulae into neural models, perhaps as constraints as compared to updating parts of these formulae using neural models trained separately?
So I think that's, I think two things about that. I think I've seen neural models, I've seen neural models where BM25 is incorporated as a signal. And I don't particularly like that because it feels like a kind of a learning to rank system where we're just now sticking in lots of different features. And in theory, one of the good things about neural models is that we don't have to do a lot of feature engineering. But at the same time, I think I've also seen some really imaginative uses of BM25 in neural models, where the goal is to teach the neural model to do the kinds of things that BM25 is not doing well. And recognizing that these neural models live in a pipeline with BM25. And so what BM25 does well, the neural model doesn't really need to focus on. And I think that's really interesting, where the different parts of the pipeline are actually aware of each other to some extent.
Okay, well, thank you very much, Amy. This was really interesting and quite inspiring. So that's why it raised lots of questions. We have quite a few more, which we are not able to cover. I hope they will be able to reach you offline. Again, thank you so much. It was really nice.
Thank you, I appreciate it.
Okay, so now we have our award ceremony, and I will hand to Ben Carteret, who will be leading our award ceremony. And again, authors, please do not leave. Any of you could be receiving awards. We have several awards, so please stay there and be ready. Okay, thanks.
Okay, thank you. Yeah, so I'm really excited to be able to attend ECIR. I wouldn't have been able to go if it wasn't virtual, and I think the organizers have done a really great job of making it a really good virtual conference. So I'm happy to be here, happy to be representing ACM-SIG-IR, and I'm really honored to be able to present these Best Paper Awards. So I chaired two committees for awards for full papers. So there's one committee for a traditional Best Paper Award, and then one for an award for potential industry impact. The two committees had the same set of papers, but there were different criteria for the awards. And in the end, it turned out that the two committees agreed on the top three papers. So they merged and then decided on which papers would get which awards at that point. So I'm going to present the traditional Best Paper Award first. So I first want to thank the committee, Grace Young, Nicola Ferro, Gabriella Passi, Udo Kruschwitz, and Dia Albacore. And for this paper, we were looking for kind of traditional research, research merit, technical quality, good presentation, thoroughness, generalizability, reproducibility, and potential for future impact on research and application. And so we picked the paper. The award goes to Panagiotis Papadakos and Giannis Konstantakis for the paper Bias Goggles, Graph-Based Computation of the Bias of Web Domains Through the Eyes of Users. All right. wasn't expecting that, but that was very nice. So I just want to read a few.
Yeah, sorry. If any of the authors are in the audience, can you please raise your hand so that we enable your camera? You can go ahead in the meantime, Ben.
Okay. So I just wanted to give relay a couple of the comments that the committee members said about this paper. So the paper presents a novel and intuitive way to think about societal bias, to think about it through a network structure based on the idea of PageRank. And they felt like the ideas in this paper could potentially be applied across a wide range of settings, and they have a lot of potential to spur follow-up work. So, so congratulations to the authors. And did they, Pablo, did they show up?
Hi. Hi, thank you very much. This is a really great honor. I don't know what to say. I really believe in this work, and I hope that it will have some kind of impact and will help everyday users consuming less biased and more responsibly information. What else? Thank you really. I really thank you very much.
Thank you. Okay, so I want to turn it over to I want to turn it over to Dia Albacore now to say a few words about the Industry Impact Award, which was sponsored by Signal AI.
Thank you, Ben. So for those who don't know me, I'm Dia from Signal AI, the sponsor of the Industry Impact Award. So I'd like to say a few words to give you some context about this brand new award. So it's all started last year on the back of some discussions in Cologne during ECIR2019, when it was possible to do physical conferences. So specifically, the discussion was on how we as a community encourage and reward IR research that considers impact. And by impact, we mean business or user value, societal impact, things like that. So the papers we want to recognize and reward are those that consider things like availability of code and data, efficiency, simplicity of implementation, costs, and users' value. So myself and Miguel from Signal, we put forward a proposal to the ISG committee and the organizers of this ECIR, and everyone was supportive. So it was agreed to run this award for at least 3 years, and we will be sponsoring the award this year and the next 2 years. And so we need a sponsor, because the nice thing about this award, there is a money prize associated with it, which is a value of like 1,000 euros. So we have a winner this year, but hey, it could be yours next year. So think about industry impact in your next IR paper. And as Jamie said earlier in his keynote talk, it's an exciting time to be an IR researcher. So yeah, finally, I would like to thank the program chairs, Emily and Joyman, for helping in making this happen, and for Ben for chairing the committee and leading the discussions that led to selecting the paper. So I hand over to you, Ben, to announce the lucky winners.
Yeah, thank you. Yeah, so we wanted to get a really diverse committee for this award, so we asked people from a wide variety of different industrial settings. So the committee was Luan Aitan from Amazon, Rashad Malhotra from Spotify, Michael Bendersky from Google, Ajia Bega from Microsoft, and Jochen Leidner from Reuters, and then Jia was also on the committee. So this is people working on a wide variety of different applications. And this award goes to Uni Krishnan, Alistair Moffat, Justin Zobel, and Bodo Bellerbach for their paper, Generation of Synthetic Query Auto-Completion Logs. One nice thing about this paper I want to point out is that it's a collaboration between industry and academia, which I think is really a really nice feature for this award. So some of the comments from the committee about this paper, they saw it as allowing much greater scope for research on query logs. It removes the problem of sharing personal data, and it can be used to generate huge amounts of data, like realistic data, to train neural models and self-learning ranking systems.
Do we have any of the winners in the meeting?
Oh,
there's Uni.
He's already here.
Yeah. Should I speak now?
Yeah.
Sure. Go ahead.
Oh yeah. Oh well. Yeah. Thanks, Ben, and thanks to all the panelists for the award. I mean, I wasn't expecting it all. This has been a work in progress for a long time, and we have worked on generating the abstracted version. I mean, a privacy-preserving version of the logs first, and then converted that into a synthetic log. So I'll be presenting this paper tomorrow. So I'm hoping that I could share more details. But thank you so much for this amazing honor.
Congratulations.
And then I also wanted to mention to award one honorable mention for the Industrial Impact Award. This paper is by Jie-Shin Wang, Adam Jataut, Michael Farber, and Masatoshi Yoshikawa for the papers Answering Event-Related Questions Over Long-Term News Article Archives. And the reviewers felt like this. And the reviewers felt that this paper was well positioned for all the criteria of the Industrial Impact Award, and the idea of time-aware re-ranking can clearly benefit state-of-the-art question answering methods. So those are the long paper awards, and I believe next on the agenda is Pablo. Do you want to take over?
Yeah, sure. So now we are going to announce the best short paper award. So Nicola Ferro is going to announce this one. And then Ana Freire will announce the best demo award. Nicola?
Hi, good morning to everybody. So traditionally, the best short paper award adopts a voting mechanism by the community. You vote the posters, the best short talk, etc. But this year it would have been a little bit more problematic to implement this community-based voting scheme. So we resorted to work in a small committee constituted by the short paper chairs, Mario da Silva and myself, plus the general chairs, Joao and Pablo. And basically, we look at the top papers, we look at their reviews, at the paper itself, at the video of the paper uploaded on YouTube for presentation, and we considered several aspects like the technical quality of the contribution, the potential impact, etc. And an aspect that we considered most was novelty, in the sense that from a short paper you expect somehow they bring in some novel ideas, or they look a new perspective, or they bring together some experimental piece of research. And this was one of the main criteria we adopted. So I think I'm happy to announce the winners of the short paper is Crowdsourcing Truthfulness, the Impact of Judgment Scale and Assessor Bias by David La Barbera, Kevin Roteiro, Damiano Spina, Stefano Mizzaro, and Gianluca Del Martini. So we have a transcontinental team here working in this paper, and one of the motivations we liked it much is this interesting angle crossing between evaluation, crowdsourcing, so ground truth creation, and assessor bias. This is a paper that adds a new angle on ground truth creation and how the bias, the personal bias of the assessor may affect their judgments. So congratulations. Is there anyone in the audience of the authors? Okay, there is Kevin.
Hi. Hi, so thank you very much for the award. I will share the news with all the other colleagues.
Great. Thank you, Kevin, and congratulations again.
Thank you.
And next, we also had an honorable mention for the Best Paper Award, and it goes to contextualized embeddings in named entity recognition, an empirical study on generalization by Bruno Taillier, Vincent Going, and Patrick Gallinari. Also, in this case, we liked here the approach in filling some gaps between our field, NLP, etc., and also trying to understand what works and why it works in the application of embeddings in some tasks. So not just looking at gaining performance, but also gaining understanding on why we have those performance, something which was also mentioned today by Jamie in his talk. So congratulations. I think that's all for the short papers.
Okay, so I think we can move on to the best demo paper with Ana Freire.
Yeah, sure. Hi, everyone. I am Ana Freire from Pompeu Fabra University in Barcelona. I would really love to be in Lisbon right now, but it's also nice to see how we are all facing the challenge of an online ECIR. I should say congratulations to all because it's been a really great success. All right, so it's time to announce the Best Demo Paper Award. I will share the criteria that all the committee had to give this award later. Yeah, usually this is done on site, you know, but we have to do this like is the rest of the awards today, right? So the best demo paper goes to Revisionista PT, Uncovering the News Cycle Using Web Archives, author by Flavio Martins and Andre Mourão. Congratulations. So I would like to know that the committee made the decision based on several criteria, including the review score, the quality of the contribution, the demo and the video, and also the topic, which is a hot topic in IR, which is fake news. You can all try the demo online as well. I don't know if any of the authors are here.
I'm here. Can you see me?
Yeah. Yeah.
Okay. Thank you very much for the award. So it's quite cool to see this work being published at ECIR, and to see that, because this is an important problem, and it's good to, well, for people to know about it, because, well, as you said, this is, and now with the COVID and everything, this becomes a larger problem that we are actually working on now. So thank you very much.
Congratulations again. And I give way to Pablo again.
Okay, so thank you, Anna. Last but not least, we have the Test of Time Award. It will be presented by Maristela Agosti, who was the chair of this committee. And we will be honored by having a very special guest joining in this announcement.
So thank you very much, Pablo.
Hi, Maristela.
Thank you. Thank you.
Steve Robertson, can you turn on your
Hello,
camera?
hello, I'm here.
Hello, Steve. So just few words to introduce the award. So this award is fairly recent. It has been started at ECIR in 2016, and is an award that is trying to give to recognize the impact of a paper over the years. In fact, the committee has to consider the papers that has been published from 10 to 12 years before the year of the award. And the committee has been formed after it has been possible to choose and collect the papers that were to be considered for the award. Because since there are 3 years and a lot of papers this year, we considered 22 papers at the beginning. It's very easy. Then there are experts that are involved in one of the papers. So to form the committee is not easy, and it's necessary to form it after the selection of the bunch of papers to consider. To avoid the conflict of interest. The committee this year was made by Catherine Beru from Grenoble, Paul CLEF from Sheffield, Fabio Prestani from Lugano, Gareth Jones for Dublin, Josiane Mote from Toulouse, and Stefan Relger from the Open University in United Kingdom. I thank you all them for the work that we have done together. The work has been done very smoothly, also if it was a very challenging work, because we have started really with very, very good papers, and it was difficult to choose and to make the choice of the one to propose. In effect, we propose one for the award, and afterwards also one for an honorable mention. So I pass the word to Stefan for announcing the Test of Time Award of ECIR.
Thank you, Maristella. I have my envelope here. I'm going to open it. And I hope that someone will reveal. So the Test of Time Award goes to a language modeling approach for temporal information needs. It was presented at ECIR in 2010, and the authors are Klaus Berbrich, Srikanta Bedato, Omar Alonso, and Gerhard Weikum.
And if you like, I can read the motivations of the committee. So this excellent paper was one of the first to give temporal information needs a theoretical foundation in language models and proves them suitable through rigorous experimentation. The increasing focus on the temporal dimension in many search applications demonstrates the importance of this foundational work for current information retrieval. As an outstanding research paper investigated a challenging and important problem, which is of increased significance today. So we have considered this worthy winner of the Test of Time this year. Somebody in the audience of the authors? I don't think so.
Apparently not.
I don't think.
No. No. So we can move on to the
So,
okay. So the Test of Time honorable mention goes to the paper Discounted Cumulative Gain based evaluation of multiple query IR sessions at ECIR 2008, authored by Callan Yavrelin, Susan Price, Lois Del Cambre, Marianne Leike Nielsen. Sorry.
And the motivation is people And the motivation is this paper reports on a simple yet effective extension of DCJ for multiple query IR sections. It addresses a challenge of evaluation in real-life search applications, which remains important today. It is extremely well argued in its development of its evaluation framework, which is then supported with carefully experimentation. This is an exemplar paper in sound experimental research methodology in information retrieval. Congratulations. Nobody there? No.
Any author is present?
I don't see any author saying anything.
I guess not.
No.
Okay. Well, so thank you very much, Maristela, Stephen. Thank all the presenters. Congratulations again to all the winners. Thanks the committees for your excellent and thorough work. I don't know, Joao, if you want to say also anything.
Yeah, I would like to say thank you to all of you. And now the most important thing is that I would like to ask you all to switch on your cameras so that we can take the usual picture. And then I will hand over back to Pablo. Jamie, Gustavo, Ana, Uni, Krishna, Andre, no, Uni. Yeah, well, he's thrilled, and I bet he went celebrating. So a big smile and thank you. Thank you all.
Thanks, everyone.
Back to you.
Okay, thank you.
Thank you all.
Thank you.
Yeah, so we're basically done with this session with the awards announcement. Thanks everyone for being here. Congratulations to all the winners. So this is it. So we will go for a coffee break now, and I think we still have one last session starting at 3:40 or 45. So I'll see you all there. Thank you.
Thank you.
Thank you.
Thank you, Steve. Thank you.
Thank you. Thank you.
Thank you, Steve.
Thank you very much.
For the collaboration. Bye.
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 Goodbye.
Hi, Gustavo.
Hi, Gabriela.
Hi, how are you?
Fine, you?
Fine, thank you.
So I'm here to help. I'm expecting that João or you will do the introduction to the session, but I'm here to take care of the questions and the chat and everything else.
Okay, very good. We have to wait and to see if all the presenters are here, or they will come in a few minutes. Okay.
Yeah. Okay. I will make them panelists so that they can share the screen.
Okay. Thank you. Thank you.
You're welcome.
Hi, Arthur.
Hi.
You are the first presenter, right?
Yes.
Okay, very good. So just to see if you all are here. So you are the first presenter. Then I see Zihu Chen. Hi, Zihu. Zihu is the second presenter, right?
Yes.
Very good. Then we have Sean, who is the third one. Hi.
Hi, how are you?
Fine, thank you. And you?
I'm doing well.
Good. Welcome to this session.
Thanks.
Okay, let's hope. Let's wait for the other people. And let's wait for the right time to start. Okay, it will be 16:45. Then Sean, Zihu, Sean, Pablo, mancano due. So we missed two people.
Hello.
Hello. Okay, Rui Enriquez. Hi, nice to see you.
Nice to see you too.
Now you can see me. Hi. So you are the presenter of the fourth paper, right?
Exactly.
Very good. So we have almost all people. We still miss the presenter of the Fabio. Ciao, Fabio. Hi.
No, it's not Fabio. I'm his student.
Fabio
Esteban.
okay. Who is going to
Gabriela,
present?
Yeah, it's Esteban. It's
Esteban.
Okay, Esteban. Hi. Okay,
Hi.
very good. Hi. So it seems we are all here. So we just wait for the right time to start. And you will have overall 20 minutes, okay? So you have 16 minutes for presentation, and then we have some times for questions, for the question answering part, okay? I think we are almost ready to start. Still a couple of minutes.
So I've released the screen. Whoever
Yes,
wants to start, and
I show myself so I can introduce the session. What do you think in just 1 minute? So we are punctual. What do you think, Gustavo?
Yeah, I think it's perfect.
Okay. So, hello. I think we can start. We can open this session. The session is dedicated to information extraction. We have 5 papers. The people are all here ready to present their interesting contributions. So I welcome all of you in this afternoon, at least in Italy it is afternoon. And so I think that we can start with the first paper. The first presenter is Arthur Brack, and is going to present, to report his research on domain-independent extraction of scientific concepts from research articles. So, Arthur, you can share your presentation.
Yes, hi.
Okay, very good. So welcome. Please, you can look at me at a certain point because I am sure that you will punctual, but if you are a little bit late, I will make you some signs, okay?
Okay.
You can start. Thank you.
Thank you. So can you see my slides?
Yes.
Okay, great. Well, thank you. Welcome to my presentation. My name is Arthur Brack. I'm a PhD student at TIB in Hanover in Germany. And TIB is the National Library for Science and Technology in Germany. So the main purpose of TIB is to organize scientific literature. In this presentation, I will present you our recent paper that deals with domain-independent scientific concept extraction from research articles. And let's start with a motivation. First, as all of you know, there is a huge amount of scientific articles out there. So it gets harder and harder for us researchers to stay up to date with the current research and to find related work. Well, one main reason for that is that scholarly knowledge is conveyed in plain PDF files and therefore not machine interpretable by machines. Therefore, research infrastructures such as academic search engines are not able to support scientists adequately in their core tasks, such as to find related work. Our approach is to represent scholarly knowledge in a knowledge graph in which research articles are interconnected through entities like tasks, methods, or materials, and so on. However, existing knowledge graphs such as Wikidata, for instance, and also some domain-specific knowledge graphs have a rather low coverage of scientific concepts. For instance, a lot of tasks in the machine learning domain are not present in Wikipedia. For instance, maybe you will find that some popular tasks such as text classification or named entity recognition on Wikipedia. However, you will not find more specific tasks such as, for instance, geolocation estimation of photos or event recognition in videos from the computer vision domain. You won't find them neither in Wikipedia nor in the computer science ontology, which was created specifically for the computer science domain. So we need approaches to construct automatically fine-grained knowledge graphs. However, machine learning approaches require annotated data, and annotating scientific corpora is very costly and usually requires domain experts because every scientific domain has its specific terminology and phrasing, and determining its most important statements require certain domains expertise. Well, in this paper, we explore the task in which we extract scientific concepts and research articles at a phrase level. Here we have an example from the astronomy domain. where our task is to extract such scientific concepts which are highlighted here. And yes, in this paper, we explore the following research questions. The first one is, are generic concepts identifiable across multiple domains by non-experts? Intuitively, most domain-specific articles share certain core concepts such as task, use materials, applied methods, and so on. So for instance, problems in clinical trials and software tools in computer science could be treated as materials. Yes, it's a very abstract term, but in particular, this can be treated as materials. And the question is whether such generic concepts are identifiable by annotators, which are not experts in all the investigated scientific fields, but experts in annotating tasks. This would enable the annotation of scientific corpora, which much less effort, which may not reach all the scientific knowledge in all depth, but still provide some science-specific structure. The second question is, which domains generalize well? And can we mix the domains to implement the domain-independent classifier? And the third question is, which amount of labeled data is really necessary? And how can we reduce annotation costs for such tasks? Well, to answer these questions, we first conduct an annotation study with 10 different scientific, technical, medical, and domains, like astronomy, chemistry, or engineering. And for that, we use the open access STM corpus of Elsevier that has been published to benchmark NLP tasks in the scientific domain. And this corpus consists of 110 abstracts from 10 STM domains. So we have 11 abstracts per domain. And then we present an automatic domain-independent scientific concept extraction systems in two variants, where we employ supervised learning with full training set and also active learning with training data subset. Yes, let's start with the annotation study. The annotation study went through several phases, which are depicted here. And the pre-annotation phase, two annotators first performed some trial annotations to identify scientific concept types that generalize well across domains. And the identified concepts were process, method, material, and data. And well, the annotators are two postdoctoral researchers from computer science and experienced in the annotation tasks. Yes, then in phase one, both annotators independently annotated subsets of the data sets, and the intercoder agreement was 52 Cohen's kappa. So we had only a moderate agreement. Then in phase two, subject specialists who are librarians at TIB reviewed the annotated concepts. The annotations guidelines were refined. And then in the last phase, the annotators re-annotated the corpus of the first phase, and they could achieve an intercoder agreement of 67 Cohen's kappa. So this is a substantial agreement. And the rest of the remaining of the data sets was then annotated by one expert. So we can conclude that generic concepts are identifiable by a non-expert with moderate agreement, and after consultation with subject specialists with substantial agreement. Here we can see some characteristics of our STM corpus compared to other similar corpora. We can see that our corpus is smaller than the others in terms of the number of abstracts. However, we cover much more domains. So we cover here 10 domains, and related corpora cover at most three domains. So here, for instance, Science AE corpus covers computer science, material science, and physics, and this CIRC corpus only artificial intelligence. We can also see here the intercode agreement. So we have 67 Kappa, Science IE has 60, and CIRC has 77. So so we have a pretty high intercode agreement, I think. Although it's very difficult to annotate scientific corpora. Yes, let's continue with automatic scientific concepts extraction. We use the current state-of-the-art deep learning architecture of Bertegi et al., where we employ CyBERT, contextual word embedding. CyBERT is based on the BERT architecture and was pre-trained on scientific text. Well, and our architecture for concept extraction is a standard architecture for named entity recognition, which consists of an embedding layer with CyBERT word embeddings and CNN character embeddings, then 2 stacked B LSTMs, and finally a conditional random field that decodes the text of the entities. And we use a B-load tagging scheme in our approach. To evaluate our models, we employ 5-fold cross-validation, where we split the data set in 8 per domain in 8 abstracts for training, or 1 abstract for validation, and 2 abstracts for the test set. And we report micro-averaged F1 scores with exact span matches. So the system has to recognize exact spans and not just overlaps. Then the first setting is where we employ supervised learning with a full training set. So we train for each domain a domain-specific classifier. So we have 1 classifier per domain, and we train 1 domain-independent classifier. So this is 1 classifier for all domains. The second setting, in the second setting, we employ active learning. And the objective of active learning is to minimize annotation. So the idea is that the human annotator shall label those instances from which the model will learn most. So in this picture, we can see the typical flow. We have a small set of label training set. Then we train a model. With the model, we predict the labels of unlabeled data. And then we select certain instances from this unlabeled pool. The annotator annotates them, and then the cycle starts again. And there are various strategies for sampling instances from unlabeled data, and the most popular one is based on uncertainty sampling, which means that those instances are selected where the model is most certain about the correct label. In our experiment, we employed the maximum normalized log probability sampling strategy, which was tailored for named entity recognition tasks. And well, the idea is that the logarithmic likelihood of the predicted text sequence normalized by the length of the input sentence. So we select those sentences where this score is least. And then we perform 25 iterations, so 25 cycles, where we add 4% of the training data in each stage. Yeah, here we can see the results of our domain-independent and domain-specific classifiers. So the blue bar is the domain-specific classifier, which was trained and tested on the particular domains here. And the red bar is the domain-independent classifier, which was trained on all the training data. And we can see that well, the domain-independent classifier generalizes pretty well, as it beats all the domain-specific classifier here, except here PO. And the overall performance of the domain-independent classifier is 65 F1 score, which is quite a good result compared to the other data sets. So we can conclude that the domain-independent classifier generalizes well across domains. And bio is the most robust domain, so the domain-specific, domain-independent classifier is not able to beat it. Well, for active learning, you can see here the results. So the x-axis depicts the percent of training data, and the y-axis depicts the of1 score. The blue line is the active learning progress with MNLP sampling strategy, and we have also a random baseline where we just sample the sentence randomly. And the experiment was performed for the 5 folds, so the areas depict the standard deviations of the results here. So we can see here that MNLP outperforms the random baseline, and we can also see that about 52% here. We achieve the performance of the classifier that is trained with the whole training set. So yes, and the random baseline is much worse than the MNLP strategy. Here we can see also that active learning provides comparable results for comparable data sets. So we have here our corpus, SAREC, Science.ie, and here we see the amount of training data that is necessary to achieve the performance of the classifier with full training data. Yeah, so we can see here we achieve here the same performance. Here it's nearly the same performance, and here we already beat the performance of the classifier with full training data with only 38%. So we can conclude that active learning enables us to nearly halve the training data for concept extraction and scientific text. We have also performed a correlation analysis between intercoder agreement and the F1 scores. So we can see here the inter-annotator agreement for each respective domain. Here we can see the number of annotated concepts for the domain. And here we see the F1 scores for the domain-specific, domain-independent, and the active learning trained classifier. And we can see that we have only a weak correlation between intercoder agreement and the F1 score, and a strong correlation between the number of annotated concepts, phrases, and F1. So we can conclude that intercoder agreement is not so important for the F1 scores than the number of annotated concepts. Yes. Let's draw a conclusion. We can identify generic concepts by non-experts, which is very good because we can create domain-independent corpora to capture the semantic structure of scientific concepts. Well, and the domain-independent classifier generalizes well across the domains. Active learning enables us to nearly halve the training data, which is also very promising. And we could also observe only a weak correlation between the intercoder agreement and the F1 score. Our source code is publicly available, so you can reproduce the results. And also the data set can be downloaded here at this link or also at this link. Yes, for future work, we plan to extend the corpus with entity linking, which has already been done at our paper for the LREC, which will be held later in 2020. We plan also to extend the corpus with co-reference links and relations, and then we also plan to expand an open research knowledge graph. That envisions to structure semantically scholarly knowledge with automatic and also manual approaches. Yeah, thank you for your attention. And yes, if you have any questions.
Thank you very much, Arthur, for your nice presentation, and you were perfectly on time with your presentation. So
thank you
for the question answering session. So I remind the audience that if you want to ask a question, you can raise question in the question answering box that you can find on the bottom of your screen. We have a question, I see. Michael Farber is going to ask this question. So the question is the following: as baselines, no regular CRF was used. Was there a specific reason to consider only neural networks?
Well, we wanted to avoid any feature engineering for our baseline, so we have chosen Cybird for that, and also the standard named entity recognition architecture for that. In the preliminary study, we also performed some simulation study with other corpora, but we observed that this architecture performed best. So therefore, we decided to employ it also for our data set.
Okay, thank you. Do you have any other questions? Yes, Paolo Almeida. You can also see Arthur, I think, the question. Were you surprised by intercoder agreement not being important?
Well, I was a little bit surprised by this result. However, I have also read some other related work where they had also observed similar observations. For instance, Teufel et al., they had also performed such a correlation analysis, and they also found no correlation between F1 and intercoder agreement. So yes, it's a little bit surprising, but it seems not to be uncommon.
Thank you. Are there any other questions?
Excuse me, Gabriela. In the participants list, there are 2 people with their hands raised. Ting Su from Glasgow. I will give them mic permissions for them to pose a question.
Okay. Okay.
Hi there. Thank you for your talk. It's very good. I have a question is about the active learning part. So how do you sample your examples, and have you tried that? Does the different starting samples would make a difference in your learning process or the results?
Yeah. Well, we have conducted the experiment for the 5 folds. So we divided our data into 5 folds and restarted the test for each fold. And then we calculated the average of the results and also the standard deviations for that. So we have repeated the experiment several times, and we could observe a similar trend.
So even for the active learning?
Even for the active learning, yeah. Maybe, yeah.
Okay, thank you. Are there any other questions?
One more question from Elena Tubalina.
Okay, thank you, Gustav.
Yeah, hi, Arthur. Thank you for the nice talk. I have a question about domain independent classifier. If I understood correctly, you train classifier on all data and then evaluating on all data also. Did you try to train on 9 domains and evaluate it on the last domain, for example, if it's actually domain independent, or it's just because you train on all domains, you consider it as domain independent? Is it clear?
Well, the domain independent classifier was trained on all the training data for all domains, and
yeah,
the domains
but what about new domain? I mean, if you train on 10 domains, you can say it's domain independent because basically you train on the domain, but with some noise. Did you try to train on 9 domains and then testing on the last domain? It would, that's only after that you can consider that it's independent for a domain.
No, we have not tried out this setup, yes. But it's an interesting question, yes.
So yeah, I'm concerned about what will be if you actually add new domain that you didn't use for training.
Well, I think if you add a few more domains, then it would be beneficial to annotate this new domain and add it to the domain independent classifier corpus. And our results indicate that you need approximately 5 to annotate 5 abstracts for a new domain. So this should be sufficient. So this is the approach that I would suggest. So if you add a new domain, then just annotate 5 more abstracts with the active learning strategy.
Yeah, makes sense. Thank you.
Yeah.
So are there any other questions? Gustavo, there are other people who raised their hand.
I don't think so.
Okay, okay. I have a very last question, Arthur. you say that annotators did their job by taking different domains and trying to annotate with common words, not specific words. So my question is, how many texts, how many concepts they figure out, they defined in this annotating activity? Overall.
When the annotators started, they had a set of concepts of about 20 to 30, I think, if I remember correctly. And this set was selected from related work. So they have not invented new concepts, but took them from related work. And that this set was pruned to the 4 concepts when they have made the trial annotations. But they started with a very broad concept set at the beginning.
Okay, so they started with the broad concept sets and then they focused, let's say, on...
yes, exactly. Exactly, yes.
Okay, thank you. So thank you again. Thanks again. If there are not other questions, I think that we can go to the second presenter of this session. So thank you again, Arthur.
Yeah, thank you also.
Thank you.
Bye.
So
Bye.
I am happy to introduce Zihu Chen, who is going to present the paper titled Leveraging Schema Labels to Enhance Dataset Search. Are you ready to present, Zihu?
Yeah, can you see my screen?
Hi. Nice to see you.
Nice to see you.
Okay, when you're ready, you can start.
Okay, can you see the screen? Share the slides?
Yes, it's okay.
Great. So I will start right now.
Please go.
Hi everyone, my name is Ziyu Chen from Lehigh University. So today we are presenting our work leveraging schema labels to enhance dataset search. So first, start from some introduction or problem setting. So first, what is a dataset? So a dataset usually includes 2 parts. The first part is a data table. The second part is a metadata of the dataset. And the data table usually includes schema labels and data rows. And in some other context, the schema labels are also named table headers or attribute names. And for the metadata, usually a data set will have the caption or description of the table. And the data set also has the title of the page that containing the data set. And there are some other metadata like the license of the data set, but other metadata can hardly be used for the retrieval task. So we don't consider other metadata in our work. So the task of dataset search is that given a user query, we want to return a list of datasets ordered by their relevance with respect to a user query. And among all of the fields of a dataset, the schema labels usually represent high-level concepts. But usually there are like large vocabulary gaps with user queries and other metadata. So for this example, the location ABBR standing for location abbreviation can hardly appear in a user query. And it will cause the schema labels to be underutilized. So a natural solution to solve that is to generate additional schema labels. So for example, if we can generate the term city, place for the location ABBRs, so such terms are more general and can be matched with user queries. So the intuition comes from the data augmentations from for the task of dataset retrieval. So next, we'll introduce our method. So our method has 2 stages. So for the first stage, we'll train a schema label generator. And after we train the schema label generator, we're gonna use the generator to generate additional schema labels for every data set. And in the second stage, we will using the generated schema labels, also the original data set, to ranking the data sets with respect to a user query and get the final results. So the high-level goal of schema label generation is to learn a function that models the probability of a schema label giving the feature of a column in a data table. So to generate M schema labels for a column, we select the top M labels by the prediction of the learned model. And in this paper, we try to generate 5 schema labels for every column in a table. And next, I will tell how to learn the features from for every column in a table. So the motivation behind from recommendation system, and in this case, we model the data sets as users and the schema labels as items or products. So basically, we can build in 2 matrices. So the first matrix tells how many times the schema labels appeared in a data set. And the second will tell the co-reference of 2 schema labels. So we can build in the label matrix, and the entry is the shifted pointwise mutual information. It's also used to build in the word embeddings in the NLP context. So after building the 2 matrices, we use the cofactor model, which is from a recommendation system paper, and we can jointly learning the schema label representations. So after we do the matrix factorizations, we can learn the representation for data sets and also the schema labels. And we also use the features from one of our previous paper that will manually extracting the column feature by its data values. And we use the concatenation of 2 vectors as the final feature representation for column. So we use the random forest to train the schema label generator and generate 5 labels for each column. So after we train the generator, we will indexing the generated schema labels for every data set and ranking the data set with the schema label mixed ranking model. And the ranking model has 2 parts. The left part will rank or score the original data sets on text field and data table field, where the text field is a concatenation of title and description. And in the right hand side part will ranking the generated schema labels with respect to a query, and will do the weighted combination of 3 scores. And to scoring the generated schema labels, we represent the queries and the generated schema labels using fast text and use the word movers distance to calculating the similarity between them. So for the data collections, we create a new collection from data.gov, which which includes more than 2,000 resources published by US federal government. And we also create tasks and query collections. And each task here will describe information need, which will ask user to looking for relevant data sets. And we using the Amazon Mechanical Turk to obtain queries for each text. So we will have 20 queries per text. And for the relevance assessments, we annotated the top 100 datasets from our baseline method for each task using the Figure 8 platform. So we use 2 baseline methods. The first method is single field document ranking, where a dataset is considered as a single document. And we use BM25 to create 3 versions of this method. The first version will score on the concatenation of title and description. The second version will score on data table. And the third one will score on the concatenation of the title, description, and the data table. The second baseline is multi-field document ranking. So this method is just setting the weight to scoring the generated schema labels in our proposed model as 0. And this will degenerate to the mixture of language model. So by comparing the MDR with the proposed method, we can have a clear view of how much improvement based on the generated schema labels. So here as a result for the data.gov collection, and we calculated, here we show the relative indices 5 score, where we set the SDR or single document ranking method scored on data table as 1. And actually by comparing the single document representation, we see that by only scoring on data table, it got the worst result. And scoring on the combination of title and description, it gets the best result for single document ranking, which means the title and description are very important for dataset search. And it's interesting that by adding the data table for single document ranking, the results decrease a little bit. But for the multi-field document ranking, by using the data table, it can get a little bit improvement. And for the proposed method, it didn't show a huge improvement on the ECIR2020 score, especially when without using data table. And actually, when using the data table, it can underperform the MDR method a little bit, which means the data table are still underutilized, or it's very hard to scoring, to combining the data table into the ranking model. But for the relative precision at 5, the proposed models have higher precisions, so which may indicate that the generated schema labels are useful in this case. So we also test the method on another purpose, which is Wikipedia tables, annotated by John et al. In a web conference paper 2018. So for this wiki table, we first generate the schema labels for every table, and we use the method proposed in their paper to calculating the features, and each feature will represent one kind of similarity based on the query and the schema labels. And it's several predefined functions which will learning the features from the query amending and schema label amending. And we use the random forest to perform pointwise regression on their data set. So it's a supervised setting. And the results show that by combining their original feature and the feature learned from schema labels, the result can be further improved, which indicates the method is also useful for the supervised ranking. And we also do the testing on the unsupervised setting scenario, which is the same as our experiment on data.gov collections. And we comparing where in this scenario, the text represents the concatenation of page title of the Wikipedia page or table and the section title, and also the caption of the table. And we use BM25 on the proposed method to score different fields, and the results show that the result is not very significantly different. So the reason we assume is that for the Wikipedia, for the wiki tables, it's like entity forecast, so that the data values has a lot of rich informations, and without scoring on the schema labels or table headers, the model can have still a nice performance. But for the collection from data.gov, since there are a lot of tables that has a lot of numeric values, and you can hardly find a lot of entities, and it can hardly be used for the traditional ranking method. And most of the features will rely on the table headers or schema labels. So we also indicate that the dataset search and the table search actually are two different scenarios, although they seem like very similar to each other. And it's a very challenging task. So for conclusions, we first propose a schema label enhanced ranking framework for dataset retrieval. And it has 2 stages. In the first stage, it will train a schema label generator. And the generator will be used to generate additional schema labels for every dataset. And in the second stage, given a user query, we are ranking those datasets given a user query with original dataset content and also the generated schema labels. And actually, the first stage can be considered as a data augmentation technique for dataset search task. And we also propose a method to learn the feature representations for schema labels by a cofactor model. The model is from the recommendation system area. And we also create a new benchmark to evaluate the performance on dataset search, and the datasets are public available. And the experiment results show the proposed method are effective on both the dataset retrieval task and also the web table retrieval task. Thank you.
So many thanks for your nice presentation, and also in your case, you were perfectly on time. So we have some time for questions. Gustavo, there is someone who raised hands.
No, I can't see anybody at the moment.
No, and I can see any question in the question answering section, neither in the chat. So anyone has to ask questions. So in this case, I can, but also not even in this case, I would like to ask you a question. The question is the following. I did not catch very well, so the overall idea is very clear, and I appreciated it a lot. But I did not understand very well how the schema labels, okay, were identified. I mean, in your application to recommender systems, in which you consider users as data sets and products as the, let's say, the attributes, okay, how can you identify the labels that, let's say, can be associated to these products? Which kind of labels? Can you give me an example?
Okay, so here, like, this is a data set, and it has, okay, we only consider it has 1, 2, 3, 4.
Okay.
Right? So actually, we can create 4 instances, and each instance will represent 1 column, and will extracting features from each column. And also, we have another matrix that based on the cofactor model, and because each data set will have several different schema labels. And some of the data set will have the same schema label, so that we can build in the interaction between data set and the labels.
I see. So in a certain sense, you have to, let's say, compress a given category of labels into one common label that you select and you associate, right? Based on the features that you find in the correspondent data sets, let's say.
Yes.
Is that correct?
Yes, it's kind of like multi-label classification.
Right.
Every column.
Okay, right. That's clear now. Many thanks. So there is I see a question. You can also see it, Zihu, in the question answering box. Patrick Ruch. Hello.
Yes.
You see the question. Why did not you use the BioCAD collection?
Okay, so the BioCAD is is because I guess that is from the domain of biology, and actually for our project we want to build in a dataset search engine that is domain agnostic, and it's not like depends on each. So we want to like include all the domains. That's why we didn't use that.
Okay, many thanks. Are there any other questions? I don't see other questions. Okay, so I think we can thank you again for your presentation, and we can go on with our session. Thank you, Zihu, and have a nice evening. So we can go with the next speaker, who is Sean McEvney, who is going to present, to report on his research on overcoming low utility facets for complex answer retrieval. Are you there, Sean?
Yep, I'm here.
Okay, hi, I see you. Hi. You can share your screen. Okay, perfect. You
everybody
can
sees?
start. Yes, I can see what you can start. Thank you.
Wonderful. Okay, right, so thank you. I'm Sean McAvaney from the Information Retrieval Lab at Georgetown University. And today I'll be talking about our work with complex answer retrieval. This is work that appeared in the Information Retrieval Journal special issue on knowledge graphs and semantics in 2019. So I want to start out by stating that many questions that people ask online can be answered with just simple factoids. So for instance, when was the first moon landing? We can extract a date range, for instance, to answer that question from maybe a knowledge graph or maybe paragraph sources throughout the web. This has been an area that's been heavily studied, especially recently. But an area that is less studied and also represents a large number of questions that people might ask are more open-ended questions. So for instance, what was the cause of the space race? This is something that can't just be like brought down to just a simple 2-word answer or anything like that. Ideally, you'd want to look at a variety of different sources, kind of see different perspectives on things. Everyone is going to have kind of a different take on it, and then kind of form your own opinion of the answer based on a variety of sources. So the idea is to put together a variety of sources to answer this complex answer here. So the task of complex answer retrieval then is, in a passage ranking sense, to retrieve passages, perhaps delimited by paragraphs, and grade them by relevance to a particular question topic. So you'd want to find a variety of sources and then rank the ones that are most relevant answers to that question high, and the less relevant answers to that question low. And then you can read through this and kind of build an answer to a broader topical question like that. And eventually you might want to reconstruct the entire article based on this. So maybe you could have a particular topic with a bunch of different characteristics underneath it that pull from a variety of different sources to thoroughly explore a whole topic, not just an individual question and facet. So with that in mind, you can kind of frame complex answer retrieval as Wikipedia article generation. So you might have a query like, how is cheese produced? You can kind of correspond that to the topic of the query, which is cheese, and an individual facet produced, which kind of links up with the heading production under the cheese article on the Wikipedia page. So you can kind of see how those two link together. And then underneath there, you can have a variety of answers or paragraphs underneath that heading that kind of explore this topic. Now, for something like cheese, like obviously this article is already created and you can look at it. But maybe you'd want to go ahead and expand this article, or maybe there's a new topic out there that you want to produce an article for. Now, when it's constructed this way, when complex answer retrieval is constructed this way, the big advantage is that you can put together a large data set for training and evaluation of this. So in the TREC Complex Answer Retrieval 2017 task, they used a portion of Wikipedia using every title and heading combination of relevant articles as queries. Linking each of those up with the paragraphs underneath produces 5.2 million relevance judgments, which you can again use for training or evaluation. It's important to note here that these relevance judgments are incomplete, so they only correspond to the content that's underneath the particular heading. This is why the TREC car track actually ran and produced actual manual relevance judgments about these particular topics. And then a total of 30 million paragraphs throughout Wikipedia, which we can kind of treat as component answers or components of the answers for answering these questions. So again, this is work from the TREC CAR 2017 task, producing this data set here. Now, when we looked at this task and we approached it, we found that some of these facets match paragraphs better than others. So for instance, we have this query here, cheese processing curd, which would correspond to a question of how is cheese curd processed or something along those lines. When we look at the relevant answers to this, we find that CERD is actually, it has a lot of utility. It usually matches in relevant paragraphs. So you see these three answers, which all are constituent answers of this question, all use the word CERD specifically. And you would imagine that it would actually be quite hard to describe the answer to this question without using the term CERD. It'd be quite difficult to do that. So we consider CERD a high utility facet here because it matches these answers well. On the other hand, a query like what's the history of cheese, the facet of history probably won't match very frequently. In this first one, we've got history mentioned there as part of recorded history, and then these other answers, which are the components of this, don't use the term specifically. So these will be harder to match. So that kind of leads us to two main hypotheses in this work that we explore. One is that facet utility is a valuable signal for ranking answers. So informing a model of the utility of a given facet should help improve ranking performance. And our second hypothesis being that related entity mentions from a knowledge graph can address low utility facets. So we can make up for situations where you don't have much information or you're not likely to match the term history, for instance, in here by incorporating knowledge graph. So to further explore this relationship and to try to figure out what signals to include in a model, we look at the term occurrence rate, so the probability that a given term from a heading appears in a relevant paragraph, and we plot that against heading frequency, so how frequently how many articles a particular heading appears in. So over here with the very high frequency headings, we have things like history. History is found in a lot of Wikipedia articles. In fact, it's the most common heading that appears, but it only has a 3% term occurrence rate. So only 3% of articles actually, only 3% of paragraphs under the history heading actually use the term history. So it's very low utility. And we see this for other very high frequency headings as well. When we look at the lower frequency though, we see a much higher term occurrence rate. So with very low term occurrence rates, so something like CERD, which might only appear in one article, you may only have CERD in one article there, we have on average a 40% term occurrence rate. So these are much more likely to match relevant paragraphs. Right, so the takeaway here is that low frequency headings are easier to match than high frequency headings. And this actually is borne out in the data itself. So we try running two different ranking models, BM25 and a neural model called Packer. And we see that both of them have much more difficulty matching these low frequency headings. So these headings these high frequency headings that have a low probability of matching relevant paragraphs. So things like history are down here. Here we also see that although Packer, the neural model, does better on high frequency headings than BM25, it actually does worse once you start it does worse on these higher frequency headings. So that's also something to consider. On average, this results in an overall better mean average precision score, indicating that these neural methods might be relatively effective at this task of complex answer retrieval. One more signal that we considered here is the structure of the query itself. So we have the title and intermediate heading, and then what we call the main heading, the lowest most heading. And we see we plot the term occurrence rates using a kernel density estimation of all titles. We see that titles are very likely to match in answers. This makes sense because it's hard to talk about a topic without using the name of the topic itself. It's hard to write many paragraphs about cheese without using the term cheese, for instance. Right, so this is just an example, but this is overall titles. Intermediate headings like processing or history are very unlikely to appear in relevant answers. And the main heading, so the lowest most, is kind of, it could go one way or the other, so it doesn't provide much information. This is also maybe a different way of looking at what we saw on the previous chart, where these intermediate headings like history are also very high frequencies. There's definitely some overlap between these signals here. So we have signals that we think could be useful for determining whether or not something is likely to match in a paragraph or not. How might we go about incorporating these into a ranking model? We chose to use interaction-focused neural ranking models for this work. And a quick overview of what these look like. We've got the query here split into the main, intermediate, untitled components and a given document. We take the word embeddings of each to produce a similarity matrix, where each cell is the cosine similarity between the embeddings of the each query term and each document term. We do some operation depending on the neural ranking model to produce scores for each of those that are then combined using, say, a dense layer into a final relevance score. So this is the general architecture. We explore two different neural ranking models here. Packer, which runs a variety of square convolutions over the input, then does some K-max pooling, finally to produce a relevance score. And KNRM, which also uses the similarity matrix, but then runs soft Gaussian kernels over that, sums them together, and then combines those scores together using a dense layer. So those are a brief overview of the two neural ranking architectures that we explored here. At the time, these were two of the leading approaches. And we end up including these heading frequency informations during the combination phase. So what we do is we encode these basically as simply as you possibly can. Just an indicator, binary indicator of whether or not it comes from a title, intermediate, or main heading. And then the percentile information about calculated from the training data about the heading frequency. So here, green sea turtle is very infrequent, and ecology and behavior and life cycle are both very frequent. They occur in many articles about animals. And then we can just concatenate those with the matching scores in the neural ranking architecture and feed them on into the combination phase to produce a relevant score. So a relatively straightforward approach for including this contextual vector information into these neural ranking models. We also thought that maybe there might be different matching logic for different heading positions. We call this heading independence, where we take the title, have a matching layer for that, intermediate headings, matching layer for that, and main headings, a separate matching layer for that, and let these models learn different logic for matching different parts of that. What we find is that both of these seem to help. So with the Packer ranking architecture, it seems like either the heading utility of the contextualized vectors or the heading independence work, and both of them together don't provide much value on top of it. There's a slight difference up there, but that's not statistically significant. With KNRM, it seems that the heading independence is way more valuable than the contextualized vectors, although the contextualized vectors do also help. And then the combination of them both also helps a little bit further. So even though the KNRM model underperforms VM25 initially, using these approaches, it then outperforms VM25. Right, so that kind of provides some evidence for hypothesis one, that including facet utility signals can help inform these models about what's important to match and what's not important to match. Hypothesis number two is that including entity mentions from a knowledge graph can help address lower utility facets like history. To do that, we build a knowledge graph from the complex answer retrieval data set, where we take each entity, so each topic, each title. Here we have cheese. We take everything it links to, or every entity we extract from it, and then we link them together with the topmost heading. So in this case, we link cheese to prehistory with the label of history. And we do that for the entire training data set for complex answer retrieval to build up this knowledge graph. Here we only see everything that relates to cheese, or even just a segment of what relates to cheese. But this then is built up into a final graph of 14 million dribbles. Then we train knowledge graph embeddings on this particular graph, where knowledge graph embeddings are a combination of entity embeddings, relation embeddings, and some scoring function. We address sparsity of relations that are very infrequent by merging them all together into one heading, or one label for everything that's infrequent. And this kind of has the nice quality of the headings that are very infrequent, which are difficult to match, have the most training data on this graph. So that's a nice characteristic of this. We then train holographic embeddings from Nickel and others on this graph, and then we try two different variants. One where we use explicit links from Wikipedia, and then also entities extracted from DBpedia Spotlight. Then to include this information into the model, all we do is take the top K scoring entities from the target paragraph, link them up with the topic title of the query, and get the similarity score there. And then just include those additional similarity scores into the combination phase. What we find is that this can actually help improve the effectiveness of these higher frequency headings, these ones with lower utility. So we see the biggest gains of using this approach are this 41 to 60% and this 21 to 40% heading frequency, as well as in the 81 to 100 percentile. The 61 to 80 actually does slightly worse, but it was already doing pretty well to begin with. What exactly is going on here, and why does it seem to work? In the paper, we looked at a couple of specific cases. And here's one such example. We have this particular query of instant coffee history. We know instant coffee, that's a very concrete term. It should likely match in relevant answers. History is very general, it probably won't match. And then the model encounters these two paragraphs. So in this top one here, it's able to go from ranking this relatively low, so lower down in the list, 9 or 10, to first position when using the knowledge graph, because it's able to see that terms like World War II and other terms like that in this paragraph are very relevant. Whereas this other one, Instant Coffee, being, in this case, a Canadian artist collective from Vancouver and Toronto, here it sees that there aren't many entities that are related to this, and thus it goes from ranking this one very high to ranking it much lower. So this entity information does seem to be useful in cases like this. So that kind of provides some evidence for the second hypothesis that related entity mentions from a knowledge graph can help address these lower utility facets. In summary, we found that complex answer question facets can vary in in their utility, so how likely they are to match in relevant answers. The facet utility is a valuable signal for ranking answers. So even just informing the model of what might be likely to match and what's unlikely to match is an important signal. And finally, that related entity mentions from a knowledge graph can address low utility facets. So being able to know what types of entities are likely to match in these lower utility facets can further help. So thanks for your attention. I also have 2 short paper recorded presentations that I encourage you guys to check out if you have time. One of them is on zero-shot transfer across languages using contextualized language models. That's with Lucas Soldani, who's also on this paper, and Nazli Goharian. And then another one where we rank significant discrepancies in radiology reports. That's with Armand Cohen, Nazli Goharian, and Ross Felice. So with that, thanks everyone. And do you have any questions?
Thank you, Sean. It was very interesting listening to you. So are there anyone who wants to ask a question? I'm looking if anyone raised their hands. I don't see any question at the moment.
Hi, Gabriela. I do have a question.
Okay, okay, Gustavo, please.
So, hi, Sean. Thank you for the nice presentation. Regarding the entity part of your paper, how do you identify and filter entities? In the sense that, do you take all the entities that you find in the document, or do you filter them somehow based on quality?
Right, so we took 2 approaches with there. The first is just using the Wikipedia links that are already there. Those are usually tend to be high quality matches, but it's not exhaustive. So it's usually like the first time an entity is mentioned in a document, then it's linked, and then subsequent times it's not linked. So then because of that, we also looked at using DBpedia Spotlight entity extraction. And for that, we just use the default settings there. That has some threshold of, I don't remember exactly, but that's supposed to kind of balance precision and recall there of the entities that are extracted from it.
Thank you.
Yeah.
Okay, so many thanks, Gustavo. Are there any other questions? So your presentation was so clear that you raised no other questions.
Or I confused everybody.
No, it was very clear. So thank you very much for your presentation. And so we can proceed with the next speaker, who is Rui Henriquez, who is going, hi Rui, who is going to present the paper Moving from Formal Towards Coherent Concept Analysis, Why, When, and How. So thank you, Rui. You can share your screen. I can see. Okay, now it's perfect. Thank you.
Okay, thank you so much. Hello, everyone. My name is Rui Henriques, and I'm here to present this article on moving from formal towards current concept analysis. We'll explain in a second what is formal and coherent concept analysis. This work was conducted by Pavel with the help of Professor Zerbinha de Proença, and I'm a professor assistant in Instituto Superior Técnico, University of Lisbon, and a researcher in INESC-ID. So we had a challenge once we start developing these contributions, which was a very large document repository with many documents from the official journal of the Portuguese state, Diário da República Eletrónico. And that is a repository that consolidates all the legislation available for the country, so millions and millions of documents, and with decree laws and other legal documents from the different ministries, and almost no metadata. And this entity that contacted us, called Casa Nacional da Moeda, they wanted us to support document organization, navigation, document retrieval, okay? But in fact, we had almost no metadata, so this was a huge challenge from the start. So it would we would need a supervised analysis in order to help with those tasks. And here, so this is the story why this article then came about. So I will be briefly further motivating this problem, introducing some background. Sorry for the light, it was raining and now it's hitting hard. So then some essential notions, and then we'll move to the solution and some results. Okay, so the motivation we already know. We have this large text collection. We want to support document categorization, organization, navigation, and retrieval. Okay, and no metadata, so unsupervised problem. And the first thing we thought would be, okay, would clustering be a nice way of grouping documents? So in a way that help us, for instance, creating hyperlinks between those legal documents and help for instance, the navigation, and create some labels that we can, and some way of annotating the documents. But soon we noticed that that was quite impractical for this task that we have at our hands. If we think that we can map this collection of documents in a vector space model, we end up with a very high dimensional data set with a structural sparsity. If we would cluster, we would get disjoint groups, at least with traditional clustering, disjoint groups of documents. So, and in fact, what we have here are documents from, for instance, we can have a document that has many topics, some pointing to agriculture concerns, to legal concerns. So clustering would not be the ideal candidate for this problem. So, also because if we, once we analyze this data set, we had a lot of local associations. Okay, so if we want to go local and do some pattern mining on this repository, one very traditional way of doing that is formal concept analysis. So before introducing what is formal concept analysis, what is a concept, okay? So we have this large text collection. So we have a set of documents as the observations of our data set and the terms produced from TF, IDF criteria, or we can even aggregate some terms into topics. So we have here terms and or topics. So a concept is just simply a subset of documents and a subset of topics and or terms that have some coherence, okay? So topics that are relevant for a group of documents, okay? So if we want to apply formal concept analysis for this task for identifying these concepts, remember that those concepts are interesting because one document can then be associated with an arbitrary number of concepts, and we can also allow for overlapping concepts. So this helps us to provide ways of navigating between documents that are not necessarily fully related. So there are here some advantages. Once we try to apply formal concepts, let's just move to this previous slide. We need to map our vector space model, our data set, into a binary, a Boolean space model. So we need to binarize data. So one thing that always raises up when we end up in doing formal concept analysis is how do we binarize data, okay? The binarization thresholds, this problem associated with the discretization, okay, or the binarization. So the item boundaries problem, values that are close to this threshold of discretization. Also, regarding the predominance of topics, we are just looking for dense concepts, meaning that we are looking just for a subset of documents that have a set of terms or topics, okay? So we are not paying attention to the relevance of a specific topic within a document. So if we would be able to analyze the origin real value data set, the space vector, the vector space model, we could, for instance, identify concepts that are sensitive to the relevance of the topics on a subset of documents. So one example might be, okay, we are looking for documents that share like 5 topics. 2 of them are not that relevant, predominant, okay, and the other 3 are predominant, and this helps us characterize the content of the documents. Okay, so by doing formal concept analysis, you cannot do that because we are binarizing data, so we lose the sensitivity to the actually frequency of or relevance of topics within a document. So how do we go from there towards a more appropriate solution? This is the domain of coherent concept analysis. So ways of doing that without binarizing data. Okay, there's some attempts in the literature to do that, but not a comprehensive overview of how can we do that. What kind of patterns can we have regarding the expected level of predominance of topics per document? Okay, so and hence our contribution. So how can we provide a systematic way of discovering different concepts with customizable properties, meaning different patterns, different tolerance to noise. We want also to guarantee the statistical significance of the topics, because if we have a large text collection, we don't want, for instance, just two documents and 2 topics and say that, oh, this is an interesting concept. It might occur by chance, might not be statistically significant, okay? So, so we have this kind of requirements for coherent concept analysis. So how do we then look for this, search for this, or retrieve these coherent concepts within our vector space model? And our proposal is doing B-clustering or bi-clustering to do that, okay? B-clustering is a technique very well known in other domains, and the goal is precisely given a real value data set, let's just retrieve subspaces within this data set that hold certain properties of interest. Okay, so this is the aim of the B-clustering task, and it's very, as you will probably see, very fitting to our solution. So here is an example. So here we have a vector space model, just 3 documents and 3 topics, okay? If we do binarization in an attempt to identify concepts given by formal concept analysis, we might end up losing some important concepts. In fact, in this little data set, we are unable to retrieve concepts, okay? If we do coherent concept analysis, for instance, using B-clustering, we are able to discover different concepts with different patterns. So, for instance, a constant pattern or constant concept is something that, okay, these 2 documents share these 3 topics, and those topic 1 and topic 3 have hyperdominance on those documents, and then we have topic 2 with low predominance. Okay. Another type of pattern, it would be the order preserving pattern. So instead of looking to if a topic is or not predominant in a given document, we are interested in looking to the orders. Okay. So for instance, here we see that topic 1 is more relevant than topic 3, and topic 3 more relevant than topic 2, independently of the absolute values that we compute, for instance, using TF-IDF. Okay, so this provides us with the motivation, and now I'm going to go quicker to the remaining parts of the presentation. So regarding background, we know like the essentials of how we map our text collections into a data set, and how we can do some if we want to aggregate some terms, group some terms. We tested different ways of doing topic modeling in order to find concepts that are either composed just by terms or by terms and topics. Here is very important in this for this text collection, because sometimes words or even phrases isolated don't have a meaning. So the look for topics is important. Then on formal concept analysis, we already know that we need to binarize data to identify concepts. This is some background. There's a very nice thing that we can do with formal concept analysis, which is for ontologies or taxonomies, which might be relevant, not for the task that we have at hand, but this is has that nice property. On B-clustering, I already introduced more or less what we are doing here. So we are discovering this concepts, subspaces, subsets of documents and topics that have certain properties of interest. We usually call these properties of interest homogeneity criteria, meaning that the documents are correlated with these topics according to a certain correlation criteria. Okay, and we want also to guarantee their statistical significance. Okay, so another motivation on why B-clustering for coherent concept this is just general, it's still background, but we can already extrapolate for coherent concept analysis. So here on this slide, you have some interesting, nice properties of B-clustering, okay? If we think of pattern mining, to discover these local associations within data, usually traditional pattern mining have some problems that have been solved in the last 2 decades by B-clustering algorithms. So we can have patterns with different properties of interest, tolerant to noise, and other interesting things. So as you already know, our solution is to use B-clustering for the discovery of coherent concepts. And one class of B-clustering algorithms called pattern-based B-clustering have the ideal properties to answer this problem, because we can specify what kind of pattern do we want to find. Remember, on that slide where we saw the constant pattern, the order preserving pattern. There's other types of patterns. So we can say, okay, what kind of patterns do I want? Okay, this, that, and that. Okay, and then we can retrieve all of them. And we can also like parameterize the tolerance to noise, meaning I have a concept, maybe some of the values within my concept deviate from expectations, from the expected value that would be there to form the pattern, okay? So how much I allow deviations to occur within a concept. So that's noise tolerance or quality. So this class of algorithms, pattern-based declassing, also helps us to do that, and also have a way of sound statistical testing of the found concepts, which is exactly what we want here. I'm going to pass these slides. So if you are a more visual person, this is an example of what would be a concept in our DRE dataset, the dataset that we have. So each line would be a document. Here we would have 4 topics. So all these documents share these 4 topics, and we see that topic 2 and topic 5 have high predominance than topics T3 and T4. Yes, and the structure also an advantage. We can discover concepts, an arbitrary number of concepts with overlapping areas, and so concepts arbitrarily positioned within the data set. Okay, just keep in mind that here we are representing concepts, but they do not need to have contiguous terms or documents. Okay, this is just for simplify the visualization. Okay. Okay, so I already also motivate some of the advantage of pattern-based big clustering. Just one thing that I did not mention is that pattern-based big clustering uses many principles to guarantee the efficiency of the search, and still is able to provide optimality guarantee. So distance to the exhaustive search or the optimal solution, like all the concepts available within a data set, which is also a nice property. Okay, the paper is called on why, when, and how. So this was more or less on how. We have here a slide for on why, and we already know some of the whys. We want to use big clustering for coherent concept analysis because we want to avoid the drawbacks of formal concept analysis and be able to discover concepts with different patterns that might be meaningful in a given domain. Okay, and also hold out the properties of interest, such as statistical significance. And on topic representativity matters. So this is when we want like a comprehensive view of what's going on within a data set in terms of the concepts that are present within that data set. When to not apply. So when we have a Boolean space model instead of a real value data set, there's no benefit of using it by clustering, then we can apply formal concept analysis. Okay. And so I'm just going to finish with a few results. So here is just some statistics regarding our data set, which is a very large one. So before and after processing, after we remove some non-relevant terms, then we apply topic modeling, and we saw the different LDA, LSA, hierarchical Dirichlet process, and we saw the properties of grouping terms using topics. So here are some networks. Each node within a network represents a term. So are terms related? Okay. So semantic analysis, we can see that terms relate with every other term. So it's not the best way of extracting topics for our problem. So LDA and HTTP seem a better way of inferring groups of terms. So we now are working with topics and terms, okay? Because topics provide an important view as well into the data set. So this is on formal concept analysis. This is just some charts that show that sensitivity to the binarization threshold, which is an undesirable thing. This is one of the ontologies that I earlier referred to, okay? And so when we moved from a formal concept analysis to coherent concept analysis using B-clustering, we are still discovering concepts, but the concepts are now slightly different because we are now are paying attention to the representativity of topics and terms within a document, okay? So here is an example of within our text collection, the concepts, some of the concepts we have. So here, okay, here some of the concepts have multiple topics, okay? Each topic has multiple terms, okay? And it is not represented here, but then we have like hundreds of documents associated with a given concept. So this provides sort of an interpretability of what's going on. And an additional visualization of some of the big clusters that we found here. And yeah, some analysis on the tolerance if we want to tolerate noise on our concepts. And also there are statistical significance. So we were able to find many statistically significant concepts. Sorry, it's just like going over, but I'm not tracking time, so I'm a little afraid that I'm over time. So just to conclude, when we have these large text collections with different, challenging properties, we might want to go for discovering concepts, and we know that formal concepts have some disadvantage, so we might want to search for coherent concepts, and pattern-based big clustering is a way of accomplishing that. And this is very interesting because once we have our coherent concepts, then we can use them right away for document categorization. So a document has 4 concepts, so it will have those 4 labels. So if you want to navigate between documents, the documents that share concepts will be linked to each other. And also for document retrieval, this is more obvious how we can benefit from it. So thank you so much. And yeah.
Thank you very much. Thank you for your presentation. It was also in this case, I listened to a very interesting piece of research report. So we are ready for the question answering session. Let's see if there are any questions that have been raised for, okay, I see one question, but I am just looking if some of the attendees raised their hands. Apparently not, but there is a question in the question answering part that yes, you can also see. Yeah, Paulo Almeida, how does coherent concept analysis interact with time? i.e. the evolution of concepts and topics through a time-stamped set of documents. That's interesting indeed.
That's a very interesting, interesting question. And so here we are looking to this collection of documents, legal documents, in a static way. But in fact, the legislation is evolving. So one thing that we could do was to group documents in accordance with their time of occurrence, and we can come up with different ways of then inferring a data set from timestamp documents. Let's say in this way. So if we think, yeah, there's big clustering algorithms that are able to deal with temporal data. So if we think that we have terms and if we have a third dimension, which is time, in fact, there are, we can find sort of concepts that would be cubes, okay? So we can use tree clustering algorithms. So tree clustering would be the task to discover subspaces within three-dimensional data where we have our variables, which are the terms and topics, and how they vary along time. So here it's not the observations would not be documents, but would be like subjects or So because one document has one timestamp, but there's ways of discovering coherent concepts within temporal data, either using big clustering or tree clustering if you have three-dimensional data space.
Thank you. Are there any other questions? No, in the query answer, I have one, but I want to see if there are other people who have a question to raise. No, so I can ask my question, Rui. You mentioned in your presentation fuzzy concept analysis. Because when at the start you outlined the limitation of binary representation, and I agree with this, I think that your solution in order to cope with this is elegant, okay, the one of using clustering. But why don't you consider to use as a starting point a fuzzy concept analysis in which you have degrees that express strengths, let's say, among concepts. I think that you can also try to apply coherent concept analysis starting from that fuzzy framework. What do you think about?
Yeah, so in fact, we tested. So we first even tested fuzzy clustering just to get a soft clustering solution and allow for overlapping documents. And then when we move towards formal concept analysis, we also apply fuzzy concept analysis, which is good. Because I should have mentioned that because it solves some of the problems regarding the binarization threshold and the other things. Still, the fuzzy concept analysis is not able to solve the different types of patterns. So this, for instance, this order preserving pattern that we want one topic or one term to have like higher that has predominance than other and other higher than other. So this less trivial concepts are still hard to find using fuzzy concept analysis. Although it's fuzzy would be like in between.
In between, but then applying fuzzy by clustering methods.
Fuzzy by big clustering methods, I am the research a lot in big clustering. So fuzzy big clustering methods, they do the same way as other big clustering algorithms. They just use a different approach based on fuzzy theory. So fuzzy big clustering algorithm against the pattern-based big clustering algorithm. This could be an interesting question.
Be a development of your research. Okay.
Thank you.
So thank you very, very much. And so we can proceed. Last but not least in our session, we have the contribution titled Beyond Modeling, Understanding Mental Disorders in Online Social Media. This paper will be presented by Esteban Andres Rissola from the University della Svizzera Italiana in Lugano. Are you ready?
Yes,
Esteban?
thank you. Thank you very much.
Okay.
Yes, thanks for the presentation.
Okay, so you can share your
Yes, I will share my
your
screen.
presentation on the screen. And then...
Can you see my presentation?
Okay, very good. You can start.
Perfect. Thank you very much. So good afternoon, everybody. I am Esteban. I am a PhD student at Università della Svizzera Italiana in Lugano, Switzerland. And I'm going to present our work in collaboration with Mohamed Alian Nejadi and Fabio Crestani, titled Beyond Modeling, Understanding Mental Disorders in Online Social Media. So the first thing that I would like to do is to introduce what are mental disorders. It comprises a broad range of problems, mostly characterized by some combination of abnormal thoughts, feelings, behavior, and relationship with others. Some examples are depression, schizophrenia, eating disorders, and many others. And why it's important to take into consideration mental health? Well, in the last year, around 83 million people have suffered one or more mental disorders in the European Economic Area countries. And in fact, the lack of a timeless treatment could lead to psychotic episodes, thoughts of self-harm, and at its worst, to suicide. So what can we do from the side of computer science? Well, research on language and psychology has shown that several useful cues about individuals' mental state, including their social and emotional conditions, can be discovered by examining or studying the patterns of language use. Language attributes could act as indicators of the mental state, personality, and even of personal values. And this is because such latent mental related variables are encoded in the words that people use to communicate. So also lately, in the last years, we have seen how online social media platforms such as Twitter or Reddit or Facebook have become increasingly popular, and more people are using these platforms to share their feelings and moods on a daily basis. This actually gives a unique opportunity to analyze the digital traces left by these individuals, and to study and to analyze their mental state and evaluate it at certain points in time in order to determine the onset of a disorder. And this is a task called online mental state assessment. So, motivated by this, we think that it's necessary to conduct or to carry out experiments in order to gain insights on how the language of individuals affected by mental disorders, it's different from control individuals, but also it's interesting and important to understand if there are differences in terms of language, between individuals who are affected by different disorders. So in this way, by extracting this information from the posts of that are written by social media users, we can visualize and put into numbers all this information, which can help health practitioners to perform a more comprehensive assessment of the individuals. So in this work, what we do is to conduct a thorough study of various dimensions of language, and we provide several methods for visualizing these dimensions that we decide to analyze. To this end, what we try to do is to answer the following research questions. So the first question is, how different is the language of users affected by mental disorder in comparison with control individuals? To what extent is the language of depression, anorexia, and self-harm, 3 mental disorders, different among themselves? And the third research question is how language-specific and emotional information can be visualized in order to be used by psychologists during the diagnosis process. So, as I said, to perform this analysis, we're going to use the IRISC 2018 collection. This is a collection which is part of the IRISC challenge from a CLEF conference, and it's a set of posts which come from Reddit. If I recommend you to go to the reference paper to get more information on the collection if you're interested. And in particular, it has 3 different disorders: depression, anorexia, and self-harm. And for each group of positive instances of that disorder, we have its respective control group. And some statistics are taken from the corpus. So the first dimension that we're interested in to study is the vocabulary uniqueness. So we want to see how similar and different are the unique set of words which comprise the vocabulary of individuals affected by mental disorder and control individuals. Why? Well, the idea is to discover the common vocabulary, but most importantly, to determine if there are any class-specific words, that is, words which are specifically used by a particular group of users. How we're going to do that? Well, we're going to study the relative size of the intersection. Since we have sets, we're going to take advantage, in particular, of Jacquard's index. Given this study, what we can see is that the language, the vocabulary in particular of individuals who are affected by depression or anorexia, it's it's more similar to the control group with a Jacquard index of 59% and 65%. It's important to recall that Jacquard's index ranges from 0 to 1. So a value of 1 or 100 or 100% would mean that the sets completely overlap, while values closest to 0 would mean that the sets are dissimilar. And also in the case of self-harm, we can see that that the set of words is much more diverse in comparison with the control group. One interesting example of this analysis is are these terms, which are some example of terms that are only used by that particular class. So in the case of depression, we have the term self-harm and the word trazodone. And in the case of anorexia, we have the words anorexic, depersonalization, and other medications. It's interesting because, for example, in the case of anorexia, the personalization, it's a disorder which is associated to the way that we see ourselves with a negative connotation. The second dimension that we study, it's the word usage. So the patterns of word usage in particular. To do so, we're gonna compute and compare the language models from each of the classes. And what we want to achieve with this, well, we want to quantify the differences in terms of the probability of using certain words that a class use more has a higher frequency of using certain words more than others. And as I said, to do so, we're gonna use the language models, want to compute the language models from the corpus and the classes. And in particular, we're going to study visually how the probability distributions look like. And we're going to support that with the computation of the Kullback-Leibler divergence. Here we are seeing the result of this study. And as we decide to use as a baseline, the Kullback-Leibler divergence between the different controls. And as we can see, there are differences in terms of the language use. And that can be also visually supported by plotting the distributions obtained. So one interesting thing to note here is that on the picture on the right, where we are comparing all the mental disorders among them, it's not so easy to spot differences. While on the case of a bipolar mental disorder and the control group, it's more noticeable. Moving on to the other indicator that we analyzed, the other signal, it's the psychometric attributes and linguistic style. So in this case, we're going to study function words. It's important to study function words because they denote a lot about the way that our writing style. And most of these words are part of what we know as stop words. And one interesting example why it's important to study them is the case of individuals who are suffering from depression. It has been shown that these individuals tend to use much more frequently the word I than healthy people. And also we want to study topic-specific vocabulary. To do so as I said, why we want to do this, because we want to determine the specific stylistic patterns in the way individuals write. And to do so, we're going to use the LWIC, which is a software equipped with a set of dictionaries manually constructed by psychologists, which covers several psychologically meaningful categories. And as I said, which are very useful to study the linguistic style patterns of the way individuals write. Here we are seeing the result of this study. So first, I'm going to focus on the topmost image. The y-axis in both cases is representing the proportion of documents for which we have found at least one word from that category. These are a selection of the categories from the LWIC. And the stars are denoting statistical significance. So in this case, for instance, if we take the adverse, it means that the individuals affected by depressions show a statistical significant difference in terms of the use of adverbs with its corresponding control group. And one interesting thing to note here in this plot is that even though there are significant differences between individuals' positive instances of mental disorders with their control groups, we couldn't find any significant differences between the mental disorders. So no differences between depression, anorexia, and self-harm, except for the case of these 4 categories in the lower image. In this case, we have the hat symbol, which actually it's denoting statistically significant difference between depression and anorexia and between self-harm and anorexia. And what we can see is actually that there is a particular topic-specific vocabulary for the case of anorexia, and it makes sense since it makes quite a lot of sense actually, since these categories are mostly related with the way the individual see himself or herself, because we have words related to body, to health, to food, and so on. Then we're going to study also the emotional expression. What do we want to study with this? Well, we want to know how individuals who are affected by mental disorder emotionally expressed in their posts. While we all individuals reveal a lot about the emotions, feelings, and attitudes that we have in the way we use words, in the words we use actually. And how are we going to achieve this? Well, we're going to use a set of emotion lexicons, which basically relates words with the emotions that that particular word evoke in order to word connotations. So the results, one of the results of these studies that we are seeing here, it's in terms of the proportion of usage. As we can see, again, we see significant differences in terms of the use of emotions between positive instances of mental disorders and control individuals. And one way to interpret this is that we can say that on average, affected users tend to share more emotions, or to share emotions more regularly than control individuals. And also, we studied the frequency correlation, the frequency of usage of the different emotion words. And here it's interesting to see, for instance, there are many examples as this, but this is particularly interesting. In the case of surprise, if we see surprise and a negative and positive balance for the case of self-harm, we can see that there is almost no correlation, maybe approaching to a negative correlation, while in the case of control individuals, we can see that actually there is some correlation. And the same happens with the case of fear and anticipation. We can see that on self-harm, there is, again, no correlation or approaching to negative correlation, while in the case of control individuals, the opposite occurs. So, wrapping up, in this work, we have reported results from a deep analysis in order to better understand the language and the differences in the language between individuals who have some mental disorder and control individuals. We study the vocabulary, the psychometric attributes, and emotional indicators. And we discovered several interesting differences that actually could help a predictive system and a health practitioner, as I said in the beginning, to perform a more comprehensive assessment of an individual. Also, we discovered that capturing differences between individuals who are affected by different disorders, such as self-harm or depression, it's not such easy, and that requires the aid of a professional. As a future work, we'd like to investigate if these findings also hold for other social media. Recall that the collection comes from Twitter, sorry, it comes from Reddit, and we would like to see if, for instance, these differences holds for Twitter, where we have other restrictions, such as the limitations in terms of characters. We'd like to use this information, to leverage this information to improve actually the actual predictive systems. And we would like to study also other modalities of data, such as images. So this has been all. I thank you very much for your attention, and I would be happy to receive your questions.
Thank you, Esteban, for your presentation. And are there any questions? There are people who want to, yes, I see. First, let me check that. Okay, Marco Viviani raised his hand. Gustavo, can you give him the possibility to talk?
Yes, he already has my permission.
Hello?
Yes.
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 Thank you, Esteban.
Thanks.
Thank you for your presentation. I would like to ask you which kind of tool or dictionary did you use in order to evaluate the emotions? Maybe I lost something during your
yes, thanks for the question. Very nice question. Also, I'm seeing that in the Q&A there is a question of David Lozada, and he also asked the same. So I'm going to take advantage to answer both. In the case of the emotional indicators, we use the NRC lexicons, the ones developed by Saif Mohammed.
I know. And
yes.
Did you employ it on the already publicly available dataset, right?
Yes, exactly. On the iRisk dataset, which is publicly available. Yes.
I just keep this opportunity in order to ask you if you have tried to use your study on real, I mean, it was a real data set, but on data that you directly crawled maybe from some microblog platform, for example.
No, we have not crawled any data. We have used all this time publicly available collections, such as the one from the iRisk one, also the one from CLEF, which is on Twitter. But would be interesting actually to, yes, like you suggest, to see what we can find out by making a crawling of of some of either Reddit or Twitter or some other social media.
Okay, and in the publicly available dataset, the tweets do you have information about the dates of the tweets?
In the case, in both in the case of the iRisk dataset, which is from Reddit, yes, there is information about when the posts was created. But one thing to take into consideration is that it's the UTC time, so we cannot know exactly what time of the day was because it's the server time. Okay. That's something important to take into consideration. In the case of the CLEF collection, also there are timestamps, and I don't remember if it is again UTC time or if it is the actual time.
Okay, it was just because maybe it would be interesting to evaluate the emotions also with respect to the time, no?
Yeah.
Maybe the same person
yes.
During different days at different moments of the day. Okay.
Yes, that would be actually very interesting. Thanks for the suggestion.
Thank you in any case.
So thank you to Marco Viviani, and thank you for your answer. There is another question from Ting Su, University of Glasgow. Please go.
Hi, I have a question about your data set as well. So do you know that, so I as far as I understand that all the data set, all the people that has classified as having a mental disorder has their diagnostic done.
Mm-hmm. Yeah.
So I wonder if all these data set is before or after diagnostic, because I remember someone mentioning that there's a diagnostic effect, that the diagnostic itself would pose effect of on the patient and how do they behave and how do they talk and how do they present themselves online. So did you chat? So do you have a data set before the diagnostic?
No, I mean, in the case of the iRisk data set, there are three cases, let's say. So you have user for which you have information before and after the post in which they declare that they were diagnosed. You have people for which you have information, you have posts after they declare publicly that they were diagnosed, and people for which you have before they declare that they were diagnosed. In this case, we have not done that study so, let's say, disseminated by these categories, but I think that could be interesting, actually, to check how these indicators actually behave before and after the the user at least declares that has been diagnosed with the mental disorder.
Okay, thank you. And the second one is you mentioned the unique words among group of diagnosed people and the controlled group. So did you just count the word itself, or did you try to categorize them? For example, some of them can be categorized into like well-being, some of them may be categorized into politics, like that. So did you find any difference between the categories used, or is it because every data is collected within the patients group, so they only talk about their disorders?
In this case, no. We extract the words. We didn't categorize them. One way could be maybe also to which actually we're planning to do, and we have done something. It's to study the topics which are discussed. But no, we have simply extracted the words which were unique for each set. But I assume that since my intuition is that since all the posts and comments are taken from the feed of these users, and they actually talk and participate in many subreddits, and they talk about everything. It's not like they are talking all the time about the disorder, which actually it's what makes the task hard, because the idea is to discover which are those patterns, latent patterns in the way they write. So I think that doing the categorization would be interesting also to find out something. Yeah, thanks.
Thank you. And my final, sorry, it's very long, but my final
yes,
comment.
please, I just ask you to be short in posing the question and also in answering, because we have 2 extra questions after. Thank you.
Okay, just last question about the cultural and country difference. So as far as I understand, the different medication and different terminologies used among Asian, Europe, and American countries. So do you have the information about the location?
No, unfortunately, in the case of the risk dataset, we have no information about the geolocation, which actually would be nice to have a dataset with that. If I'm not wrong, there are no data set, at least for this task, for the automatic assessment of mental disorders, with that information. If there are, I'm not aware of them.
Thank you very much. Thank you.
You're welcome.
Okay, so there is, if you look at Esteban at the question answering box, David is going to give a suggestion, but there is Javier San Cruzado who is asking a question. You can answer him first, and then Paolo Almeida.
Okay, so I will try to answer Javier's. Let me read.
Javier. Might there be some overlap between the different disorders that might make differentiating them harder?
Yeah, actually what we found out is that except for the case, maybe I can show again from the presentation to clarify my point. Thank you, Javier, for your question. And except for the case of the topic-specific vocabulary, yeah, there is intersection between the mental disorders, and actually that's what makes it difficult. Also, it's true that at sometimes there is a phenomena called comorbidity, which means that an individual who is, for instance, affected by depression could be also affected by all other mental disorders, such as anorexia, or one thing could lead to the other. So that could make that the thing to determine difference between them, between the disorders, much more difficult.
Okay, then the very last question, Paolo Almeida.
Yes.
Okay, you have seen.
I want to thank David for the suggestion. Thank you very much.
And can you see the question of Paolo?
Yes, control groups.
Follow up to last question. If you split control groups in 2, how many unique words would there be in each one?
We have taken the control group as, each respective control group as one group, let's say, but would be interesting to to see what happen if there are more actually between the control users. Maybe there are some differences, or maybe there are some control users will look more like individuals who have some mental disorders. That would be something interesting to discover.
Okay.
I don't know if I answered Paulo's question with that, but anyway, we can discuss there offline, no problem.
Paulo is not reacting. I suppose that silence is an agreement. Okay. So I believe that we can, okay, first of all, I thank you, Esteban, for your presentation and for answering to the question.
Grazie mille.
So I am going to close this session. The session worked very well as the entire conference. This online conference is working well indeed. Of course, it is sad to be here for the reason that we all know, and I really hope for all of us that the situation can be soon improved, and then that we can meet soon in person, because it's of course much better to see each other and to talk and to be together. And so let's hope that everything will be solved very soon. Here in Italy, in Lombardy, I am in the region which is in the core. We are slightly improving, and so I wish all of you that this can be soon overcome. Thank you very much. I see that maybe, okay, thank you, Rui, and thank you, everyone. So please spend a nice evening and a nice rest of days. Hope
Thank you, Gabriela.
Bye, grazie mille.
I just have two gentle reminders to make, is that there's going to be a social event on room D, the details are in the chat. And a gentle reminder to the attendees that they can participate in one-to-one sessions with the sponsors in the Slack. Thank you.
Yes, thank you, Gustavo, for reminding. This is very interesting also to see an online social event. So please, let's virtually meet later, okay? Bye-bye to everyone. Ciao.